Okay, it is 9 o'clock, so I think we should start, and hopefully a few additional people will trickle in during the first talk. So Ren was unable to be here in person this morning, so he joined online, and he will give the first talk on deep convective transport in CAM-CAM is sensitive to nudging analysis choice.
All right, thanks, Nick, and thanks everyone. Can you hear me okay? Just to verify quick.
Yes.
Yeah. Okay, excellent. All right, yeah, thanks for the introduction, and good morning, everyone. I apologize I was not able to be there in person today. We had a sudden daycare emergency and suddenly, unexpectedly ended up with 2 kids at home. So apologies for missing out, but happy that I still get the opportunity to give the talk. So as Nick mentioned, I'm going to talk about the sensitivity of deep convective transport to, I guess, a couple of different things. One is nudging analysis, and the other one is a upcoming parameterization development. Before I move on, especially want to acknowledge Simone Tilmez and my collaborators here, and I should also shout out to Rich Neal as well for the help with the parameterization development as well. And there's a great many other people, I can't list them all, for their help and contribution to the project. And I think I have to come over here. How do I do this? Okay. So as I mentioned, the goal of this project here is to characterize how deep convection changes as a result of the different analysis product that you would use to nudge, as well as an upcoming parameterization development with the Zhang-McFarlane convective parameterization that's developed by Rich Neal. I'm referring to this as ZMKE. It's a kinetic energy addition that sort of considers the kinetic energy of a parcel once it reaches the level of neutral buoyancy. And so it's intended to deepen convection, and we'll look at the sensitivity of that. And importantly, specifically characterizing the resulting impacts on atmospheric composition that those changes in convection have. I'm going to just for simplicity here, the suite of sensitivity runs is nudging toward ERA 5 reanalysis, as well as nudging toward MERA 2 reanalysis. And then for each of those, we have the standard ZM, as well as the ZMKE parameterization development. And I should mention too that the ERA 5 is available every hour, and so we actually nudge every hour. And MERA 2 is available every 3 hours, and so we're nudging every 3 hours. But ERA 5 has that better temporal availability, and it also has a higher native resolution. So we're expecting this to undersample the convective environment less than MERA 2. And I'd like to just also point out that just as a note, so the question doesn't come up of what's my model configuration. This is an older model configuration. We're using 32 vertical levels, the previous low top version, as well as a 1 degree finite volume here. We have posterior CO emissions, courtesy of Ben Gobert, who worked on those and sort of calibrated those to match well with Moppet satellite retrievals. And we're using updated CAMS mosaic emissions as well. And this is CESM2 as well. So one obviously area of future work is going to be to move into CESM3 with this. So I don't want to frame too much else here. So I'm just going to jump right into it. We'll be happy to answer any other questions that come up as a result. But here's the 4 different simulations. We have the ERA 5 nudging on the left, MERA 2 on the right, and some observed convective cloud top observations on the bottom there as well. And we're looking at deep convective cloud fraction, and I'm using 200 hectopascal as just a subjective to screen for that. And I've also had to subset the models for convective precipitation above some threshold. And the reason I do that is to conceptually match with the observations for some compatibility there. And this evaluation is for a 4-month period in the summer of 2022 as well. So I think what jumps out here is actually as you move from the top row to the middle row, which is moving from the standard Zhang-McFarlane to the ZMKE parameterization development, you see additional convection, additional deep convection, and I would argue that that improves the representation of deep convection compared to observations. And I'll also mention too that as you would move from the right column with MERA 2 to the left column with ERA 5, you're also improving or increasing the amount of convection as well. And I would again same thing, argue that that's improving things relative to observation. So it would seem that nudging towards this higher resolution ERA 5 product is improving our representation as well as the parameterization development as well. looking at that in terms of the depth of convection, so not just the convective fraction. These two simulations are with the standard ZM and the ERA 5 and MERA 2 nudging, and then the observations are in black. Right away, it jumps out that both of these appear to be a bit too low. And I should mention too, this is 20 south to 20 north, so it's in the tropics comparison here. I would argue that ERA 5 is doing a better job, but both of them are too low in terms of, we have more convection with ERA 5 nudging, and also tends to maximize a little bit deeper. But nonetheless, we have a bit of a low bias there, and I'll address that again in a second. But the question the crux of the presentation is, how does this impact atmospheric composition? And so here are difference fields in carbon monoxide mixing ratio at 3 different levels in the upper troposphere, lower stratosphere. And you can see that there is indeed a signal in terms of how this impacts atmospheric composition. And I should say too, if you're not used to thinking about composition, CO is sort of the quintessential tropospheric tracer that we use for seeing a signal from or influence of the or the surface and sort of anthropogenic emission regions, as well as, I guess, you could have biomass burning, but it's really a surface tracer that we see at different levels of the atmosphere. And so what you see here is in the lower stratosphere, particularly at 70 hectopascal on the top there, you actually get an increase in CO by about 10 to 20% when you nudge toward ERA 5. And I don't have observational comparisons here. I do think that we should be evaluating these with available observations to understand whether or not this is actually making things better or making things worse. But nonetheless, I think it's worth just pointing out that there is, in fact, a sensitivity there. And then next, putting side by side here, the runs that use the ZMKE parameterization. And this is sort of one of the primary rationales behind the parameterization development, is that it increases the depth of convection in the model. And so when we use ZMKE compared to just standard ZM, maybe we're still a bit low in terms of convection. That being said, there's a clear improvement with both nudging products to move towards those higher deep convective cloud tops, and that's definitely improving things compared to observations. So I think that that's clearly good news, and wanted to make sure to point out that anticipated development is going to make things better here in terms of the cloud top. However, I would also like to mention, again, from the composition side of things, these plots are difference plots, actually looking at the impact of ZMKE versus ZM. And what we're actually looking at here is NOx, nitrous oxides in the model, and the generation of NOx by lightning goes as something like cloud top to the 5th power in the chemical mechanism. And so when you do improve the cloud tops, when you move from the lower bias low cloud tops to these cloud tops that are higher, there's a significant impact in terms of changes in NOx. In fact, in the tropical lower stratosphere, the impact is about 20 to 40%. I've actually changed the color bar from the previous slide with CO. And in the upper troposphere at 200 hectopascal, where you expect a lot of the deep convective tops to be, we have up to an 80% increase. And so this is not me saying that this is bad, that ZMKE is going to hurt us in terms of composition. I think it's just a note to make to everybody that as we sort of tweak the dynamics, we'll want to keep an eye on how this impacts composition. And I think some tuning and evaluation with observations is going to be required there. I'd also like to spend a little time on a case study. This actually is, for full transparency, is what initially motivated us to look at the different analysis nudging data sets. And this is a particular case from some airborne observations that were taken in the summer of 2022 during the ACLIP campaign. That's the Asian Summer Monsoon Chemical and Climate Impact Project. And this project was geared towards understanding the composition of convective outflow from Asia. This is a unique region where you get the coupling of enhanced anthropogenic emissions with this sort of seasonal maximum in deep convective uplift. And so these airborne observations are taken in the upper troposphere. And this was sort of a perfect storm event from August 19th where we have deep convection. Actually, I think I have a laser pointer here, where we have deep convection here positioned over these enhanced emission regions in eastern China. And the large-scale winds, these are the vectors from ERA5 at 200 hectopascal, are transporting the outflow from this convection out over the Yellow Sea. And I've colored the airborne tracks in terms of the observed CO along the track, and you can see, everything along the Yellow Sea there is in excess of 200 hectopascal. Or 200 parts per billion, excuse me. It's worth noting, again, if you're not used to thinking about composition, the science team more or less confirmed that this is a record-setting pollution transport event that was sampled here. And so, although we're used to a lot of times looking at things on longer timescales, and this is one particular event that we sampled, we don't think that this was anomalous in terms of its frequency. It was anomalous in terms of us being there to sample it, but it was not anomalous in terms of the frequency that it would occur. And I should also mention too that although I'm focusing on CO because it's a really easy tropospheric tracer to sort of emphasize, this sort of outflow plume was associated with a very enhanced loading of very short-lived chlorinated substances as well. And this has implications for ozone depletion as well for a lot of these shorter-lived substances that are not regulated by the Montreal Protocol. So anyway, all this to say, it's important for us to want to try to get this sort of representation of this sort of event correct so that we can have this representation on those longer timescales as well. Also worth mentioning for the motivation standpoint is when we sampled this, or when this was sampled in the field, the in-field chemical forecasts struggled in general to represent this because, again, it was a record-setting sort of previously unheard of pollution event that was sampled in the upper troposphere. So this is of altitude profiles of CO, and you can see the two different forecast models that we had. We had our version 0 of our Musica model with the spectral element with regional refinement to 25 kilometers over parts of Asia. And then the NASA GEOS model was also included as well. And then you see all the observations from the campaign are in gray, but the observations specifically from that August 19th case are in black there. And so you see just how anomalous those are, and the forecast models don't really seem to have that in there. So again, all this to serve as motivation for wanting to try to represent this case. So now we can come back to our four sort of flagship simulations that I introduced earlier and see how well we're doing at representing this. This is CO at 200 hectopascal, and ERA5 simulations are on the right. The MERA2 simulations, or ERA5 is on the left, MERA2 is on the right, and ZM simulations are on top, ZMKE on the bottom. And we all like animation, so I'm going to animate these. What you're looking for here, it's about a 2-day animation. We're looking for this plume sort of over eastern China and seeing whether that's represented in these simulations as well. Let's see here if I can get this. Oh, no. No? Is it not going to play for me? One moment. There we go. So in all of these simulations, you do actually get an outflow plume, a CO plume that forms over eastern China, gets transported out into the LOC region. The representation of these plumes are wildly different depending on the parameterization you're using, as well as the nudging analysis product that you're using as well. So I think it's worth pointing out these very different sensitivities when you're looking at some of these small scale events here as well. Moving on here, this is one freeze frame from the airborne sampling time. And I just want to point out that I think all of these simulations actually do put a relatively polluted plume into the upper troposphere. But for whatever reason, the ZMKE doesn't really seem to position the most polluted outflow over the LOC where it was sampled. And it's really only the ERA5 and ZM run, which is up here in the upper left corner, bring the laser pointer back, that actually positions this primary outflow plume at the correct location and at the correct time as well. And so I don't necessarily have a big take home here. I'm going to look and analyze a little bit more about how these different plumes evolved in these different simulations in a second. But I think it's worth pointing out that that seems to be, at least for this event, the best simulation that we have here in this set of four. I think it's also worth interpolating the model, since we're looking at a small scale event and seeing the timing of this plume and how sort of the representation of that nudging went. I'm looking here at actually interpolating the two ZM model simulations to the airborne flight tracks, both in space and in time. The red curve is ERA5 nudging. The blue curve is MERA2 nudging. The black dots are the airborne observations. And then I have the flight track and altitude also with time here as well. And I think it's worth pointing out here too that the altitude really in that middle section of the flight isn't really changing all that much. And so it's really that you're flying in and out of this plume, and the timing of that plume and the location of that plume really is excellently represented when you're nudging toward AR5. So I think that's good news, and also shows us, I think, that the probably the more narrow in terms of space and time of the event that you're looking at really benefits extra from the nudging toward the higher resolution analysis product. I'd like to, or actually, there's one more thing I wanted to mention here. I'm cheating on this, actually. The observed CO is on an axis all the way up to 300 ppb, as I mentioned. The model still is not quite giving us the exact magnitude of the CO that was sort of the record-setting CO plume. Nonetheless, I want to emphasize that ERA5 nudging is improving that representation, all else equal. And there's maybe opportunities for us to look at emissions and other things that sort of, and also then the representation of the convective transport that goes into that as well. I know I'm kind of starting to come up on time here a little bit. So I want to just spend the last little bit here talking about the sort of dynamics that allow for, or the changes in dynamics that allow for the different representations of composition. So this plot looks like the CO plots that we were looking at before, except these are updraft mass flux coming from the ZM convective parameterization. When you're nudging toward ERA5, you actually see quite a bit more mass flux over this convective region. I've done this pink box here just to signal the convective uplift region that we expect. All four simulations actually do a good job of putting the convective uplift plume in the right place. However, it's just worth noting that the ERA5 nudging considerably intensifies that updraft mass flux. And here's the average mass flux profiles at the location of maximum upper troposphere mass flux over that uplift period and within that little pink box that I had on the last slide. And so the red and orange are for the ERA5 nudging, and the blue and the cyan are for MERA2 nudging. And so I think it's worth pointing out that, as I mentioned on the last slide, where you have more mass flux with ERA5, not only do you really seem to get more mass flux, but also the mass flux peaks at a higher altitude layer, and there's just generally more of it. And so this is a pretty considerable difference, I think. And then, these are CO profiles at those same points, basically trying to understand the relationship between the convective mass flux from ZM and how that translates to composition impacts. These are the CO profiles on the right are heavily averaged just because the pressure levels are different depending on where you are over land with the topography. But nonetheless, I think it's interesting that the ERA5 nudging plumes that have the higher altitude and higher quantity of mass flux are then also bringing a higher altitude of detrainment and also additional CO that's being transported into the upper troposphere. So that's kind of the crux of why we get a better representation when you're nudging toward ERA5 for this particular event. And I think I'm running too low on time here. I just want to mention, since models are the ultimate sandbox, we did. I did a sensitivity run where I doubled the emissions, and I also doubled a buoyancy scalar just to see if we could get 300 ppb of CO in the upper troposphere. And you are able to get that when you juice up that run. However, I think the realism of that is questionable at best. So I'll save that for later. Just to go quickly to the take-home messages here. Tropical deep convection abundance and depth improve with both the nudging toward AR5 as well as nudging toward compared to MERA2, as well as the parameterization development for ZMKE compared to ZM. We do see global composition being altered when nudging toward AR5 and when using ZMKE, so it'd be important to compare with observations and do some tuning to the composition as well. And then for this prominent pollution transport event, nudging toward ERA 5 improves the concentration of CO and also improves the timing of the event as well. But I just want to say as a last broad statement that we usually think about improving the dynamics as the way to improve composition a lot of times, but I also think that using composition as a way to improve the dynamics is also an important avenue for our model development. So with that, I'd be happy to take questions if there's time, but thanks for your attention.
So I think if anyone in the room has questions, the ceiling mics work. There's several questions we can take, and there's also a question from Julio. So June first.
Hi, Ren. It's June here. Very nice work. I think it's very interesting to see how much difference when you nudge between MERA2 and ER5. I'm wondering if you're using the new nudging approach for all the case, and are they using the same nudging time scale? Maybe you mentioned I missed it. And also, if all this parameter you nudged, Julio has a question, UV or T, are they interpolated into the model levels? And if they're all, everything is the same, I'm wondering if you looked at the raw data, say how much actually the MERA2 and ERA5 data difference is there that caused so much difference in the convection? Thank you.
Yeah, thanks for the question. So I can't actually tell you if we're using the newer, I think Rich actually asked me that question at one point also, and I wasn't sure how to answer it. I don't know if we're using a newer nudging approach. We are nudging to U, V, and T. We are not nudging to Q. The nudging coefficients are all the same, but the ERA 5 is nudged every hour, whereas MERA2 is nudged every 3 hours. So that's another thing that I've done a sensitivity run to also is nudging ERA 5 every 3 hours to see if it's really the fact that you're just nudging every hour, or is it the fact that there's more information content in ERA 5? And the answer is it's a little bit of both. ERA 5 has more information about the convective environment, but also the hourly nudging seems to be playing a role in that as well. And then, yes, I've looked a little bit at the differences between ERA 5 and MERA2. What I was trying to do actually was understand, and actually I might have, if I go quick here, I think I have an extra slide on. This is actually the moisture fields. These are actually the model moisture fields. So I was looking at the moisture fields in ERA 5 and MERA2 as well. There's more moisture in the low-level environment at 850 hectopascal in the ERA 5 simulations, and I think that's what leads to more instability and therefore more mass flux. It's worth mentioning, though, I'm not nudging to moisture, yet there still seems to be more moisture. So it's probably how the low-level winds interact with the environment, or low-level winds interact with the moisture that is helping stimulate the convective environment more. So I hope that answered the question.
Yeah, and I can help you to look if you're using new or old nudging approach.
Thank you.
Ira, did you have a quick question?
Yeah, it was mostly if you were going to be nudging to Q, but it might apply to T as well. That I think ERA 5 assimilates more things near the surface than MERA, so maybe T is being more constrained, and then the humidity is following that. I'm not sure though. I would be more confident about that if you were nudging humidity. I'm less confident about it with T alone.
Yeah, that definitely makes sense and something I'll look at too. The only T I looked at was mid-level T to see if there was more instability. In other words, if ERA 5 had lower temperature in the mid-levels, that would also then increase the amount of CAPE, and that could lead to more mass flux as well. But I haven't looked at it in the low-level environment as well, so that's a good suggestion. Thank you.
Okay, I think we should move on to the next talk. Thank you, Ren. And so the next talk will also be online. Luisa Campanolo, I think she is here. So yes. Do you want to share your slides?
Yes, let me do that.
And the talk is on investigating the atmosphere response to radiation belt electron precipitation.
Okay, I think you're seeing my screen right now. Hopefully. Yeah, okay. Okay. Hi, everyone. Thank you so much for having me. A quick disclaimer, I am not from the atmosphere community. I come from the magnetosphere community. I just started to learn a bit about WACM and the atmosphere. And in particular, I'm curious about what is the atmospheric response to the radiation belt electron precipitation. So we're looking at charged particles falling into the upper atmosphere. I want to thank my great collaborator, Kathy Duderstadt. I think she's online. And then, just to give you a quick introduction, if you have never heard about the radiation belts, these are two regions right around the Earth. There's an inner belt, which is fairly stable, made of protons, and an outer belt, which is primarily composed of electrons, that is very, very. And this plot here essentially shows you how the outer belt flux varies as a function of time. These are about 20 years of data. The L shell value here is essentially the radial distance from Earth to the radiation belt. And in color, you'll see the flux. And then on top, you can see the solar wind speed and the sunspot number. And so you'll see that there's a lot of variability in terms of flux, but also in terms of where this radiation belt is getting closer to Earth. And so overall, what we know from kind of the radiation belt observations and modeling is that the radiation belt structure typically is the result of several mechanisms, in particular the acceleration, transport, and loss of these particles, charged particles. And this heavily depends on plasma waves that occur in the magnetosphere. And these plasma waves can interact with in this case, with the charged electrons, and then they can cause essentially a precipitation of these electrons into the upper atmosphere, where they dump their energy interacting with the neutrals. And so the radiation belts, like to put them in kind of a broader context, they are part of the near-Earth radiation environment, and they contribute to space weather. And in particular, the radiation belt particles that precipitate into the upper atmosphere, they can affect ionospheric conductivity. And then it's an actual energy input into the system, and it can also alter atmospheric chemistry, possibly enhancing ozone loss. There's no real consensus on the true energy input from radiation belts, especially the higher energy tail. And in particular, there have been a few studies that looked at NOx enhancement due to the solar energetic particles precipitating, the galactic cosmic rays, as well as the auroral electrons. But it seems that this enhancement is underestimated. And so there's a potential a candidate to kind of make up for that loss, for that missing enhancement could be the radiation belt electrons. And this topic actually has gotten a lot of interest in the last few years. And there was also a Chapman conference about actually exactly a year ago, looking specifically at kind of the coupling between radiation belt particles and the atmosphere response. So just to give you a kind of a broad introduction on how so far we've looked at radiation belt precipitation in terms of ionization rates. So this is just an example here where there's 8 different research groups that they've looked at the same data source. So we're looking at POSE satellites. These are LEO satellites that measure electrons. And these 8 different groups have also focused on a specific event this month in 2010. And they calculated the ionization rates due to the precipitation. And as you can see, the results are fairly different across each group, even if we're using the same exact data source and the same event. And additionally, the POSE data is kind of like the one that is looked at the most to essentially measure the precipitation input into the upper atmosphere. But the real precipitation intensity is not really accounted for. They just use the data that POSE observes. In particular, the CMIP6 recommendations use this model, the APEEP. And the most recent data set was developed by Josh Pettit, and it's called MP15. And it's got they have slightly different assumptions, but they still get to only 1 MeV of energies in terms of electron precipitation. And so there's actually a newer model that estimates these ionization rates in a little in an improved way. So this model was developed by Wei Zhu and Bob Marshall in 2020 at CU Boulder. And this model actually goes past the typical model that we've used so far, which is the Fang 2010 model, and it extends past the 1 MeV threshold. And additionally, it also requires a specific pitch angle distribution for these electrons that are precipitating. So in the past, I've collected a bunch of precipitation events from another LEO satellite, the Elfin CubeSats in particular, and I was focusing only on relativistic energies. And so this is just data that, an example of data that Elfin is observing. This is the precipitating flux. The energy is right here. And so you'll see that there's kind of an enhanced precipitation as the satellite is crossing through the region of precipitation. So what we did, we used this observed flux to calculate the ionization rate using this kind of updated method. And so these are the ionization rates that we got. This is the altitude and this is the ionization rate. And then we can compare these with the CMIP6 recommendations. So these are the medium energy electrons. I think they get to about 1 MeV. And then we have the SCP particles, which in this case were not really happening, and then the GCRs, which penetrate much deeper. So essentially what we see is that this relativistic energy precipitation ionizes the mesosphere, which is right now, at least from CMIP6, underestimated. And then other studies have, this is actually a study by Kathy, they identified a 10-day electron loss event. And so all of these electrons were falling into the upper atmosphere. And these are the ionization rates. So you have the galactic cosmic rays, the radiation belt particles, and in this case, there were also some solar proton events. And this is the view from the North Pole. And they were using, in this case, just the ionization rates up to 1 MeV. And so these are the results in terms of WACM and in terms of the ozone reduction. The top panel shows you the results of the ozone change using the CMIP6 input. So without really looking at the high energy tail of precipitation. And the bottom one instead looks at a slightly more realistic case where you are looking at higher energy precipitation. And so you'll see that you can even get up to 40% of change in ozone. But you need to look at the 100th percentile of the flux of these electrons falling. And then more recently, there was a paper by UD Pan in 2025. They are running WACM for the whole year of 2003. And they are running two different simulations, one looking at electrons up to 1 MeV and one looking at electrons up to 9 MeV. So this is the change in NOx. And then they also look at the change in ozone. And so for the kind of the lower energy-ish electrons, we get about 40% of ozone loss, which gets an additional almost 20% if we instead include multi-MeV electrons. And then this is actually a paper that shows evidence of this ozone depletion. So essentially this paper here, they identified a couple of events where you see precipitation of electrons, and then at the same time, also depletion of ozone. And this was observed by timed. And these are just like kind of different, similar, essentially the same data, but plotted as a function of altitude and the timed trajectory. And so what you see is that essentially, as you're crossing the region of precipitation, there's some ozone loss. And this is also shown in these profiles here, where you'll see that this black line is indicating the monthly mean of ozone. And then during that event, during the crosses of the satellite, you'll see that the ozone is instead depleted. So obviously, we don't exactly know how much these percentage changes in ozone are going to change the atmospheric response. And so kind of the idea that I have, and Kathy and I have tried to develop recently, is trying to understand specifically what is the energy input from the relativistic electron precipitation, but in kind of more a realistic way, and also look at the resulting effects. So we're going to look at realistic precipitation regions rather than what has been assumed so far, which is kind of like a constant drizzle of relativistic electrons. And this is not necessarily accurate. And in fact, it might actually overestimate the energy input, at least at these energies. And then, so we're going to focus only at energies above 700 keV to specifically isolate the response of those electrons. And the reason why we care about those is that those electrons actually precipitate deeper into the upper atmosphere, as I showed before, into the mesosphere. And then hopefully we'll also look at the local time dependence of this precipitation, because the precipitation doesn't happen at all longitudes, but it's actually focused typically on the night side, dusk to night, and then also understand what are the impact, what's the actual resulting effect of the ozone loss. Does it affect radiative heating and the thermal structure, zonal winds, and so on? So in terms of the data methodology, I use the POSE satellites, as I mentioned before. So these satellites are at LEO, about 800 kilometers of altitude, and they can cross through regions of precipitation and observe electrons. And so what I have is a database essentially of all of these relativistic electron precipitation events, and I can sort them into regions of precipitation or patches, and I'll show an example later. Then what we do, we use Berry to calculate the ionization rates, and then we use those as a driver to WACM, and kind of a bit more details are shown here. And then what we do is we attempt to look at the local and global response of the atmosphere with or without this relativistic electron precipitation, and ultimately understand what is the specific characteristic of this precipitation that could cause impactful changes. So this one here is an example from POSE data. This is the flux as a function of time. So this is essentially the trajectory of the satellite as it's crossing through a region of precipitation. And this is I'm marking that region in gray. The solid line is indicating all of those electrons that are falling, and the dashed line is instead the electrons that are bouncing back and forth between the hemispheres. In terms of like the occurrence rate as a function of years, the relativistic electron precipitation typically occurs on the declining phase of the solar cycle. And then instead, in terms of local time, it happens primarily from, say, pre-dusk up to post midnight. And in reality, though, a POSE satellite is going to cross through the region of precipitation just once, but that precipitation region is probably more extended than just what POSE is observing in one pass. So what we can do is we can collect a bunch of these isolated single passes of POSE and get a patch of precipitation. And so this is shown here. So all of these crosses here are a pass of a POSE satellite, fairly close in time. So we're looking at about 100 minutes. And so we call this a patch of precipitation, which will be mapped on specific latitude and longitudes in the geographical coordinates. And so this is the one of these passes of POSE that is shown here as an example. So this is, again, the region of precipitation. And so the assumption that we make is that this is kind of like the representative flux of all of these passes. We can assume that the flux in that patch is pretty much the same as the flux measured by that POSE. We can get the differential flux, and I will skip through this because I don't believe it's key information, but essentially from the data, we can calculate the pitch angle distribution of the flux and use Berry to get the ionization rates. And this is the ionization rate that we get that peaks at about 64 kilometers of altitude. And then again, if we compare it with the CMIP6 observations, you'll see that it kind of dominates in this region here where the MEE, so the medium energy electrons, are not really depositing energy, and the GCRs are depositing energy much more deeper. And there were no SCP events in this case. And so we actually picked a specific month, which is the July month in 2013. This is the kind of overall geomagnetic activity. So the red line indicates the substorm index, and anytime you have substorms, you typically have precipitation, and the bottom panel instead shows the geomagnetic activity. And these circled ones are the storms. And we counted about 12 patches of precipitation, which are marked here in green. So in terms of what are the inputs that we use for WACM, so just as an example, this would have been the CMIP6 that we would use for this specific month. It peaks at about 90 kilometers. This is due to the medium energy electrons. And then instead, the actual Berry input that we use is shown here, where you'll see that it peaks much deeper at about 60 kilometers. And also the other difference is that we assume the realistic duration of these patches. So you'll see that this is much more bursty versus the CMIP. And so this precipitation is essentially not really sustained in time, and it's constrained by the data that we have. In terms of the latitude, we have similar bands where this precipitation is occurring. And so we're looking at about 60 and above latitudes. And ultimately, we also want to look at the realistic latitudinal extent, because actually these patches are not going to be fixed in latitude. They're actually changed depending on the specific precipitation event. So from the north and south pole, this is where we assume the precipitation is deposited. And then we use the GCR ionization rates, which are shown here, and also the solar proton events. And this was actually a quiet month. There were no SEP events in this specific, in July. And so very quick preliminaries. These are very preliminary. So these are essentially plots that show enhancements of NOx, HOX, and ozone loss as percentage, where essentially we are comparing the NOx and HOX and all of these other components with respect to what we would get if we don't have precipitation of relativistic electrons. And so in this case here, this is the NOx case, and you'll see that in the polar, the South Pole, which is the winter hemisphere, that's when you see that the HOX remains elevated. And this is instead the NOx enhancement, where you'll see a circle showing up, and that is exactly the deposition of these electrons. And it seems to persist in the southern hemisphere. And sometimes you do see also these kind of like circles that form because of that precipitation. And then this is instead the ozone reduction, which you'll see happening kind of like on more local scale, probably more evident in the southern hemisphere. But again, these are very preliminary results. So I just want to leave with kind of summary. It's possible that the radiation belt precipitation has been underestimated, especially at relativistic energies, or at least not taken into account in a realistic way. And this precipitation deposits energy in the mesosphere, primarily peaking at 60 kilometers. And we actually have some data that can help us identify realistic precipitation patches. And so we can use that as input to WACM and try to compare what would be the atmospheric response with or without this precipitation. So we're currently running these simulations, and I'm leaving here kind of like the open questions that we have. And I'm very curious in particular to understand if there's a specific characteristic of this precipitation that is going to show kind of the most effects. And again, I'm very happy if you have any feedback or if you want to collaborate, because I come from the radiation belt community. Happy to take any questions though. Thank you.
Are there any questions? Yeah, Hanli.
Hi, Luisa. I have a question on the calculation of the ion pair rates. Is that calculated in line in the model, or is it pre-calculated and then read in when you run WACM?
Yeah. So what we do for that, I have like Bob Marshall and Wei Zhu have like a MATLAB code that essentially takes in the flux as input, and then it spits out the profile of ionization. And then what I do, I basically create an input file to WACM. Sorry, I'm just trying to, I think I went too far. I create this, where is it? An input file to WACM. And it's very similar to the CMIP6 input file. But instead of using the MEE electron energy, I use this customized, the Berry ionization rate. So,
okay.
Yeah.
That's what I thought. So when you do that, you need a background atmosphere. For that, you first run WACM to get that?
Yes, I see what you mean. No, because Berry, yes, Berry requires an atmosphere, the atmosphere density. No, for that I actually use MSIS.
Okay.
Yeah, just for simplicity, because otherwise, yes, probably the most accurate way would be to run WACM, get the atmospheric density, and get Berry. Yeah.
Okay, great. Thanks.
Yeah, thank you.
Okay. Thank you again. In the interest of time, I think we should move on to the next talk, which is also remote by Brandon Duran. I hope he is online.
Yeah, let me share my screen.
Here you go. And it's on aerosol ice cloud interactions in the perturbed parameter ensemble.
Okay, hopefully you can see my slides now.
Yes, we can.
Okay, great. Yeah, thanks for having me. And yeah, so I'm excited to talk today a little bit about aerosol ice cloud interactions in a CAMP6 PPE. And this is work that I've done in collaboration with Casey Wall at Stockholm University and then my advisor, Nick Lutzko at Scripps. And so just to jump into some brief motivation for our work, aerosol cloud interactions drive the largest uncertainty in historical radiative forcing. This is a nice figure that illustrates that. So kind of at the top, we're seeing that we have a pretty good constraint on the warming effects of carbon dioxide over the historical period. And that's kind of in contrast to, towards the bottom of this plot, this light blue box showing the effects of aerosol cloud interactions, and more notably, this uncertainty range, which goes to show that we don't have a good grasp on the magnitude of cooling from ACI over the historical period. And so really this uncertainty is something that the ACI community is striving to reduce. And one of the reasons that we care a lot about this is that uncertainty hinders our projections of future warming. And so I just pulled this figure, which shows for 3 different values of aerosol forcing, historical aerosol forcing, what are the effects on the evolution of simulated global mean surface temperature change up through 2100. And really, as a result of this uncertainty, we can see towards the right of the figure, by 2100, you can get kind of large differences in simulated temperature change as a result of our inability to constrain the magnitude of aerosol cooling over the historical period. So really, we got to be able to better constrain these estimates to reduce some of the uncertainty associated with future climate projections. And to this day, really, most of this research has been focused on aerosol cloud interactions and warm phase clouds or liquid clouds. And ice clouds have really been kind of sidelined in this story. And I pull this quote from this 2020 review paper on aerosol forcing, where they go through and kind of try to systematically bound some of the different components of aerosol forcing. And when it comes to aerosol ice cloud interactions, they essentially don't even provide a bound in this review. And they argue that there's simply not enough evidence and research that has been done to date to try to constrain this. And so I'm going to be walking into this field of ACI research that to this day has kind of relatively been understudied. And so to frame the rest of the talk, I want to provide 3 framing questions that I hope to address. And so the 3 of them are, do aerosol ice cloud interactions contribute substantial cooling to shortwave ERF ACI and a GCM? What sets the dominant ice cloud response to aerosol in CAMP6? And then can we use observations to constrain the magnitude of shortwave ERF ACI from ice clouds? So I'll jump into this first question. And the way we're going to go about this is with PPE in Camp 6. And so just briefly, what we're doing is we're perturbing 19 different aerosol and macrophysical parameters in Camp 6 to explore the parametric uncertainty associated with them. And this is just showing a table of the parameters that we perturb. And in terms of the simulations that we actually run, we have 161 perturbed members. So these are simulations where these 19 parameter values have been perturbed. And then we have one base case, which represents the default Camp 6 parameter values. And so for each of these parameter combinations, we have a pair of Camp 6 runs, 2-year fixed SST, nudge to MERA2 reanalysis. And the only thing that differs between this pair of runs is the aerosol emissions and precursor gases. So one of them represents a pre-industrial atmosphere and the other a present day. And that's how we're able to diagnose the radiative forcing from ACI. And then when it comes to actually taking that total aerosol forcing and understanding the contribution from ice clouds, we're relying on this MODIS cloud radiative kernel method that I'll briefly talk about here, and I'm happy to answer more questions about. But there's kind of 2 key components to this decomposition that I'll walk through. So on the left, I'm showing you a cloud fraction, an ice cloud fraction histogram partitioned by effective radius and ice water path. So this is basically telling you from the ice cloud fraction in the model, it's partitioning it into different cloud properties. And this is coming from, this is output from the MODIS satellite simulator that is implemented in the cost package. And so we're producing these cloud fraction histograms from each of the simulations that we run in the PPE. So this left-hand side, this component is coming from the model. And then on the right-hand side, the radiative kernel, that's coming offline. So we're generating this kernel offline in the radiative transfer model. And what this kernel essentially represents is the sensitivity of the top of atmosphere radiative flux to changes in ice cloud fraction. And the way to roughly interpret this kernel is just that the thick ice clouds are going to have a larger radiative effect than the thin ice clouds. So that's being shown by the stronger cooling perturbation that you get in the upper left of this kernel. And those are coming from thick clouds that have small ice crystals and large ice water path. So these are kind of the crux of how we're going to attempt to understand the aerosol forcing from aerosol ice cloud interactions in the model. And so jumping straight to the results, so I'm going to be showing this panel of the PPE ensemble mean response. And just to walk through the different panels that I'm showing, in the top left, this is the total shortwave forcing from aerosol ice cloud interactions. And then panels B through D are showing the decomposition of that total forcing into the ice to me effect or changes in effective radius, the ice cloud fraction adjustment or changes in cloud amount or cloud fraction, and then the ice water path adjustment. So changes in ice water path while holding cloud fraction and effective radius constant. And really what I want to note here is that the predominant response is this dipole pattern where we see generally cooling from ice cloud changes over Asia and extending into the North Pacific. And then perhaps surprisingly, we see this warming that's occurring over the tropical Pacific that's coming from both effective radius changes and cloud fraction changes. And so it's really this dipole response in the ensemble mean that we want to understand whether this is systematic across all of our simulations or whether there's different cloud responses that we're hiding when we look at just the ensemble mean. And so to that end, we actually find that there's generally 2 distinct cloud responses that can occur in the PPE. And so what I'm showing here on the left are just composite plots of the total shortwave aerosol ice cloud forcing stratified by kind of the tails of the PPE distribution. So what I'm calling here as the cool and warm group are really the 2 groups that either give you the the strongest negative forcing from aerosol ice cloud interactions or the strongest warming. And so it's this cool group response that really drives the majority of the PPE. So about 80% of the simulations tend to show this characteristic pattern of warming over the tropical Pacific and cooling elsewhere. And then this warm group pattern, which is kind of an inverse, is only shown by about 20% of the ensemble members. And so to kind of try to understand what's driving these almost two completely different ice cloud responses to aerosol, we look at the two parameters that differ the most between these two groups. And so what I'm just plotting here are on the X and Y axes are parameters controlling the cloud to rain auto conversion rate. And then the Y axis is a parameter that controls the strength of ice updrafts that get passed into the ice activation scheme. And generally what you can see is that there's this clustering whereby these cool group members, which have really strong negative forcing from ice cloud response to aerosols, tend to have both a weak auto conversion parameter and also really strong ice updraft parameter, and vice versa for the warm group. And so we take this kind of clustering that is occurring across the PPE as kind of the framework for how to address the ice cloud response. And so I'm going to focus on the cool group, given that it's kind of the predominant response in CAM6, and focus on, again, these two parameters. So micro key aero W sub I scale, which is controlling updrafts for ice nucleation, and then micro MG autocon conversion LWP exponents. This is a parameter that controls the auto conversion rate. And so, yeah, jumping into this next question of what sets the dominant ice cloud response to aerosols in CAM6. So we're going to argue that there's this subtropics to tropics pathway that's going on, and I'm going to try to link both of those parameters that I just mentioned into what we're seeing in the model. And so starting off with that auto conversion parameter, we really expect that to be important in the subtropical low cloud regions where you're getting a lot of aerosols that are interacting with low clouds, and the weaker your auto conversion is, the more cloud water you're going to retain in response to these aerosol perturbations. And so that's what's being shown on the left is fractional changes in boundary layer moisture from pre-industrial to present day. And you can see in the cool group, this buildup of boundary layer moisture is really amplified in the subtropical low cloud regions. And so this is why we think this auto conversion parameter seems to matter in the cool group. But if you remember back to the first plot that I showed you, these aren't regions where ice cloud forcing is actually strong. And so we need a way to connect this boundary layer moisture enhancement in the subtropics to changes that we're seeing over the tropical Pacific. So as a result of this moistening of the subtropical boundary layer, we get this enhanced moisture transport to the tropical West Pacific. So that's being shown in the top right panel here with the change in boundary layer theta E. And you can really see that there's this large increase in theta E in the boundary layer in the warm pool region of the tropical West Pacific. So we're getting this change in the subtropics that's being modulated by aerosol, and it's being kind of communicated down to the tropics. And this theta E buildup, or this enhancement of moisture in the tropical Pacific, is really important for changing the tropical temperature profile. And so the temperature profile is typically controlled by the moisture content in the boundary layer. And so when we have an increase in moisture content, we actually see a shift of the tropical temperature profile to a warmer, stabler, moist adiabat. And then that temperature change in the upper troposphere gets communicated throughout the tropics and kind of globally. And that's being shown by this large increase in static stability in the cool members that's being radiated remotely from the tropics. And so as a result of this stabilization, we actually see that large-scale ascent weakens in the cool group. And so that's being shown here by plots of omega 500. And notably, you can see that this kind of large-scale ascent is decreasing or weakening across the entire tropical Pacific basin. And this goes on to suppress convection. And then this is also where we can link this other parameter that I mentioned, which is controlling the scaling of updrafts into ice nucleation. And so when we see this weakening of large-scale ascent, that alone would lead to a reduction in ice nucleation over the tropical Pacific. But this result is actually amplified in members that have the strongest value of this scaling parameter. And so what I'm showing here are just changes in the activated ice number concentration in the upper troposphere from homogeneous nucleation. And drawing your attention to the left panel of the cool group, kind of everywhere outside of the tropics, we see large increases in nucleation, which is not unexpected given that we're seeing kind of huge perturbations in the amount of sulfate from anthropogenic emissions. But really in the tropical Pacific, as a result of this weakening of large-scale ascent coming from the subtropical low cloud response to aerosol, we then get this associated reduction in nucleation in the upper troposphere. And then from there, it really becomes a microphysical pathway whereby as a result of this reduction in nucleation, we see a decrease in cloud top ice number, an associated increase in the effective radius of ice crystals. These larger ice crystals have faster sedimentation speeds, so they're going to fall out of the cloud faster, leading to a loss of cloud ice and a decrease in cloud lifetime. And so these panels are just walking through that microphysical pathway whereby a reduction in nucleation from a slower large-scale ascent is leading ultimately to this quite strong reduction in ice cloud fraction over the tropical Pacific. And so that's kind of the pathway whereby these two parameters that I mentioned earlier seem to drive the dominant cloud response in Camp 6, at least. And so jumping briefly to whether we can use observations to constrain the magnitude of this aerosol ice cloud interaction forcing in the model, we're going to pull in observations of long wave cloud radiative fluxes from Ceres and also ice cloud fraction retrievals from MODIS to try to understand whether there's a sensitivity of the ice cloud response to aerosol to the mean climate state. So in a PPE, you generate an extremely wide diversity of mean states. And so we really want to assess, do our estimates of aerosol ice cloud interactions change when we kind of just exclusively focus on ensemble members that best reproduce mean state climate. And so we use these observations to constrain our estimates, and that's what I'm showing here. Really what's important is the difference between the red and the black curve. So the red curve is the Gaussian prior PDF of the total shortwave ERF-ACI from ice clouds, and the black curve is the distance weighted. We have this metric by which we weight ensemble members that best represent observations. And what we're able to achieve is about a 35% reduction in the spread in total shortwave ERF-ACI. Notably, the central estimate of this cooling, which is around 0.4 watts per meter squared, doesn't change much from the ensemble mean as a result of this constraint. And then what I don't show here is that actually walking through this constraint for the net ERF-ACI from ice clouds, so both the shortwave and the long wave, actually leads to a much tighter constraint of about 0.37 to 0.12 watts per meter squared of cooling in the net across the PPE. So with that, I'll kind of put up my three framing questions just to emphasize that we see about 0.43 watts per meter squared of cooling in the global mean as a result of aerosol ice cloud interactions in the shortwave. We believe that the dominant response in Camp 6 is driven by this subtropical to tropics pathway whereby low clouds in the subtropics are responding to aerosols, and that's leading to this enhanced moisture transport into the boundary layer of the tropics, which then has these knock-on effects that I've shown here. And then lastly, we're able to reduce the spread in the total ERF-ACI from ice clouds by about 35% when we focus mostly on ensemble members that best reproduce present-day observations of ice cloud state. With that, there's more details in the preprint that we have out, and I'd be happy to take any questions if time allows.
We can take at least one question. Just one quick question on the last part of the observations. Can you also use that to kind of train a single estimate of what would be the best set of parameters to use?
Yeah, that's a great question. And so I didn't show it here, but what we end up finding is that when we do this sort of constraint, you can look at how that changes the posterior distributions of the parameters that we perturbed in the PPE. And what we find is actually there's kind of this W sub I scale parameter that I focused on here. You can actually end up constraining the range of kind of effective values for that by about 75%. So it tends to favor weaker values in that respect. And so, yeah, there's definitely a way here where you can connect the observations to future PPEs where you maybe reduce the size of the parameter values that you perturb for some of these the parameters that I mentioned. Yeah.
Okay. Thank you.
Thanks.
So if there's no other questions, I guess we can move on to the next talk, which I think is in person. Jolly Louis, and it's on the, I think, fast track value. So performance using like comprehensive suite of GFDL models. That's preliminary system.
Thank you for having me today. My name is Jalalo. First of all, I'd like to thank my collaborator, Andrew Wittenberger. This project came together during a transition period for me. I'm very grateful for having this opportunity to work on this project and to share the results with you today. So over the past year, I've been working on using an ENSO diagnostic package to evaluate ENSO performance using a comprehensive suite of GFDL models. Hopefully throughout today's presentation, I can provide some useful information, not only for diagnosing the GFDL models, but also for NCARS models as well. As we all know, despite substantial improvements in general circulation models, long-standing biases still exist, largely exist across different climate models as over tropical Pacific, as illustrated in this plot here. We often see cold town bias, warm SST bias over eastern tropical Pacific near South America, excessive trade winds, and double ITCZ. This means that biases often can have huge impacts on ENSO simulations, leading to weaker ENSO ERC coupling and damping, less ENSO diversity and asymmetry, and shifted ENSO teleconnection patterns across the globe. And also, it can in turn have degrade our ability of data assimilation to initialize climate models and induce climate drift and initialization shock in numerical forecasting systems. Here I'm using an example from my previous work, which essentially to illustrate how ENSO forecast skill is closely related to the overall model performance. On the left, we are looking at a Tyler diagram for Nino 3.4 prediction. Each curve here represents a forecast skill trajectory made by one CMIP6 model with forecast leads from 1 month up to 24 months in advance. As we can see, although forecast skill will eventually drop off over time, some models definitely perform better than others. It turns out to matter a lot because the choice of which models we include in the data library to train our data-driven ENSO forecasting models makes a huge difference. On the right here, when we include the 9 best performing CMIP6 models as indicated in the red curve here, the forecast scale definitely outperforms that obtained from 5,000 random model combinations. So we left to wonder if there is any quick way for us to tell whether a model is good or bad. A few years ago, Ian Planton and colleagues put together a very nice diagnostic package. It turns out to be perfect for addressing this type of question. On the right, we are looking at the heat map, which essentially shows a standardized metric score for almost 100 CMIP models from both CMIP5 and CMIP6 archives. So here, each cell represents a metric score that is standardized relative to multi-model mean. Red color here means worse than the multi-model mean, and blue color here means better performance. Just to clarify what I mean by metric here, metric can be either root mean square error or absolute percentage error computed between model simulations and observations. Root mean square error is used for things like mean state biases, seasonal cycle, ENSO SST pattern, and ENSO life cycle. And AP is applied for ENSO characteristics like ENSO skewness, amplitude, seasonality, asymmetry, duration, diversity, and ENSO feedback processes. The reason we use AP here is largely because the metric score itself is a scalar value, such as a regression coefficient. With this background information, let's take a look at the heat map on the right. Once again, the bottom few rows shows the observational references as they are in general blue, indicating the ideal best scores we can get. However, there's some exceptions. For example, precipitation for having larger observational uncertainty. If we move slightly up, there are 2 rules with very pale colors. They correspond to CMIP5 and CMIP6 mean. This actually within expectation because this is how they defined the multi-model mean. Since we are here at NCAR, so you might be wondering how NCAR's model performed relative to the rest of CMIP model. As highlighted in the red box there, we can see in general, NCAR's model outperformed most CMIP model as the metric scores are generally on the blue side. As one of the major modeling centers, GFDO has also recently developed a family of general circulation models, each with its own focus. For example, SHIELD listed on the left focuses on weather scale processes with finest atmosphere resolution. In contrast, model like SPEAR, ESM, and CM focuses on seasonal to centennial timescales, each proposed with its unique strength and focus. In particular here, SPEAR is designed for initialized seasonal to decadal predictions. It uses large ensembles and has multiple resolutions. So, which makes it very useful for prediction and predictability studies. The schematic on the left again shows the GFDO models that we're interested in. They are organized by horizontal resolutions. If we look from left to right, we are increasing the atmosphere resolution from 100 kilometer down to 25 kilometer. If we look from bottom to top, we are increasing ocean resolution from 100 kilometer down to 8 kilometer. So for example, SPEAR High 8 on the top right has an atmosphere resolution of 25 kilometer and ocean resolution of 8 kilometer. In contrast, SPEAR Low on the bottom left has a resolution that is comparable to the standard CMIP model. The numbers in the brackets represent how many ensemble members we have for each simulation. In this case, SPEAR Low and Medium have 30 ensemble members for historical simulations. Large ensemble actually allows us to investigate the ensemble spread and look into how robust the ENSO performance actually is. Note that ESM 4.5 marked here is still under active development. So the diagnostic results are subject to ongoing model refinement. For simplicity, I won't talk about it throughout today's presentation. This slide shows the observational references we used to compare the model outputs with. So the variables listed here. For some variables that might have larger observational uncertainty, we use multiple data sets to cross-validate. For example, precipitation, we use ERA5 and different versions of GPCP. The period we studied here is overlapping period between historical simulations and observations. So for SST, it's from 1940 to 2014, and for precipitation, it's from 1980 to 2014. Just another housekeeping note here. When I say equatorial Pacific or along the longitude, I'm referring to the meridionally averaged quantities over the blue box here. And when I say Eastern Tropical Pacific or along the latitude, I'm referring to the zonally averaged quantities over the red box up there. So with model outputs and observations being ready here, we'd like to address these three questions in this study. Does increasing model resolution systematically improve ENSO simulation? How robust are ENSO simulations across large ensembles? And how can diagnosed model biases inform observing network design in the topic Pacific? With these questions in mind, here we are evaluating the full suite of GFDL models. Again, we are looking at the portrait plot for the top 10 CMIP model. These top 10 CMIP models are selected by ranking the row-wise average of the metric scores, as I showed a few minutes ago. So here, it's not surprising to see that relative to the top 10, CMIP are generally not on the top 10 list, as indicated by these two red rows here. So here, one thing that really stands out is that 4 out of the top 10 models come from NCAR. They are CSM2, CSM2 WACM from CMIP6 archive, CCSM4, CSM1 BGC from CMIP5 archive. So with the newly defined threshold reference, here we are now looking at the portrait plot for the full suite of GFDL models organized by increasing horizontal resolutions from sphere low down to sphere height 8. So we can, by just eyeballing these color changes, we can see GFDL models are good at certain metrics, but continue to struggle with certain metrics as indicated in the red color column here. So here, when I say bad, it doesn't necessarily mean bad. It only means relative to the top 10, it's not among the very best. So in comparison, we're also looking into simulations with stronger constraints like nudged and flex-adjusted simulations. So where surface temperature, surface salinity, and wind stress are either nudged to the observations or adjusted to observed climatology. A detailed discussion can be found in Shane Wu's submitted manuscript. So here I include them to provide more context alongside the free runs. So now let's start with increasing atom field resolution. We're looking at sphere low, medium, and high. Here, according to different behaviors here, we are categorizing the metric scores into 4 groups. Consistent good or bad, getting better or getting worse with finer atom field resolution. So we can see sphere models are good at, for example here, climatological precipitation in the Eastern Tropical Pacific. Seasonal cycle of SST and tau X along the equator. And so life cycle and ENSO seasonality. However, sphere models continue to struggle with climatological precipitation along the equator, ENSO skewness. They are bad in sphere low and getting worse in sphere high. And the ENSO feedback processes as indicated in the red patch here. There is only one metric that is getting better in sphere high. That is thermal damping feedback. However, I will illustrate later. The single improvement doesn't actually help the sphere high get better. It actually introduces other issues. So For some metrics that used to be good in sphere low and medium and getting worse in sphere high. They include climatological tau X along the equator, seasonal cycle of precipitation in the eastern tropical Pacific and along the equator, and ENSO pattern, ENSO duration, and ENSO diversity. So just by eyeballing it, we can see finer atmosphere resolution doesn't necessarily guarantee better ENSO performance. But why? Why that's the case? So here, one nice thing about this diagnostic package is that we can actually do some thorough diagnostic to pinpoint where the bias actually comes from. So here I'm showing the climatological precipitation along the latitude and longitude and climatological tau X along the longitude. So even for those metrics that perform relatively well, like the top panel shown here, we can clearly see some extraordinary bias. So we can see the excessive rainfall over the equatorial South Pacific, contributing to double ITCZ bias. And the rainfall bias persists even when SSD is nudged toward observations, pointing to some like intrinsic structural bias. And then those mean state bias are often connected. For example, here, we can see the overly strong trade winds over the Western Pacific moves the convective zone further west and contribute to the overly sharp rainfall gradient, leading to the too dry atmosphere in the equatorial, in the central equatorial Pacific. In comparison here, CSM2 is one of the best performing models for tropical mean state changes. At the bottom here, I'm showing the seasonal cycle for precipitation along the latitude and longitude. We can clearly see the precipitation is too strong and contributing to the double ITCZ problem in the sphere models. We can imagine that when seabelt comes, it rains a lot in the models, and when rain belt moves away, it stops raining abruptly, contributing to the unrealistic strong precipitation. So for CSM2, despite having good precipitation along the latitude, it overestimates the precipitation along the equator. So here, move on to basic ENSO characteristics. We are looking at, I'm using the ENSO pattern, ENSO amplitude, ENSO skewness, and duration as an example. We can easily spot some long-standing ENSO biases. For example, the ENSO westward extension as the negative and positive SSD anomalies extend further west compared to the observations in pink. And also, if we stare at the orange line here, which represents the sphere high, it has too weak variability. So here for ENSO skewness, so observation has negative skewness over the Western Pacific and positive skewness over the Central and Eastern Pacific. In the models, they are generally too Gaussian distributed. Despite having larger ensemble spread, none of the ensemble members can actually simulate the observed skewness, pointing to the intrinsic model bias. And for ENSO duration here, although ENSO duration is shorter in sphere high, if we look at the orange box there, it might likely due to sampling error as model spread largely overlaps with observed range. So here, for the time concern, I'm just scratching the surface. If we stare at the diagnostic plots here, we can have more interesting findings. For example, La Nina is lasting longer than El Nino in the observations. However, this is not the case in the model simulations. In comparison, despite having one of the best mean state changes, CSM2 continues to struggle with ENSO characteristics. For example, we have ENSO westward extension, too strong ENSO variability, like Ayla pointed out yesterday, too schematic over Central Eastern Pacific. So I guess this shared bias is pointing to some collaborations and communications between different model developing groups. So last, I want to show the ENSO feedback processes. The schematic here it shows two major ENSO feedback processes that shape the evolution of ENSO. So as indicated in the red arrows here, they represent Bacon's feedback, which is a positive feedback. And as indicated in the wiggling arrows here, it represents heat flux feedback, which is a negative feedback. For example, during La Nina phase, the ocean tends to gain more heat from atmosphere, and which drags the negative SST back to normal. So this is how the negative feedback works there. The diagnostic plots on the right shows linear fits between two different variables, with upward slope denoting the positive feedback and downward slope denoting the negative feedback. So in general, we can see it often has a 2-week feedback in the models, as the slope of the simulated quantities is lower than the observed ones. And for the SSH to SST feedback, here we can see given a -2 degrees Celsius changes in surface temperature, the upwelling is stronger over the observation, pointing to the weak upwelling in the simulations. And also we have 2-week thermal damping feedback here. It points out to a very interesting error compensation here. That is, an overly weak positive feedback offsets an overly weak negative feedback, yielding seemingly realistic ENSO variability, which is the case we talked about for sphere low and sphere medium. However, there is an outlier there, which is sphere high. Despite having slightly improvement over the thermal damping feedback, however, there is no matching improvement in the positive feedback, which damps the ENSO variability too much, causing the ENSO being too weak in the sphere high. So why increasing the atom field resolution doesn't improve ENSO simulations? Generally, as a rule of thumb, we know that resolution matters, but parameterization schemes matter more. Especially for sphere high there, we tuned up the subgrid diffusion parameterizations, which stabilize large-scale precipitation and avoid some singular values at smaller scale. However, we also we increased the droplet radius and fallout speed. It delays the precipitation onset and intensifies precipitation events. The upside of this tuning is that extreme precipitation got significantly improved associated with tropical cyclone, as indicated in Hero and Borting's previous work. However, the downside is apparent. That is, seasonal cycle of precipitation is too variable, and ENSO variability is too weak in sphere high. It is mainly through this pathway there I mentioned before. So to sum up, I found the ENSO diagnostic package is very easy to run, given that I'm not a Python user, and the ENSO diagnostic package enables rapid fit-for-purpose selection and comparison of models. So if you are interested in ENSO amplitude, for example, you can definitely quickly locate which model are the best candidates to use. And Sphere performs strongly for ENSO SST metrics, but has rainfall bias across resolutions, even when SST is nudged toward observations. This suggests a need for further advances in atmospheric convection and cloud parameterization, especially at high resolution. Those biases are often connected, like mean state biases are often related to ENSO characteristics, biases in ENSO characteristics. And error compensation among weak ENSO feedbacks can produce realistic ENSO amplitudes, but for the wrong reasons. And these results highlight a need for targeted observations and process studies of the air-sea transition zone in the equatorial Pacific. What's coming up is that I'm gonna extend the ENSO diagnosis package to E3SM, focusing on cloud radiation feedbacks when I join University of Wyoming next month, and explore how the diagnosed ENSO biases affect ENSO forecast skill. I'm sorry I'm running out of time, but thank you so much for listening.
Any questions?
Hi, I'm Judith, and I want to make a comment and phrase it very carefully. Great work, you have done a lot of work. It's great to have these diagnostic packages. I guess a criticism I have, not to you, but really everyone who looks into ENSO, is it's so easy to go diagnostic and find out what's wrong. And so little work is done to really understand the processes and why something is not good or better. And there is just another way to look at really from Hasselmann and stochastic processes. And it just to first order, right, it's the atmosphere forcing the ocean. And from that perspective, it makes a lot of sense that high resolution might improve ENSO variability because you have a stronger atmospheric forcing. If you just think of simple linear damped oscillators and stochastic theory, Hasselmann-like. And I agree with you, what probably happens is that the high resolution, the physics is maybe not as tuned or processes are not well represented anymore. I just would be very careful to say that the high resolution doesn't help the problem, because it might be that really if you tune the model correctly, the high resolution one, and it forces the ocean better, you actually get a better ENSO.
Okay,
thank you.
Thank you so much. Yeah.
There's no other questions. I think we can move on to the next talk because of time. So last talk of the morning session is given by Jonathan Beverly, and it's coupled development of systematic tropical ENSO related seasonal forecast errors.
Yeah. Just gonna try and get a on here. Gee. Cool. Yeah. Hello, everyone. Yeah, my talk will actually changed slightly since I put in my abstract. So today I'm going to be talking about how we might be able to use seasonal forecasts as a tool to diagnose what are driving errors in ENSO in models. And this is work I've been doing down the road at PSL with Matt, Andy, and Antonietta. So for many years, as has kind of been alluded to already, client models have suffered from systematic errors in their representation of ENSO events. Two such errors are shown on this figure here. So on the left here, this shows for observations, SST anomalies for El Nino and La Nina events, and then for 3 other climate models on the right here. And if I put a vertical line on here, you can see that relative to observations, all of these models extend their SST anomalies associated with both warm and cold events too far to the west in the tropical Pacific. Another prominent error that climate models tend to have is that they tend to persist with ENSO events too long in the spring following their peak. And that's, you can see on here as well. You can see that, again, relative to observations, the climate models tend to persist with their positive and negative anomalies associated with these events for too long in the spring. And yeah, these have been long-standing errors. And actually, it was interesting to see in Isla's talk yesterday. I just took a screen grab here. And this is still an issue. This westward extension error is still an issue in CESM3 as well. And one of the problems with analyzing coupled models is that it can be quite difficult to determine what is actually driving an error, because the errors can affect each other. And that's where some of the work I've been doing in this talk comes in. And these errors are also present in seasonal forecasts. So this figure on the right here is from one of our papers from a couple of years ago. And the top panel shows multi-model mean for 11 different seasonal forecast models, and it shows the ENSO-related SST error. And what you see is that there are 2 prominent areas of errors in the tropical Pacific. One is in the Western Pacific here, where you see a positive error here. So this means for an El Nino event, you have positive errors. For a La Nina event, you have a negative error. And this is associated with that over westward extension of ENSO SST anomalies. You also see in the Eastern Pacific, there's another positive error there, and that's related to the slow decay of ENSO events in the model. I'm also showing here the equivalent for this for just the ECMWG5 model, which is what I'm going to be focusing on today. And this model is very representative of the seasonal forecast models as a whole, which is one of the reasons why we're focusing on that model. I've also shown the precip errors here as well in the bottom two panels for the multi-model mean and again for CEAS5. And you see that the models shift their ENSO precip anomalies too far to the west relative to observations. In this paper, we also showed that these errors develop very rapidly within a week or two following initialization. And as a result of this, they very quickly lock onto the seasonal cycle and become much more a function of the verification month than of the lead time. So today I'm going to show that seasonal forecast model errors in the wind fields develop almost immediately in response to the initial observed SST field, and that in the coupled system, these erroneous winds tend to drive a westward extension of ENSO SST through affecting errors in latent heat flux and wind stress errors. And I'm going to also show that a coupled error develops in the model, which occurs within 1 month as the model gradually adjusts, kind of goes into its own ENSO phase space. And actually after this time in the coupled model, some of the errors actually reduce as the model adjusts. So to do this, as I said earlier, I'm going to be focusing on the ECMWG5 model. One reason that we're focusing on this model is that it's very representative of seasonal forecast models as a whole, but another is that we have a pair of hindcast experiments that we could analyze. So the one hindcast experiment is just a regular fully coupled hindcast, just a regular seasonal forecast run. And we were also actually given access to data from an uncoupled hindcast experiment. And this experiment uses prescribed observed SSTs, but the atmosphere is free to evolve. And both of these experiments have 25 ensemble members, and I'm going to be focusing on the ensemble mean today. I'm going to be showing initializations, one initialization from the growth, mature, and decay phase of ENSO events. So an initialization from August, November, and February. The hindcast years we use in 1993 to 2016, and reference data sets are ERA5 for all atmospheric, all variables except for ORS5 for sea surface height, and actually I haven't got it on the slide here, but I use GPCP for precipitation as well. For this talk, I'm going to be showing what we call the ENSO-related errors. We're interested in the errors that are related to ENSO. So to do this, I'm going to be computing the error for a given variable, so error being model minus reanalysis or observations. I'm going to be calculating a warm minus cold composite of these based on ENSO events. And I'm going to be focusing on errors in the first 2 months after initialization, so earlier on in the seasonal forecasts. So first of all, I'm going to be showing some monthly mean figures. So what's shown here, so this is for the August initialization verifying in August-September average. What's shown at the top right here is for the fully coupled hindcast, and this shows the warm minus cold composite error for SST. A fully coupled hindcast, you can see that consistent with our earlier results, you see that there's a big significant positive error in the Western Pacific, and this is associated with that over westward extension of ENSO SST anomalies. When you look at turbulent heat flux here, you can see that there's also a significant positive turbulent heat flux error. But the spatial pattern and magnitude of this doesn't appear to be enough to fully explain the SST error that you see here. And when you look in the observed SST experiment, so obviously in the observed SST hindcasts, there is no SST error, so that's why this map is blank. But you see that there's a much larger positive turbulent heat flux error in the Western Tropical Pacific. And this actually, the pattern of this actually matches up pretty well with the SST error that you see here. And what this means is that, so this is positive means downwards. So this means that in the uncoupled experiment, the model is trying to warm the ocean, but is obviously unable to do so because it's uncoupled. There are also errors in ocean heat content, which you can see here again for SSH in the observed SST hindcast, there are no errors by definition. And in the fully coupled experiment, you see that there are positive height errors in the West Tropical Pacific and negative in the East as everything is kind of shifted towards the West. When you look at surface wind stress, these errors are consistent with the errors that we see in ocean heat content. you see that in the uncoupled experiment, the errors are actually larger, as the atmosphere is kind of trying to force the ocean, and these errors are consistent with the SSH errors that you see in the fully coupled experiment. So a depression of the thermocline in the Eastern Pacific and less upwelling in the Western Pacific, more upwelling in the East Pacific. And again, the errors are slightly reduced in the fully coupled hindcasts as the model is kind of more adjusted to its ENSO phase space. And finally, showing precip and shortwave radiation here as well. You can actually see that for precip, in the coupled hindcasts, there's an indication of this westward shift of ENSO precip anomalies. But actually for precip, the errors are reduced somewhat in the Western Tropical Pacific in the uncoupled hindcasts. And this suggests that perhaps the precip errors are more directly driven by SST. So by prescribing the SST in the uncoupled experiment, you do improve precipitation errors here. And again, similar story for shortwave radiation. These errors are reduced also in the uncoupled hindcasts, but they are slightly larger in the fully coupled hindcasts. So now I'm going to show the November initialization, and it's a similar story overall, really. You see that there are, again, positive SST errors in the Western Tropical Pacific, slightly reduced in magnitude, which makes sense because now we're initializing the model well into an ENSO event. But again, in turbulent heat flux, these errors are much larger in the uncoupled experiment as the model is trying to warm the ocean, but isn't able to do so in the uncoupled experiment. Sea surface height errors are also quite similar, with positive in the Western Pacific, negative in the East. And again, the wind stress errors are consistent as well with the SSH errors. And precip errors are actually more obvious in terms of the westward shift in the fully coupled hindcasts here. You see a pretty noticeable positive precip error in the Western Pacific here. And again, this is reduced in the uncoupled experiment, again suggesting that these are SST-driven errors. And then I'm going to show what happened there? Okay, going to show the February initialization as well. And the story is a little bit different here because now we're getting into the ENSO decay phase. So the main SST errors that you see are in the Eastern Tropical Pacific, which are, again, similar to what I showed earlier, which are associated with that slow decay of ENSO events. And actually, you see that this might be more of a local effect driven by the wind stress. These wind stress errors are consistent with suppressing the thermocline and suppressing the upwelling, resulting in a slow decay of ENSO events here. There are also some pretty significant precip errors in this initialization, again, positive in the Western Pacific, which are possibly related to SPCZ errors. What's going on there? So given this, we then wanted to look at how the errors are developing early, kind of in those first 2 months of the hindcasts. So now I'm showing 7-day running means. These are Hogmuller plots, averages across the tropical Pacific and Indian Ocean for our 2.5 north to south. And this is for the August initialization. So time is going down the y-axis. So the model is initialized from the top of the plot here. And I'm showing SST, SSH, zonal wind stress, and turbulent heat flux. And this is for the fully coupled model. And you see that significant errors develop very rapidly following initialization, almost immediately, in fact, in some variables. You see that for SST, these errors actually take a little bit of time to develop and to kind of reach a peak. This is a similar story for SSH. But for turbulent heat flux and wind stress, you see that these errors are pretty large almost immediately as the atmosphere is responding incorrectly. It's responding incorrectly to the observed SSTs at the time of initialization. But you can see that for the turbulent heat flux, this error is initially large, but then actually reduces in magnitude as you go kind of beyond the first 2 or 3 weeks. As the model is able to adjust, it's kind of able to put that extra heat into the ocean and everything. The ENSO extends westwards, and then actually this results in an overall reduction of the turbulent heat flux errors as you go past the first couple of weeks. You can also see that there's some indication that perhaps these early wind stress errors are driving an east propagating Kelvin wave, which you can see kind of propagates from the central to the East Pacific. It takes about maybe a month to propagate eastwards. And it seems that maybe this is what's causing there's actually a delayed error in the East Pacific, this cool error here, which might be related to that east propagating Kelvin wave associated with those wind stress errors. When we look at the uncoupled experiment, again, obviously for SST and SSH, there are no errors in this experiment. The wind stress and turbulent heat flux errors in the first 2 to 3 weeks are very similar to what you see in the coupled experiment. But then after that is when in the coupled experiment, the model is able to adjust to its own phase space. But in the uncoupled experiment, the model is continually trying to warm the SSTs and shift ENSO to the west, which you see in the turbulent heat flux, but isn't able to do so. And so finally, the last thing I'm going to show here. So we then broke the latent heat flux. So what I didn't show is that the turbulent heat flux is almost all of it comes from the latent heat flux error. So we break the latent heat flux down into different components relating to the mean bias, ENSO-related errors, observed ENSO anomalies, and observed mean terms. And we calculate products of these terms, and about 6 products shown here. And what you see is that almost all of the latent heat flux error is related to this term here, which you might not be able to read, but this is the term that's related to the ENSO-related wind error. So this suggests that almost all of the latent heat flux error is actually related to these ENSO-related wind errors. But this is still a work in progress. We're still looking at this in more detail. So that brings me to my summary. So I've shown that the initial westward shift of ENSO-SST anomalies in the model appears to be driven by the atmosphere, which immediately responds incorrectly to the initial observed ocean that you get, that is given to the model. And surface wind errors appear to drive turbulent heat flux errors, which then lead to an erroneous westward extension of the ENSO-SST anomalies. And these wind errors also drive wind stress errors, which appear to excite an east propagating Kelvin wave, which then gives you a delayed response in SST errors in the eastern tropical Pacific. In the coupled hindcasts, the model is able to gradually adjust because there's obviously that interaction between the atmosphere and the ocean, and the model is moving towards its own ENSO phase space. But in the uncoupled model, this is obviously can't happen, so the model is kept out of balance to some extent, which actually results, for many variables, results in larger errors, such as for the wind and turbulent heat flux, as the atmosphere is trying to warm the ocean but isn't able to do so. And hopefully today I've convinced you that it'd be really useful in terms of model error evaluation, it'd be really useful to be able to run these client models also as forecast models, including both coupled and uncoupled hindcasts, just such as the ones I've shown. Obviously, this is a really useful way of being able to help diagnose what is driving errors in the model. Because in a coupled model, particularly in a free-running model, it can be quite difficult to determine what is driving what error, because the errors can feed back on each other, changing the model climate and the nature of the errors themselves. And actually, I'm just going to end with a question here, which is that why is it that the surface winds are so rapidly responding incorrectly to the observed ENSO-SST anomalies? And this seems like a really important thing to understand, because it seems like it's a really important factor in the development of this very persistent westward extension of ENSO-SST anomalies. And I'll stop there.
Any questions?
Yeah, I very much agree with your point. We tried to do more of this CSM3 development, and we saw basically the same thing, but from a climate development perspective, like seeing how the mean errors evolve. It sounded like you said you did. Yeah, this was mostly ENSO-related errors as opposed to.
Yeah, I mean, just when we looked at the latent heat flux, that seems to be the case, and obviously the speed at which these errors are occurring as well suggests that it's kind of like a faster process that's involved. And yeah, we saw here that it seems to be that I've got different terms here. It seems like the mean bias terms are pretty small overall, at least in terms of the latent heat flux. So it didn't seem to be the mean bias that was causing these errors, that they're related to the ENSO component.
Yeah, it's cool. On the next slide, the crux, of course, is answering that last question.
Yeah.
what we have not been able to do, I guess. It's fair to say, seems kind of similar kind of things. And so I'm curious if you thought about that at all, and I'll just seed it with a little bit. That one thing that I think, I know it's Brian here, Brian Medeiros is doing is running a perturbed parameter ensemble in forecast mode. I think he's doing that. And at least then you have an ensemble of possible different errors showing up. You might learn something. But do you guys have any ideas about how to get that question?
Not really, to be honest. I mean, I wonder if it's some sort of boundary layer issue or some convective parameterization problem that's just, there's just straight away the model just doesn't like the state that it's been put in basically between the atmosphere and the ocean. And I know that I've spoken to people at ESPWG who have worked on this problem as well, but they immediately have far too short easterlies of chocolates. And they, I think they did something, I'm not sure whether it was nudging or whether it was some way of tuning the model, but they were able to kind of reduce those errors, but then everything else in the model broke. So yeah, it's a pretty big problem, and yeah, I don't know exactly what's driving it.
Yeah, I mean, one thing we looked into a bit is the maritime continent, and that was getting biased very quickly, like too warm. And I wonder,
like maybe an error, like an issue with like resolution of land or something like that. Or,
yeah, not having all those ocean passageways.
Yeah.
Yeah. So we like nudged the temperatures in the maritime continent to observe, and that led to some improvement, but not our whole.
Okay, yeah, interesting.
One wonders whether sensitivity experiments could be that you could maybe smooth the surface in the Pacific such that it doesn't respond, even though you set up the wind response, the ocean itself doesn't feed back as much. And I'm wondering if you could just tune that. Oh, it's artificial, yeah, I agree. Yeah. But like, it's very clear, this Bjerknes response of the surface stress is too strong. And I wonder whether you can get at that by trying to understand the sensitivity of how your whole cycle of bias growth that you describe.
Yeah, I think that'd be interesting to try because, I think there's obviously a lot going on, so it's kind of a little difficult to pin down exactly. But yeah, I think there's a number of different ways to go about it, probably. Yeah.
It's quick. Just a quick comment on that. I mean, one thing about this error is that this is so long-standing. It's in almost every model, almost every version. So if it's something like that, why hasn't anyone been able to kind of address this problem before? I mean, to me, it's always felt like this is something fundamental about the nature of the way parameterization is being addressed in trying to deal with missing resolution. If you look at gustiness, for example, there's always been this issue that models they don't seem to be gusty enough. Basically, you don't have enough of this kind of fast process, and there's no real easy way to put it in. That's what stochastic parameterization presumably is trying to do. So it may not be that an easy fix is possible either, but at least to identify where the error is would be, we think is a good first step.
Okay, I think we should conclude there, and if there's more discussion, we can do it during the break. So we're a bit behind schedule, but why don't we try, if we can, to still come back at 10 after 11 to stick to the schedule time.
Okay, so we are on time. Thanks everyone for coming back. So we have a short before lunch session with two talks. One was from so the first one is Kay Wang, representing QBO impact on the Canadian legislation.
Oh my. Okay, cool. Yeah, thanks for having me. And today I'm going to talk about our recent work on the QBMG connection, where we proposed a potential new mechanism through the mesoscale convective systems in the observations and some preliminary results in the modeling framework. And this work was done in collaboration with Jack, Mitch, and Yaga here at NCAR. So first, a brief introduction of the Menden-Judy oscillation, or MJO. It actually refers to the organized convection propagating eastward in the tropics. And it has a time scale of 20 to 100 days, and it is the dominant subseasonal mode in the tropical troposphere, which bridges weather and climate as it has both downscale impacts on weather patterns and upscale impacts on the climate modes. And due to that, it actually serves as a very important predictability source for the S2S or even S2D predictions. And from the intensive works from the observations, we know that the Quetelet-Baogne oscillation in the tropical stratosphere, or QBO, have strong impacts on the MJO activity. That MJO is stronger and more likely to propagate across maritime continent in the QBO east phase than in the QBO west phase. And such unique QB-MJO connection has some very interesting features such as its seasonality, location preference, its uniqueness among the convective coupled equatorial waves, and its emergence. And during the past decade, since the discovery of the QB-MJO connection, several mechanisms are proposed, but I don't think the connection is thoroughly understood because these proposed mechanisms cannot completely explain all these features or the QB-MJO connection. And other than that, all climate models fails to reproduce the QB-MJO connection in it, even with a prescribed stratospheric condition, same as the observations where the QBO is perfect. And other than that, the QB-MJO connection is slightly captured by the forecast systems and some MJO case simulations, but improvements are needed in this forecast system to fully capture the predictability source coming from this QB-MJO connection. And our recent work actually found QBO does not only modulate the MJO in the tropics, it also modulates the mesoscale convective systems in the tropics, or the MCSs in the tropics. Here on the right, I'm showing you the composite maps for the MCS frequency, focusing on the Indo-Pacific domain in conditioned by the QBO east phase and QBO west phase in the NDG-FM season. And if you look at their differences here, you will find a significant enhancement of this MCS frequency west of the Sumatra Island or west of the maritime continent. And if you compare this pattern with the locations where the MJO negative precipitation will happen before the MJO propagate across the maritime continent, you find a very good alignment for this negative MJO precipitation patterns, along with this enhancement of the MCS frequency west of the Sumatra Island within this gray box domain. And if you are familiar with the multi-convection structure related to the MJO mode, this negative MJO precipitation anomalies happens before the arrival of the mature MJO deep convections. So they represent the locations where these leading shallow convections are happening. And if you get a stronger leading shallow convection ahead of the MJO deep convection, it will transport more moisture from the lower level to the higher levels in the troposphere, and therefore helps the growth of the MJO convection itself and its eastward propagation. And if you investigate or do a composite analysis for the MJO-related vertical profiles for its vertical velocity, specific humidity, and dry static energy as a function of the precipitation anomaly within the domain I just showed on the last slide, and do a difference in the QBO east phase and QBO west phase, it is very interesting. You'll find this kind of low-level humidification for this negative MJO precipitation anomalies where these shallow convections are happening, along with a warming effect around the same levels. So it seems like the MCSs are getting enhanced over this leading shallow convection development region for the MJO mode, and it in turn brings more moisture and instability in the lower levels, helps the growth of this leading shallow convection, which in turn helps the eastward propagation of the MJO across the maritime continent in the QBO east phase. So this kind of interaction between the MCSs, MJO, and the QBO are also found if you, if you do do a Hofmuller diagrams of the MJO precipitation and MCS precipitation the function of the arm and face and conditioned by the different cubial faces. So first thing we realize here is regardless of the cubial face, we constantly see a leading enhancement of the MCS precipitation ahead of the MGO propagation, MGO convection at both the western and eastern ends of the maritime continent. And if you do a differences between the cubial east face and cubial west face Hofmüller diagrams, this is a pattern you are seeing. First, you are observing overall enhancement of the MGO convection as denoted by the contour lines here. Secondly, if you look closer around the western boundary of the maritime continent, you see a leading enhancement of the MCS precipitation ahead of the enhancement of the MGO convection. It has two effects. First, it is westward propagating into the MGO convection and get organized by the MGO convection, intensifying the MGO convection amplitude over the Indian Ocean. Second, it is constantly leading the enhancement of the MGO convection propagation during its propagation across maritime continents, leading to a more eastward propagation MGO convection in the cubial east face than in the cubial west face. So overall, we found the cubial east face will enhance the MCS activity west of the maritime continent, which helps the MGO to propagate across the maritime continent. These are all the observational work we did. And in the latest version of CAM7, actually, it partially includes the MCS effects by adding heating tendencies through the multi-scale coherent structural parameterization, or MCSP. So it is activated or triggered when the convection depth is greater than 500 hectopascal. So basically, if there are deep convections in the happening, like we think there might be, there will be MCS happening, and the updraft of the MCS will bring more warm air in the lower levels to higher levels, creating some heating there, also due to the condensation. And the downdraft of the MCS will cause some cooling at the lower levels, along with the cooling from the re-evaporation of this rainfall. And therefore, when the MCSP is triggered, we're adding this sinusoidal heating tendencies to the in addition to the DM heating across the convective heating depths, creating a warming effect in the higher half of the DM depths and cooling effect in the lower half of the DM depths. And this heating tendency intensity is controlled by a parameter called the heating coefficient of the MCSP, or the MCSPHC here, which this parameterization scheme, once they are introduced in the climate model, it will improve the convective variabilities in the tropics. So what we did in our recent work is we related this MCSP scheme to the conditions of stratospheric wind. We conducted 2 single-member 30-year simulations, where in the CAM7 control run, we set the MCSP heating coefficient to a constant value, so it will not change in response to the cubial phase. While in the sensitivity run, or CAM7 run, we set the heating coefficient as 0.1 when the U50 is greater than 0, or the cubial at 50 hectopascal in its westerly phase. And we increase the heating coefficient to 0.7 when the U50 is less than 0, or when the cubial phase at 50 hectopascal is in east phase. What we want to do here is we try to prescribe the cubial modulation of the MCSs from the observations by manually tuning this up or down, this heating coefficient for the heating intensity the MCSP is adding to the DM scheme. And we want to know, could this prescription of the cubial modulation of the MCS in the model allow the model to capture the cubial M2 connection? And we are seeing some preliminary promising results from some preliminary diagnostics. So we found here on the right is actually showing you the differences between the MGO filtered OIR standard deviation in the DJF season. Basically, it's measuring the season mean MGO activity, and the shadings are giving you their differences in the cubial east phase versus cubial west phase. So in the observations, you see this overall enhancement centered around the maritime continent for the MGO activity. And in the CAM7 control run, you don't see this kind of enhancement of the MGO activity in the QPO east phase. Instead, you see a decrease of the MGO activity, which is in the opposite to what we observe in the real world. But by manually tuning up the MCSP heating coefficient in the QPO east phase, we are now reproducing the observed QPO MGO connection. The MGO activity is now increased in the QPO east phase around the maritime continent. That is a good sign for the QPO MGO connection in the respect of the QPO modulation or MGO amplitude. So for the MGO propagation or propagating features, we're doing this Hofmuller diagram based on the MGO OR. So on the left, I'm showing you here the results from the observations. In the QPO east phase, you see a stronger MGO, like more eastward propagating across the maritime continent compared with the QPO westerly DGF season. And in the control run, where the MCSP heating coefficient is set to a constant value, therefore the QPO modulations of the MCSs are missing there. You don't see this kind of correct capturing of the QPO effects on the MGO propagation. But if you prescribe QPO modulation of the MCSs from the observation into the CAM7 by tuning up or down this heating coefficient associated with this MCSP, now you are reproducing this more eastward propagating MGO across the maritime continent in the QPO east phase than the QPO west phase. So far, the preliminary results looks very promising through the modifications of the MCSP scheme in the CAM7. So finally, some takeaway messages from this work. We propose a new multi-scale interaction mechanism for the QPO MGO connection, where we think MGO is preconditioned by the MCSs around the maritime continent, favoring its eastward propagation. And QPO could modulate the MCSs around the maritime continent, causing a decoupling between the MGO and MCSs in the QPO west phase. As a result, the lack of leading MCSs around the maritime continent leads to a weaker and stored MGO in the QPO east phase. These are from the observational work, but it remains an open question how QPO may modulate the MCSs around the maritime continent. And by prescribing this QPO-MCS relationship in the development version of CAM7, we see a captured QPO-MGO connection in CAM7, which is very exciting. But we acknowledge these are only single member simulations with 30 years. So we will conduct more ensemble simulation to confirm the robustness of the captured QPO-MGO connection there. And also we plan to diagnose for the effects on the MCSP on the MGO multi-convection structure, where we think that will be the responsible physics to capture the QPO-MGO connection. And that concludes my talk today. Any questions or comments are extremely welcome.
So thanks for the time. So we have plenty of time for questions.
One comment on the question, just so that people don't take away the wrong thing. We don't necessarily expect CAM7 to have the QPO MGO connection. It's just because you've kind of prescribed it in, just so people don't go away thinking this is a model that has the QPO MGO connection.
Yeah.
And then my question is, you seem to be pretty convinced that it's the mesoscale systems that are responding directly to the QPO, but how are you convinced that it's that as opposed to, say, some large scale circulation change that changes moisture that is then changing the MCSs?
That is a good question. So first, we ruled out the possibility of the MCS response due to the QPO-MGO connection. Basically, we only exclude the MGO active days. Still, the QPO modulation or MCSs are thin if we do the composite of the seasonal mean MCS frequency there. And secondly, we did composite the background mean SST state in the QPO east versus QPO west state. And this is actually, the shadings are actually their differences with QPO east minus QPO west. First, none of these SST differences are significant. Second, actually, it is causing a cooling over the western boundary of the maritime continent, which is in opposite to an enhancement of the MCSs here. So I think we can exclude effects from SST or moisture there. But other possibilities like the large circulation changes are not strictly excluded here. I admit that. Yeah.
I'd like to comment a little bit on this. The MCSP is a different way of representing organized convection. It represents coherent structures, which means the upscale effects really of tropical convection is the major one. We've looked very carefully at the MCS in 3 models: the INCAR model, the HDOE model, and the Met-Office model. The results are quite consistent. It has a hugely positive effect on the Madden-Julian oscillation. That is completely proven. And we know the NJO and QPO are connected closely. So I think it's very, very encouraging what you've got here, because it's a way forward. What the MCSP does is to represent mesoscale circulations in global climate models. I've looked at that in the past in the ECMWF model, which of course of data assimilation, and the results are getting remarkably close to that now. So I'm quite encouraged by this, and you've done a fantastic job on this. It hasn't been an easy task, but I see a way forward. This is a new way forward. And it's been, the Met Office was particularly good because it's a connected, weather climate code. I'll say a little bit no more at the moment about that, but it's interesting.
Oh, thank you very much.
Just have you looked that when you either strength of the MCSP or just this inclusion, whether convection as diagnosed in the model is actually deeper than the default setup? Because that's not built into the way that it's configured.
Can you see that again? Sorry.
Well, the way that the existing scheme decides what the top of convection is also used when you with MCSP. But I'm wondering if that somehow projects onto a deeper convection compared to the default version. Sorry, this is
to your question. I do think it will promote a deeper convection, like in the model by adding the heating tendency at the top half of the DM. But I don't think. I think that added tendency is physically reasonable because the mesoscale convective systems are not being resolved in the model, and it is missing by the parameterization scheme if you do not add this MCSP scheme into the model. That is my understanding.
I'd add to that the depth of the convection in most climate models is too shallow. It's a general problem. And it's got to be tackled. And I agree with you, Rich, that to get the deep convective properly parameterized with ordinary convective schemes should be a priority. But it's not the case here, unfortunately.
Agree with that.
Yes, thank you.
Okay, so thank you very much. We move to the next presentation. Implementation of 7 volcanic sulfur emissions in CSM and its impact on in WACAM 6 compared to CVCWG.
Okay. So I've been working on the implementation of the CMIP7 volcanic sulfur emission in CSM and evaluating how this is different in WACAM 6 compared to CMIP6. And I've been working on that with Simone, Doug, and June in ACOM. This is time series of the new and old emission for explosive volcanic eruptions. The new one is in yellow, provided by Aubrey's team at University of Exeter. The main differences between this new emission file and the previous one in blue is that, first of all, we are covering the 2014-2023 period. And we also have the inclusion of more small to moderate volcanic eruptions. And we're also including upper tropospheric eruptions, since they might be transported in the cloud, might be transported in the stratosphere due to self-lofting through radiation interaction. And additionally, there are more multi-moderate volcanic eruptions included for the pre-industrial period due to use of new and more accurate ice core records. And another important thing is that the altitude, not just the amount of previous eruptions that were already included in CMIP6, have been changed now. And we will see how lately. So the script that I wrote builds upon the script that Mike Mills wrote for CMIP6. We have in input the location of the volcano, the altitude of injection, the band of injection, and the timing. So what we do is point injection. In both cases, in CMIP6 and now in CMIP7, we use 6 hours emissions. The main difference is that now we are implementing the Gaussian distribution. As you can see from this plot for the Pinatubo eruption in 1991, we had the blue dots before, which are supposed to be uniform distributions. And now we have what is in green or orange, which is the Gaussian distribution at the altitude provided and with a standard deviation that is defined by the injection depth. Following what Mike did, we applied a mass scaling factor of 1/1.8, but instead of applying it only for injections that are larger than 10 teragrams, we applied it to all kind of eruptions, and that would result in the green line. We also, following what Mike did, we applied altitude scaling for injection larger than 3.5 teragrams and altitude larger than 20 kilometers. So we shift them down to 20 kilometers. And the orange line is what the Pinatubo injection would look when we apply these altitude scaling. So in the simulation that we performed to test these injection files, I will have CMIP7 in orange, that is when we're applying both mass scaling factors, and the CMIP7 stars when we don't apply the mass scaling factor, which was the first test that we performed. That's how the climatology would look like. So beside the fact that now we have to average between 8050 to 2021 instead of 8050 to 2014, we can clearly see, comparing panels 2 and panels B and panel C, that we have higher injections and also injections at the upper troposphere that were not included in CMIP6. But since we applied the mass scalings to all the eruptions, at the end we have a similar amount injected per year, around 0.54 in CMIP7, 0.58 in CMIP6. And we, for future scenarios, we use the same values, the same emissions file built for the pre-industrial period, but we have been suggested to use a 9-year ramp over 2022 to 2030, which I don't think is gonna affect much the simulation, but that's what they asked us. So we test these, the CMIP6 and the CMIP7, both with all the mass scalings and just with mass scaling, but not the altitude scaling reduction in WACAM 6, 2 degrees resolution, fully coupled. And for this, we have what I call CMIP6, CMIP7 stars, and CMIP7, accordingly to what I presented in the previous slide. And I added a new simulation, CMIP7 and E30. That is the one that Simone was talking about yesterday, using CSM3 CAM6, which approximately has 1 degree resolution and 93 vertical levels compared to 70 vertical levels of WACAM6. But in this case, it's a fixed SST simulation. We evaluated our results, comparing them with observations, and I wanted to rank the skills of the simulations using this metric, the weighted root mean square error, which takes into account the distance between model and observation for each grid point. So it's evaluated in terms of how well they perform in time, level, and latitude, not longitude because those are tonal means. And they are evaluated with respect to the observation standard deviation. This is an example for GLOSSAC that provide the stratospheric aerosol optical depth and how the standard deviation would look like. And we also take into account the latitude. So we wait for the latitude of the grid cell. We started looking at the stratospheric sulfate burden. I showed the whole time series from 1980 to 2022, but we only have observation from years for the Pinatubo period. So generally what we see is that for large eruptions, we have a smaller burdens in CMIP7, independently from kind of simulation we perform compared to CMIP6. It's more variable for small to moderate eruptions. And when we evaluate the model skills for the Pinatubo period, here we can see that CMIP6 has the larger weighted root mean square error, which means that has the lowest skill in reproducing observations. So with CMIP7, especially when we apply the altitude scaling, we get a better reproduction of the observations. Then I look at the stratospheric aerosol optical depth compared to GLOSSAC, as I showed before. GLOSSAC here is also showing the first in the first row. Then we have CMIP6 and the 3 version of CMIP7 simulations. Generally, the triangles represents the volcanic eruptions, and the size is proportional to amount of SO2 that has been injected. So we can see that for the large volcanic eruptions, El Chichón in 1982 and Pinatubo, we can better represent the southern transport that we were not able to represent in CMIP6, or smaller in for Pinatubo, at least smaller values compared to GLOSSAC, and that we were able to reproduce in CSM only during meridional spread of the SO2 injection. So in this case, with a point injection, we can get a similar dispersion of the aerosol cloud. And the values shown on the right actually show that we were doing a better job with CMIP6 when we evaluate that for the whole time series, but to me, it didn't look like that when looking at large volcanic eruptions. So I wanted to, I went more in that. Okay. And I look at the weighted root mean square error by the time series to evaluate where we have this worse performance in CMIP7. And if excluding the simulation in CMIP7, when we don't apply the altitude reduction, we have a similar behavior between CMIP6 and CMIP7. And so the main problems come from the small to moderate volcanic eruptions. And I was wondering if that was dependent on the new approach that we were using or on the data set itself. So I first focus on the Pinatubo eruptions, evaluating the extinction profile for four more important moments. So the build-up phase, the peak in 1992, and then the descending phase of the eruption at the end of 1992. And what we see is mostly that, so Glossec is representing the first column, and then we have CMIP6 and the other three simulation from CMIP7. What we see is that CMIP7 without the mass scaling reduction, and we understand that it's completely offset. But CMIP6 better represents the extinction distribution, still overestimating it during the descending phase, but not as bad as CMIP6. And then I went more in depth on the small volcanic eruptions, again, to make sure that our approach is correct and it's dependent on the new emission dataset. For the first eruption, the Kasatochi one, we have a large disagreement with observation, the dotted line in black, in all the cases. So, and this is mostly based on studies that I read. They're based on the fact that ice and ash are not included in our simulations. So we are keeping too much SO2 in the stratosphere. So I excluded that volcanic eruption from our analysis, and I focus on the second and third eruptions. Since CMIP6 seems to be really close to the observations and have a large disagreements in the new data set. And looking at the extinction profile and then comparing that with the emission strategy, what we see is that we have a larger overestimations in CMIP7, and this is due to the fact that we are injecting at much higher altitude compared to CMIP7. And there's not much we can do. This is how it looked like, but it's consistent with the new data set that was provided. But then we also saw that, I forgot to mention that on the previous slide, that we have a good agreement for the Raikoke eruption, which compared to the previous eruption, inject like 4 times more and almost at the same altitude. So I would assume that for larger injections, this low, kind of high altitudes for high latitude injection, the resolution of the models is really impactful. But again, there's not much scaling that we can apply here. This is how it's going to look like. Is fine as long as it's not my fault, like in producing the file. I also look at the rigidity forcing. We have results that are consistent in all cases with observations. Clearly, we have less variability with CMIP7 when we use CSM3, but just because compared to the other simulations, we did a fixed SST case, not a B case, so we remove part of the variability. But we have comparable values for the Pinatubo eruption, so we are happy with our results. Even the profile of the tropical temperature anomalies for the Pinatubo eruptions looks good in CMIP7. It was good also in CMIP6, but at least in terms of how it's distributed. But now we also have more comparable values, not this strong heating that we saw in CMIP6. And even the stratospheric ozone column that we evaluated against observation from SWOOSH. Here is shown for 4 different regions, yearly means, 60 degrees north-south, tropics, and the relative spring in the northern and southern polar region. And when applying the weighted root mean square error over the whole time series, we can see that we get better results in CMIP7. And this is how the climatology would look like. The global sulfate burden and the global stratospheric KOD are pretty similar in how they are distributed and the global values. Actually, those are zonal, but and what they expected with the new data set was a larger burden, a larger stratospheric AOD, but since we applied all the mass scalings, we mostly have the same results. But we have an increase of the total ozone and the stratospheric ozone column of about 5 Dobson unit. So generally, this summarizes what we have seen. We have better results for a better agreement with observations in terms of global stratospheric sulfate burden, stratospheric ozone column, and even the stratospheric KOD and extinction, but depends on the size of the eruptions, and better tropical temperature anomalies. Thank you.
Thank you, Sylvia. Don't have any questions?
I think you said this, but I didn't quite follow. This altitude shift, why do we do that?
Because we tested in CSM and the results were really awful, completely offset compared to the observations, and was something that might be before, and we assume that with the new data set things would have been better, but they are not. Actually, most of the volcanoes have been shifted upward, so we had to apply that, and this is fine because what the Thomas group said that as long as we document what we have done in CSM, it's okay that we apply other mass scaling factor altitude reduction. But I didn't want to apply that also for small volcanic eruption because that was the main point of the new data set. So, and actually for dry cog it works pretty well. So not sure what to do for those.
So is it like to get the TOA right or the burden?
It's mostly the stratospheric QD and the extinction. Maybe you said this, but I missed it. You calculate the root mean square error. You compare with observation, but there are different source of observations. Like errors, so you have WAWG and you also have HRRV. Which one you're using? I'm using all of them based on the variables that we are evaluating. And actually, one of the main points. So if you look at the number itself, we actually have like a big difference compared to low skills compared to observation because the numbers for AOD are really big. So it's low skills.
and better skills for the stratospheric surface burden, and even better for when comparing the stratospheric ozone column. But then it's a result of how big is the standard deviation on observation. So that's why I remodulated the colors in a way that we don't really focus on the number, but we compare the skills with respect to the models.
Okay. Thank you. So go for lunch. The first talk after lunch is at 1:10 p.m. So make sure to be here on time.
All right. Hi, everyone. Welcome back after lunch. So now we have a series of talks on a number of kind of cross-cutting projects that are ongoing. And so the first of these is Ryan Patnod talking about the INFORM project, which is trying to bridge the gap between field campaigns and evaluating our models. And for the speakers, I'll try and give you a 5-minute warning before your time is up.
Let's test this. It's working. Everyone can hear me? Okay, great. Thank you for the introduction, Isla. My name is Ryan Patnod. I'm a postdoc here at CGD. And as she said, I'm going to be talking about this INFORM project, which is about bridging the gap between CSM and field observations, specifically aircraft observations. So anything that's collected aboard aircraft in field campaigns. And this project right now, or at least my portion of it, is motivated by the large biases that continue to exist in representation of global cloud cover in both CAM and other global climate models. This study from Brian Medeiros in 2023 shows a low cloud cover bias globally compared to the ISCEP model, and that continued on from CAM 5 into CAM 6. However, there's been some differences in where that bias has changed between those two models, but it still is present and obviously underrepresenting global cloud cover. So specifically, global climate models struggle to resolve liquid phase clouds. And the portion that I'm most focused on is this stratocumulus to cumulus transition. So this other study done by Davis and Medeiros in 2024 looked at different cloud regimes around the globe, and they isolated one particular using a K-means clustering method, their CR7, which was specifically looking at like low boundary layer clouds or stratocumulus in the transition to trade wind cumulus clouds. You can see on the left where these types of clouds most commonly exist, the western part of the continents, and the model has been underrepresenting these as well, leading to issues. And we really are focused on trying to better understand the process level understanding of where these biases are occurring. So I just want to, just want to also point out that fortunately for us, we've had a lot of field campaigns that exist already in these parts of the world where this type of cloud regime exists. So I'm going to be talking about the CSET and the Socrates campaigns today. And you can see where those two took place. So this is the INFORM team. It's a cross lab effort. So there's folks here at CGD, there's folks at EOL, and I'm only talking about my portion of the project, but if you're here tomorrow, at the end of the day, Todd Emenegger will be talking about the deep convection focus that he's been working on. So stick around for that. And that's, but I'm only be talking about my portion of the INFORM project. So in an ideal world, we would have this perfect apples to apples comparison of the model to observations. And we know in reality that doesn't exist. It's closer to something like this. Christina has made this, and it's a great representation of how we are trying to bridge this gap where the model has, coarse resolution, grid box average quantities in these in that space, whereas the observations, although they're great, they're not perfect either. Certain instruments will have detection limits or uncertainties when they're sampling. So obviously, we're trying to find sort of this perfect happy ground where we have a better representation of the model, but also, sort of this refined observation apple as well. So these are some of the key points down below that we're trying to address: the temporal and spatial representatives. So that's focused on the observation side, the sampling bias, detection limit, like I mentioned. There's also a spatial and temporal resolution mismatch. So we're talking about CESM, we're talking about, 100-kilometer grid spacing, whereas an aircraft observation can be 1 hertz. That can be on the order of, 100 meters. So bridging that gap is also really tricky. And then there's a couple other key points that we're trying to focus on down the road, looking at instrument simulators and how we can use usability for model development. So how can we improve the model going forward? So we're really focused on a regime-based approach, looking at process system for assessing the research model. So I've been talking about stratocumulus to cumulus regimes, which is this large-scale circulation dynamically driven by the Hadley circulation. As the subtropical winds go southward toward the equator, you have this transition from low-level stratocumulus clouds and then a transition to the cumulus regime. And you can see in the bottom diagram, we have a really well mixed coupled boundary layer, which is topped by the stratocumulus deck. And as the boundary layer slowly decouples, you get entrainment from above. And then as the sea surface temperatures warm, you can get this decoupling leading to more open cell cumulus type clouds. But from an aircraft perspective, there's a lot of different quantities here that we can be measuring to sort of understand what's driving this transition between stratocumulus to cumulus clouds. These are all quantities that we can actually capture in real time. If we want to look at the cloud microphysics in cloud, like liquid water content or cloud droplet number, we can look at the aerosols in the boundary layer or above cloud, what's driving and seeding these types of clouds. We can also look at the turbulence and the dynamics that are occurring, as well as the actual radiation, shortwave, and long-wave fluxes at the cloud top. So this regime-aware approach, so basically what we're trying to do is produce this process system database. So just pulling out the most important parts of the aircraft flights and the campaign as a whole, that can be most useful. So only isolating specific flight maneuvers, which are listed on the right, and the quantities that we can actually measure during those specific flight maneuvers, all the different quantities we can measure during that. And that's sort of like refining the observations that can be then used on a more statistical bulk level to analyze sort of the same bulk statistical quantities from what the model outputs. So it's kind of motivated to work away from this co-location aspect where we're comparing the field observations to sort of what's happening on a process, cloud regime type system. So what we're focused on here, and this is a time series of a specific flight during Socrates and the 4 different flight maneuvers that we're looking at. You can see that we can isolate each one and extract those, and we sort of have these flight blocks that we can then apply some cloud regime methods, which I'll talk about next, and have this process system database that we can then use to compare to the model. So you'll see anything in the black is basically time where we're like, this is probably not as useful data. We can look at the above and below cloud quantities, which are the blue and green portions, whether we're profiling in cloud, that's the red. Blue is when we're level in cloud, purple is above cloud. So these are all the times during the flights that we can extract and use and ultimately produce effectively a database that we can then give to the users, that it's all this refined data that then they can just take and compare to their own specific types of model simulations and focus on whatever processes that they're focused on. So now I want to talk about how we're actually doing this cloud regime method. So we have all these data that we think are important during specific flight maneuvers that we think are most relevant. But now we want to be able to say, well, this flight maneuver was a stratocumulus cloud regime, and another cloud maneuver might have been for an open cell cumulus. So what I'm showing on the left is a time series of the Cloud Radar product. It's an echo type product. So this is some folks at EOL that have been able to sort of already categorize the types of clouds that we were sampling. So this particular example is a low stratiform type cloud. So very clear the stratocumulus type clouds. So what we did was we went through all the flights during Socrates and just found time periods during a given flight where it was very obvious that it was one cloud type. So in this case, it's very clearly that stratiform cloud. So we took just that time out of the flight and then co-located it with ERA 5 data, looking at all of these cloud controlling factors, which from the literature are known to sort of drive stratocumulus or drive the transition to open cell cumulus. There's a lot of literature in all of these. And then just for these specific flight blocks, whereas a given, I think it was 6 total flights, we said, all right, this is only stratocumulus co-located with ERA 5 data. Now let's look at how the cloud controlling factors look. You can see from the PDFs on the right, there are certain cloud controlling factors that are more obvious for a given cloud regime than others, whereas like Omega, I think 700 millibars, not a big difference between those. So we didn't actually use those to sort of separate between the two cloud regimes. So we see, all right, service wind speed, service temperature up here, pretty clear difference. So we focus on just those and produce these joint PDFs of the cloud controlling factors. Kind of hard to see, but on the x-axis for all these panels is M, which is basically a low tropospheric stability term. The top two are the wind speed y-axis, and then the bottom two panels, the y-axis is estimated inversion strength. So basically, how strong is that inversion in the lower troposphere? That's between the surface and 700 millibars. And then, based on what the definition of the echo type product, that's how we distinguish between stratocumulus and open cell cumulus. And I just want to point out again, this is only for about 6 flights, where it's very clear and obvious. And then based on that, we sort of define thresholds for a given cloud regime. And then we can apply that to the rest of the flights where it was less obvious based on the echo type product. And then obviously there's some parts of this PDF space where it's unknown. So we just kind of said that's an unknown cloud type. And then you'll see once we apply it to the rest of the campaign, this time series now, where we have all the flight maneuver patterns, we also have a cloud regime. So it's in a regime-aware cloud process system database. And you'll see when we apply it to the entire campaigns, it looks something like this. So you can see the distribution of the two cloud types and then the unknown category for CSET and Socrates. The bottom are the thresholds we chose to use for that. And then the marker shape tells you just what was the flight pattern that we were in during that particular flight. So now moving into how do we use this process system database to assess the models? So it's kind of hard to tell in this diagram, it's really small print, but the main point is we want to be able to provide this to model users so that they can run their own simulations and then make decisions on how to proceed using these aircraft observations to evaluate whatever they're focused on, whatever their scientific question is. So the first thing we really wanted to focus on was, okay, we have this process system database, but let's make sure our model base state is correct. So we started with just assessing, the environmental conditions during the simulations to make sure, you at least have a good starting point. And fortunately for us, the Socrates campaign had dropsons during that. So we actually have vertical profiles of the environment during those flights that we can compare to what the model was producing. So we first did this model base state assessment. So I'm showing the vertical profiles of relative humidity for the dropsons that were launched during the flight campaigns. We used the same thresholds that I showed for the aircraft observations to define the cloud regime for the dropsons, and then co-located that with whatever the nearest column was from the model output, as well as Era 5. This is a Camp 6 run nudged for U, V, and T. And you notice the nudging timescale, 6 hours on the top and 48 hours on the bottom. And you can see that the model is actually doing a pretty decent job of showing, the different relative humidity profiles for the two cloud regimes. And then on the right is just the difference. So can it resolve the difference between these two cloud regimes that we saw during the observations? One thing you also can note is we wanted to also investigate whether or not a difference in the nudging timescale led to a degradation in how well the model can resolve this model base state. And you actually see that 48 hours doesn't actually produce a significantly worse model base state compared to the 6-hour nudge simulation. So that's good. Model users might want to have less nudging. So we can say with, decent confidence that, it might not be too big of a problem to, nudge a little bit less and you still get a decent result. I also want to point out the Era 5 should look really good compared to the dropsons because the dropsons are used directly for the input for the simulation. So that's part of the reason that that's so closely related. But I would just also point out that although stratocumulus is pretty well resolved, the open cell is a little, clearly more moist as you go between about 900 and 700 millibars. So that's something that could be improved. We did the same analysis for the new Camp 7. You'll see, we still see that moisture bias for the open cell cumulus clouds that we saw in Camp 6. But overall, doing a pretty good job. And then here is really just like the difference between the two cloud regimes for the observations compared to the model. And you'll see that the model, can produce the difference in vertical profiles between the two cloud regimes compared to the observations. It actually does a pretty good job, which was nice to see. So, okay, at this point, you're like, all right, now in this diagram of how do we proceed, we'll call this tolerable model base state. Let's move into actually digging into the cloud microphysics. So what I'm showing here is very preliminary. I'm showing these simulations have been run very recently. So this is very preliminary data, but I'm showing PDFs of cloud droplet number on the left and liquid water content on the right for CAM 6 and CAM 7 runs. Again, this is nudged for U, V, and T. And then the colors of the PDFs just denote the two cloud regimes. And I'm only focusing on the warm phase portion of the clouds. And you'll see observations that we saw not a big difference, but there is a clear difference between the PDFs, between the stratocumulus and the open cell clouds. And the model is actually doing an okay job at resolving that difference. You'll see CAM 7, especially for the stratocumulus, the dashed blue line is a little bit broader. It's shifted to slightly higher cloud droplet number. So it's actually improving a little bit in terms of the microphysics. And I would say, again, for liquid water content too, CAM 7 is doing a little bit better job of representing the difference between the two regimes, but it's clearly a little low bias for liquid water content, but doing a decent job. And then I did the same thing for some CSAT simulations that were just getting going. Again, we see a pretty obvious difference in the cloud droplet number between the two cloud regimes that the model is not necessarily able to resolve. Specifically, the stratocumulus cloud is a little bit more narrow and has a higher peak around, maybe 30, 40 per cc. And then obviously the liquid water content is also struggling to resolve that difference. But it's clearly showing that this, well, I'll get to that point right now, where show the difference between our results to a study done by Isabel McCoy in 2021, where they looked at CAM 6 nudge simulations compared to their CSAT and Socrates simulations. So that's cloud droplet number on the bottom. And there, what they found was that CAM 6 had a low bias for cloud droplet number for both of the campaigns compared to what they observed. The main difference, what they did was a direct co-location for all aircraft observations and model below 4 kilometers. So I would argue that our results using this compositing method where we have this threshold, I didn't actually mention that, but I'm using my same thresholding method to define our two cloud regimes that I used for the observations. The same numbers were used for the model. So I would just argue that this method may show some promise in terms of a better way of assessing, or at least doing a direct comparison between aircraft observations and the model, but I would say the jury is still out. It's very preliminary and early on, but or at least some optimism that this method may be working well. So just some discussion to finish up. We created this process system database. It's motivated to use aircraft observations for a specific cloud type, and it's meant to be provided to users that are running model simulations that want to use direct in situ aircraft observations. So we so far have assessed the model base state and the microphysics. And the model representation of the base state is actually pretty good, and it was able to represent distinct cloud regimes in terms of the base state compared to the observations. Early signs show the microphysics that there's a low bias for cloud droplet number, which I think has been discussed in the past, but we might see some improved representation. So this updated cloud microphysics may be improving representation of these types of clouds. And just a little preliminary results suggest that this compositing method for the two cloud regimes may be slightly better method for direct aircraft to CAM evaluation. So this is only, the first year of this project. We're really motivated to continue on addressing, more digging into the microphysics, what's driving this transition between the two clouds. How can we use the model in conjunction with the aircraft observations to better understand these types of clouds? One thing that we haven't been able to address is sort of, if I go back to this diagram, somewhere in between the microphysics and the cloud base state is sort of the cloud macrophysics. So the cloud fraction, cloud optical depth, are the cloud fields being represented well by CESM So we'd like to use satellite data, COSP output, to evaluate how well the model can produce the actual cloud states compared to what was actually present during those flights. And then ultimately expand this process system database to different cloud regimes, different parts of the world. There's been a lot of recent Arctic mixed phase cloud field campaigns, CSER specifically, which was in 2024. So looking at that, expanding this would be of definitely something that could be useful. So I'll stop there. Thank you. And I can take questions.
Questions for Ryan. And if you're online, feel free to raise your hand or put your question in the chat. I guess I'm wondering about the nudging of T and whether you think that's helping us a lot with the model, or do you think if we, I guess have you looked into that?
I don't think we've done any. I think it's worth looking into. We haven't done any simulations without nudging T, so I think nudging just UV would be useful because I'm not showing this in my model base state, but I've looked at how well the model, when T is nudged, it's pretty much smack right on in agreement with the dropson and Air5. So it's really well represented. These models, obviously, these simulations aren't nudging Q, so that's why there's some disagreement with relative humidity. I think it is a worthwhile test. I think ultimately we want to see how far down we can go and how little nudging we can do to get the best result. See how well the model is actually doing. Yeah.
Any other questions?
You're I don't have a great question.
Oh, well, I'm just curious, what's the plans, and maybe you haven't thought about it, what's the plans when it's not tolerable, or, because there was kind of that workflow when you go on the right, but there was all that left stuff, I guess, what's the...
That's ongoing very much. What is tolerable, I think, is a huge question. And it's something that we're probably going to have to decide as we go. It might be something that's fluid. We at one point think this was tolerable. We find out that it's no longer tolerable and we have to make it more strict or less strict. That's a great question, and it's very much under work.
Thanks.
Dave?
It was essentially the same question.
Okay. Thank you.
All right, thanks. Okay, our next speaker is a virtual speaker, I believe, Chengyuan Yang, on the use of PPEs in tuning. All right. Can you hear us?
Yes. Can you guys hear me?
Yes, we can hear you.
And you can see the presentation. Okay.
Yeah.
Okay. Hi, everyone. My name is Chengyuan Yang. Thank you for joining this presentation. The title of this presentation is Perturbed Parameter Ensemble-Based Model Calibration in the Presence of Structural Error. So a lot of us may already know that the PPE is a set of parameters and the corresponding climate model simulations. You can think of it as two tables. The X table is all the parameters, and each row is a set of parameters. And we run the climate model with this row of parameters for each of them and collect and post-process the output. The Y table, the second table, is just recording all the variables of interest. It could be global climatologies, regional or temporal climatologies we're curious about. So the PPEs are very important because they can help us understand how the model responds to varying parameter values. The relationship between the parameters and the model output. They're also used for model calibration, which is the main topic of this presentation. We all know that the parameterizations in the climate models are just a simplification of the real physics, and the corresponding parameter values of these parameterizations could have a significant impact on the model output. Here, I'm showing the envelope is one of our PPEs, the minimum and maximum ranges relative to the red line, the observation. It's very spread out. A lot of them are just not very Earth-like. So our goal is to find the parameters such that when we run this parameter with the model, the results would converge towards the observation. So that's the goal of calibration. How do we make use of them? They're not really directly used for calibration. They're used as training data we built emulators, surrogate models, regression models, however you want to call it, that map the parameters to the variables of interest y. And in this way, so we can, instead of just a few hundreds of model simulations, we could sample as many parameter values as we want, put them in the surrogate model, get the equivalent number of y's. Together with observation, we can use them to constrain the parameter values as calibration. However, the following features of a climate model make it very difficult for us to do this exercise. First, we have a few hundreds of simulations, but sometimes we perturb several tens of parameters. So the parameter space is very high. We have very sparse simulations. And also we have lots of targets. Sometimes it's a global climatology, sometimes seasonal, local, and etc. And these are all have to be done in the presence of model structural error. That's something we cannot resolve by varying the parameter values. The figure here is showing the biases of two climatologies from a series of CAM6 runs. They are different by the parameter values. We can see none of the points are actually at the 0, 0. It shows that we can never find a parameter set that leads you to zero biases for these two climatologies. So an example of structural error. So because of these features, we come up with our method. The first is our emulator. The emulator, we choose it to be Gaussian process because it allows for uncertainty quantification. And we build this Gaussian process emulator for each of our target. And the input of this Gaussian process, instead of a whole lot, several tens, we only use 2. And these are the most sensitive parameters for each of the target variables. And these most sensitive parameters are selected based on a simple sensitive test beforehand. The figure on the right is a summary of kind of this sensitivity test. The x-axis are all the climatologies we're curious about that's investigated, regional. And the y-axis are the parameters. For each of the red line, horizontal red line, all the yellow tiles are the target variables, local climatologies that share the same sensitive parameters. And for the vertical line, you could imagine for one observable or one target climatology, it could only have 2 yellow tiles, which are the 2 most sensitive parameters. So we have the surrogate model. And next step is parameter estimation. There is two approaches. The first is Bayesian, the other is called history matching. We didn't use Bayesian because sometimes the Bayesian method could be too automatic, and that could lead to some errors, which we'll show later. So for history matching, it's also kind of like a Bayesian method that you can think of the likelihood as binary. So here is how it's done. Just imagine you have just one variable of interest and one parameter. So you perturb them, you put it in the climate model, you collect them and plot them, you get the green points. And then you build a surrogate model and generate lots of points. And these are the yellow and the blue points, right? For each of these yellow and blue points, we're just plotting its mean. It also has an uncertainty quantification because we're using Gaussian process. So what history matching does is that it keeps these ensemble samples if the observation falls within the 95 or some confidence interval. So if the observation is close enough to the emulated point, we keep them. Otherwise, the blue points you see, we discard them. And in this way, this parameter's range is constrained by this process, right? So it's from 0 to 1 now. It's a little more narrow. And we do this for a lot of these climatologies. Right? So this is the idea of history matching. But when we have more targets, the problem becomes more complicated. So here's an example. Imagine now we have 2 targets we want to match, and for one target variable, the observation is way above all the simulations we have, like Riemann mouses. And in this case, we can have just by eyeballing the parameter for this target variable A is probably in the range defined by this red bracket. But for here, we can't find anything, right? So we cannot find any parameters at all if we consider all this. So a common approach is to say, okay, let's introduce some tolerance on the structural error. What it's done is, so the gray band here is on the left is showing kind of the observational uncertainty. So when we introduce the tolerance of structural error, that's equivalent in a way of increasing the observational uncertainty. So when we make them wide enough, this structural error or equivalently the observational uncertainty, there's a chance that we get some samples from these two climatologies. So this really, really yellow small bracket. But the problem is already appears, that is, this parameter range is so controlled by an observation that is full of structural error. So it's actually dominated by this climatology B that has inherent issues that the model cannot really match. And in some worst case, if we increase the tolerance too much, because sometimes we have so many variables, right? We have to make sure we are able to have samples. So this very, very valuable observation is just not used because the uncertainty is we are too lenient. The tolerance is too much, so the parameter range is not constrained. We're wasting a lot of useful observations. So that's the issues we find. But because of these features, what should we do? Here is our propositions. The first is we should avoid arbitrarily increasing the tolerance, like was done on the right. The second is we always have to report it if we find such structural error. The third one is a little bit counterintuitive. It's just, let's just ignore the structural error when that happens. And you may wonder why. I hope this convinces you. That's because our simulation result is always smooth. So we could have one area of interest that has some climatology that has strong structural error, like the one on the left here. But the neighboring locations, there might be less severe structural error, but they're similar. So in this case, on the left, there's structural error. But you also see if we make this parameter a little bit smaller, there's a chance that our simulation result is closer to this observation. If we totally ignore it because it's neighboring climatologies, spatially neighboring climatologies, they're correlated because they're close by. You just focus on this climatology, that gives you similar information, which is that this parameter should be smaller. So this is kind of a summary of our method. It will be made public on GitHub soon. I highlighted here this red box just to show it detects structural error and report and summarize it for you. So now it's time to test our method. We use CAM6 with machine learning based macrophysics parameterization as a test bed. We don't know how the physics is changed. So we run uncoupled simulation for 1 year. We sample 100 parameter value combinations with 34 parameters perturbed. We run them, collect output, and our target is 10-degree zonal averages of the 6 climatologies listed here. Now you can see the original envelope is very wide. We apply our method, we have some parameters, and then we run the climate model with the parameters. And the result is presented in the dark blue. You see, it's still not good, but it's narrowed towards the observation. And then we have this new data set from this kind of our method. Then we apply our method to this new data set to further constrain the parameters. And then you see the light blue envelope. So it's further squeezed towards the kind of the observation. And from this set of simulations, we're able to find some ensemble members whose metrics are really comparable or even better than the CAM6 default run, depending on what metric you're using. But we are able to find comparable parameters from, in this case, 300 runs because we apply our method twice and we have the original data set. So then we're very happy with this uncoupled simulation. We want to test it with the coupled simulation. We want to see if we're able to help with CAM7. So we do the same thing. We find 2 parameters that we're very proud of, very happy about. we run it with the coupled simulation. And unfortunately, there is some improvement and there is some degradation, but the rest time is a little more biased than it should be. So the main reason for that is because of the differences between the uncoupled and uncoupled runs. So there is something that we never know, but there is something that I should have known. So that's one missing gap. For example, I should tune the rest time with a certain bias. This is one of the reasons that our parameters are not good. Also, this plot is showing the blue points are the kind of the global biases of our constraint, our selected parameters, right? We will only select 2, but we have an ensemble. And the red point is the kind of the default run at the time of this analysis. You can see the differences happens in the strategy. That is, the reference point just care very little about the long wave cloud forcing, but it's focusing more on balancing the OLR and the net short wave. But for our cloud of points, you can see what happens is kind of it is a little bit of improvement, but it's a little bit improvement for short wave. It's a little improvement for others. So this is not making full use of the knowledge on the difference between the coupled and uncoupled runs. And now it's time. So let's compare the parameters with this reference run, right? So it's interesting that these 6 parameters that are always important, they're very consistent with the default run. So we didn't do it. We did some subjective choice about structural error, but it's pretty automatic, especially for DCS. The DCS is very sensitive, but in all of our experiments, it's very easy to constrain. But there is this one parameter which always couples with DCS. It's a scaling factor that computes the falling eye speed. It's a lot bigger than the default run. So our method, thankfully, is able to trace back why. And this, where my mouse is just showing that it's able to detect what went wrong. And it turns out it's this a water vapor quantity that's leading our method to think, oh, this parameter should be a lot bigger. So in this case, maybe our tolerance of the structural errors should be even, we should be more strict, less tolerant of the structural error as shown in here. So a lot of the differences is not actually from the method, it's from how we prioritize these variables, or if we consider some improvement is important or not. So here I just want to have a summary, and I just want to stress the lesson we learned is maybe in between the hand tuning and completely automatic tuning, maybe we can also have some informed tuning where we can make use of the kind of the inferences or the insights from such data analysis and make a decision on what to prioritize to improve. Also, I just want to thank everyone in the AMWG working group, especially Adam, for all of my questions, and thank you for all your help. Thanks.
Thank you. Any questions for Yan? Yes.
Hi, Yuan. Very nice talk. I want to ask you, like, when you calibrate, do you thought about the equifinality problem of the model, where model can get the same sort of result for different combination of parameter? So how do you think about equifinality in calibration?
Yeah, I think that's a really good question. So there's kind of 2 kinds, in my opinion. One is they're kind of around Gaussian, kind of where like just one mode or 2 modes. Within one mode, you could also have several kind of multi-finality problem. If it's just one mode, you could just sample from it. And for 2 mode, we sometimes run into such problems, but it's very rare because imagine if you have 2 modes, that means your parameter and climatology relationship is could be a little bit nonlinear, right? But in that case, it actually rarely happens because we know that the nonlinearity exists, but even just 100 data each time, that rarely occurs. But that occurs rarely, and if it happens, I make a subjective call. Thanks.
Any other questions? Yep. Andy?
Yeah, thanks for the talk. I'm curious, when you did your sampling, was the sampling of every parameter? I think you had like 34 independent, and if certain parameters are conditional on other parameters or related to them, is there a way that you can do your sampling to represent that conditionality and maybe reduce your parameter space a little bit in that?
You sort of see it after you do the sampling. So what I'm showing here, you can see it seems like they're all independent, but a lot of the times they're correlated. And that is the benefit of focusing on multiple targets, because maybe for a small area like the warm pool, there's a certain parameters that you can easily tune. But if you focus on just the global climatologies, it will become very not important. So you kind of ignore it, if that answers your question. Yeah.
Thanks.
Thanks.
I was wondering if you could see any ways of incorporating the process system database that Ryan presented into this kind of method, maybe kind of more constrained situations with in situ observations.
Yeah, I think it's very interesting, definitely interesting, but kind of we have to know where the structural error is likely to happen for our model, and if we have to find the places where it gives you reasonable results. So I think it's a kind of like to connect the pipeline, it takes some expert judgment and all, if that makes, because of the scaling problem, time scale. Yeah. Thanks.
Alrighty. Thanks. Guess we'll move on to the next speaker. Thank you. Next speaker is Dave Lawrence about the plans for the machine learning enabled CDSM.
So this is going to be repeat material for many of you. But the fundamental problem is we've seen already over this last few days that there's many biases that are still existing in the model that have been persistent over decades, really. And I heard an example this morning about ENSO position at the westward extent. On. Yeah, green light now. Okay, yeah. So we've heard about some biases that have, we know about some biases that have existed for a long time and heard about them this meeting, heard about the WAWG still around, the position of ENSO and the SSTs too far west and things like that. And so we want to see if we can break out of this mold, right? Models are getting better. They're getting better slower than we would like. And so can we get out of this mold? And the idea here is that maybe we can use some of the advantages of machine learning to build either better parameterizations that are taking advantage of information that we can't define in our relatively simplified parameterizations, and or do calibration in a more interesting or impactful way, to like the stuff that Young just talked about. So this is the overall vision that lots of people are talking about, and we wrote about in this paper with Veronica Eyring led. That we have lots of information from, say, kilometer scale models or LES or even DNS, direct numerical simulation, and there's a huge amount of Earth observations, and we're not utilizing that information as much as we could. And so the question is can we take that information and use that to better define parameterizations or to do calibration to build a hybrid model with combining physics and machine learning? Still maybe the standard resolution as we're running now, or maybe going to slightly higher resolution. And then, the overall framework then says, you would have these still be able to run large ensembles, because it's not, it's computationally expensive as a kilometer scale model, which is really infeasible to run, century scale or even decadal scale simulations, do downscaling or regional refinement, and then can drive impact models. So there's kind of an overarching framework here that allows us to hopefully make a step change in the quality of the science and that we're doing. Just want to make a point here really briefly that people always want to ask about emulators in this space. How much can emulators help? And emulators are, I think, going to be really key components of this overall picture. We didn't put it in this paper. We should have. But credit here to develop the NCARs that work on emulators and other groups around the world. And I think the idea that we have is that as we start building these hybrid ESMs, especially going to like a high resolution core to read version, we could then use an emulator to really explode out the parameter space and to do further explorations if you've had a couple of really key simulations. But especially if you're dealing with the problem of climate change, having better and better emulators, you're going to essentially run out of room to get any better because you're really relying on the climate model forecasts. And so I think we still need to make the climate models better. And that's where this, this hybrid modeling comes in. And we also want to have the ability to do exploration, and the emulators may or may not allow you to do, scientific exploration in the same way that a more physically based model has. Okay, so now I want to talk about our efforts so far on this space here, the hybrid models. So we have two big projects that have been supporting this work, LEAP, Learning the Earth with Artificial Intelligence and Physics, and the M-squared lines activities supported by Schmidt Sciences. And so both these projects started about the same time and are both trying to do the same thing, which is bring in new machine learning algorithms, combining them with high fidelity models and observations to create either new machine learning based parameterizations where it seems like it's fruitful to do that, or to do ML enabled parameter optimization and then build the next generation, in our case, CSM. So I'm going to talk first about the ML enabled parameter optimization, which we've made quite a bit of progress on, and you heard some about just now. So on the left is work we've done in CLM to do parameter estimation using a similar history matching type approach that Yang was talking about. The idea, you generate a perturbed parameter ensemble, you train your emulator on that ensemble to really fill the parameter space, and then confront the model with observational data with all the additional caveats that we heard about previously about considering about observational uncertainty and then potentially structural uncertainty. You constrain the posterior parameter space and you can do iterative refocusing. So you zoom in on the parameter space where you're finding the most relevance for you in terms of your parameters. And so in CLM, it's actually been quite successful now. We've been able to calibrate in land-only mode quite well to even some relatively hard variables like the leaf area index, which is a really important integrating variable in the land model, which controls fluxes of water, carbon, and energy. And so on the upper right there, this is a little bit old figure now, but going from mean absolute error and leaf area index bias from 1.36 down to about 0.6, so cut it in half. So it's a really good evidence that you can do this. So we can now constrain to multiple observational targets and get a pretty good simulation in land-only mode, and we've been using this then in CSM3. So it's actually gone all the way into CSM3 for this cycle, and so we're excited to see how it works. If we run our CMAP7 simulations. And if you compare to this is the ILAM backward results, these kind of similar kind of diagrams we've seen before this morning in terms of comparing model results against each other. So the default where it's red means the model is performing worse, and the green is performing better. So in the calibrated model, we've been able to improve a bunch of, in fact, most of the carbon cycle diagnostics. And we didn't really try to focus on the hydrology, which is why the hydrology didn't get better. And part of that was because the observational data sets for hydrology are not tight enough to really provide good constraints. There's such observational uncertainty across the multiple data sets that exist that we don't have much constraint at the global level. So it's something to be tackled in the future. But anyway, this is showing good success. So it looks like we can go, and we have a ton of science going on around this sort of activity. In terms of CAM, we've gone from this sort of interesting position where, before I think we were developing CAM6 and even really CAM7, there was no automated tuning capabilities. The only thing we could do was hand tuning. So expert judgment and hand tuning, and the big brains of Cecile and Adam and others in the team were what we're doing. But now we have multiple approaches. So we heard from Yang about this history matching approach, Gaussian process emulators. But there's also an approach called contrastive learning framework, which don't ask me to explain because I don't really understand it, by Dafan and DJ Gagne here at NCAR, taking advantage of the latent space. I should be able to understand this, but I feel like I'm aging out of the ability here to keep up with everything. But and then we also have this thing called quad tune, which is maybe not strictly machine learning based activity, but still in the space of doing automated calibration. And Vince Larson and his group have made pretty good work here. And in fact, we've actually been testing out all three of these methods with CAM7 development. Probably none of them are going to actually be the primary set we use, but we're definitely learning a lot about the process along the way. So one thing I'm doing is trying to get these teams together to try to compare notes and understand what advantage do you have from different methods? What can we advance in all the methods? Is there one method that's really superior in certain situations, et cetera, et cetera. But the aim with both of these things the CLM and the CAM calibration is to build these automated tools that allows not just us here at NCAR, but any user to come in and do a calibration on their own for their own problem. That's the ultimate goal. We're a ways away from that, but I think we're moving towards it. Okay, and then moving on to the parameterizations, the machine learning based parameterizations, we've been doing a lot of work on this. And the first activity is a project that started many years ago. You've all heard about it many times, that Andrew Getteman worked on, working on machine learning based parameterization for warm rain microphysics. And the idea here is you can emulate cloud droplet autoconversion and accretion with neural networks trained on CAM simulations where the warm rain process is replaced with the highly resolved bin microphysics. So basically taking this very expensive so-called TAO code, putting it into CAM, running a simulation and getting a better simulation, but it's extremely expensive to run that, so we can't do it all the time. So then you can take that simulation and learn from it and build a machine learning based parameterization, which is much, much cheaper. And so the default parameterization is the KK2000 and blue, and the orange is the machine learning based warm rain parameterization. And this is showing the precipitation frequency PDF. And so we've always, in large scale models, tend to not be able to reproduce the high frequency, the high precipitation amounts, and the overproduce the low precipitation amounts at these low resolution simulations. And so this is the issue. And what we see, here's the KK2000, you're saying not getting these really high values in the CMORPH data set, and this also shows up in the iMerge data set. It looks like it's a little bit better, or significantly better, with the machine learning based warm rain parameterization. So that's good news. We're getting better precipitation frequency distribution, important for exchange, et cetera, without necessarily going to like ultra high resolution simulations. So, possible improved tail behavior using the more parameterization. But the challenge is that as you introduce this new parameterization, the model looks different. And hopefully, if the parameterization is substantially different to the original parameterization, the climate might look very different. In some cases, we're hoping it looks very different because we're hoping that we make a step change in the quality of simulation. So we see this improvement in the tail of distribution, and this is just hypothetical. It might give you a significant new biases in your overall AMEP type simulation. So greater performance. And so this is really why we're doing this hand in hand, is building this automated calibration methodology alongside building these machine learning based parameterizations, so that you can then potentially quickly recalibrate rather than relying on just a few people who know how to recalibrate, which is really not sustainable. So that's the idea here. And then the question really is, can you either get back to the quality of your original simulation, hopefully get to something better, but also retain like the new feature you have here, the improved precipitation frequency distribution as you move to that new calibrated version. And so as it's the process of trying to develop the workflow to do this sort of recalibration after you've introduced a new parameterization, we've been working on this workflow to say we're going to try to calibrate both in the original parameterization, the original KK2000 parameterization for machine learning based warm rain microphysics, and then also again with this machine learning based parameterization. And this just shows a set of 10 ensemble members, and each one of those ensemble members is showing some indication that you're getting an improvement in the precipitation frequency PDF, indicating that most likely when you calibrate, it'll be retained. And in fact, that's exactly what Adisu has done now. He has done the full calibration, targeting specifically to get as good as he could for this precipitation frequency PDF, and shows that in the purple there with this new machine learning based parameterization optimized, we're almost matching perfectly the precipitation frequency distribution from the observations. And even after optimization, the original version can't get to that level. So it's indicating that there's something in the physics of this new machine learning based parameterization that is allowing you to get these high rain rates. Now, the caveat here is that he didn't really try to also maintain good climatological fields. So this result should be taken with a little bit of a grain of salt, but it is sort of promising. Okay, so we're kind of getting methods in place. We have a few machine learning based parameterizations. We have a calibration methodology. Can we now move towards a coupled model version, CSM3 with machine learning enhanced? So what do we need to do? So one thing we're realizing is that there's quite a few activities out there trying to build machine learning-based parameterizations within the LEAP and M-squared lines and other activities. A lot of times there was like a scientist who was working on a project, building, training something, an emulator, neural network or something, and then coming to the like CAM or CLM development team and saying they have this product and they're ready to go, and then it turns out that there was a mismatch between the inputs or the outputs that the model needed, and it wasn't actually suitable necessarily to go into the model. So we have now developed, put together an integration team supported by M-squared lines and LEAP. And we have a few people here, Javier here, Adisu's in the room, Linnea is here in the building. And they're the ones who are trying to connect between the LEAP and the M-squared line researchers and the CSM developers. And so it's really proven, I think, be a pretty effective way to move on this. And one of the things they've done is to help make sure that we have some of these tools and infrastructure in place that we need to make this work. So we have a bridge now implemented into all of CSM with any component model where you can couple Python through FTorch into Fortran. And so that's really important if you want to use all the technology you have in Python to do machine learning-based learning and neural networks and all the things you can do there. And so Javier here has been playing with this and working with this implementation for his deep convection integration that he's going to talk about later this week, tomorrow. We've also have some documentation there to help other users figure out how to do this and other tools and support. So we're really trying to build this into a community resource so that anyone who has an idea about a machine learning-based parameterization they'd like to test out, it shouldn't be too hard for them to try to pull it in. So what are we doing for CSM3 MLE? If this is another figure from Veronica's paper, there's a lot of opportunities where you think you might be able to use machine learning to improve our parameterizations. And here's some that we're sort of actively working on across the CSM activity. So you'll see that they're spread around land, the atmosphere I've already mentioned, but there's also significant activities on the ocean model, on the sea ice. Each one of these is in sort of different levels of development. Most of them are moving along pretty well, but there's big issues that come up in every one of these as you try to really move it all the way into the model. But we have 2 to 3 that we think are far enough along that it's worth considering to put together. And our first real combined AMIP simulation that we might be able to sort of start seeing some significant improvements. And that is warm rain microphysics that I've been talking about, convection parameterization that Javier has been working on, and then potentially a plant phenology parameterization, along with the calibration of automated calibration of CAM and CLM, or quasi-automated calibration of CAM and CLM. And so Javier will be talking tomorrow. We just heard from Yang. Linnea will be talking at the Land Model Working Group, and actually there's also a talk in the Polar Climate Working Group by Jia Zhang at Mojo for some cool work she's doing with the ice flow parameters. So we're making progress. So the goal, one of my goals, is to try to get our first AMIP configuration with like this set of parameterizations done by the CMIP meeting in March. That's probably a bit ambitious, but I like to set ambitious targets, as you probably all know. Spend most of my life doing that and then missing them. Okay, so here it is. So to summarize, I think after we finish this CSM3 push, we can really move forward to test this hypothesis that machine learning can help us build better and more accurate ESMs. And it's going to require sustained team interactions, more coordination, communication. And to that end, we're having a hybrid model implementation workshop jointly with the ICON group, Veronica Eyring's group, which is kind of, I think, along with CSM, maybe as far along as our other groups are in terms of trying to do this hybrid modeling. We have to be careful how we define success. We don't need to have every single parameterization in the model switched out. If we have just a couple of parameterizations in each component, or even just one, I would call that success for CSM3 MLE and also the automatic calibration. We know there's going to be a lot of challenges, right? It's what is the reliability in out of training climates? The potential for model instabilities, we're almost expecting that. Unanticipated interdependencies of the new parameterization, substantially simulated new climate may degrade orthogonal simulation aspects that we can't correct, and new tuning challenges may occur if some of our historically used tuning knobs are gone now with a new machine learning-based parameterization. But these are challenges that we have to try to overcome, and if you don't just try, you're not really going to be able to figure out, where the real stumbling blocks are. And then the last point I want to make here is that, a fundamental challenge that we're all experiencing, we've definitely experienced over the last year and a half of the CSM development team, is that it is really hard to build a coupled model. We've tried things over the years to make it faster, and we really have not been able to make it faster. It's basically taking us a 2-year cycle this time, just like it did last time, 300 plus simulations to get to a coupled model. And so we really need to find ways to make this faster. And so I'd like to try to take advantage of this opportunity where we have a relatively constrained set of new things. Can we build a coupled model faster than we did for CSM3? We better be able to, otherwise this project won't work. And we're going to hopefully take advantage of a call from Schmidt Sciences that's coming out soon on coupled model calibration and use this as our target. And we already have a lot of ideas of things to test. And we can do it in a bit more systematic way, I think, without that pressure of trying to have a model ready for CMIP. If we get a CSM3 MLE for CMIP 7, that's great. If we don't, that's great as well. And we have a bunch of ideas here. I'm just listed a few. I'm not going to read through them, and we'll generate a bunch more as we go through. But we can be more systematic and honest about what we're doing in that. So I'll stop there. Thanks.
Questions for Dave? Yeah, Raphael.
In the last figure you showed, I didn't see the atmospheric chemistry. Are there enough observations to think of implementing these machine learning emulators also for the chemistry?
You know better than me, probably, so I could turn that back to you. But I think that we actually, some of my slides I include atmospheric chemistry because some groups are working on this. And I think the main idea with chemistry is that it would be a speed performance improvement. So you could run a high fidelity, maybe quarter degree simulation, or even our 1 degree simulation with all the full chemistry you want, and then learn it, and then replace that and be much, much faster, I think, than our current version. So that's, I think, what I've been hearing groups saying that's the most promising near-term path for chemistry. But I'm happy to take suggestions. Or we are.
I would just add the same thing for aerosols, right? I think that's an area that kind of underscore, but the speed of like having more accurate aerosol parameterization while having a machine learning aid, that could be another frontier.
Yeah, I think we're not focusing on speed as much as we could, I think, because I want to see if we can build something better first. But there's definitely opportunities to make the model faster, and that's almost just as important, right? If we make the model faster, we can do many more things, run high resolution, et cetera, et cetera.
Yeah, thank you so much. I'm going to sort of ask the obvious, but I mean, we've seen right in the first talk that there's structural model error, and it's hard to fix everything with optimal parameter settings. And then we saw an example that, the PDF of heavy precipitation is improved, but the rest of the climatology is deteriorated. So I think we all know that if you change something, we need to retune the whole model, right? And so how do you see this in the future, especially when we have hybrid modeling, right? If we put a hybrid model in and many things get better and a lot of other things get worse, we would need to have a PP and retune it all for this new one. Where do you see the low-hanging fruit there, or maybe a first process?
Well, yeah, I think we're in a position now, we at least have these automated calibration methodologies that exist, right, within the CSM framework. And so before that, we didn't have it at all. So it was like totally almost like a non-starter. Now we have the potential. And so we're going to, I think through this process, learn whether or not we can recalibrate and achieve the same level of performance or improve. So to bid, I would just say we have to experiment and see whether or not we can do it. But there still will be structural errors. You're right. So we're going to have to make decisions on how we deal with the structural errors. And Yang is making a suggestion. I expect there's other suggestions about this as well. So it's going to be hard, right? And we just can't let it. It doesn't have to be perfect. We just have to do the best we can. But the hope is that there'll be fewer structural errors because we've made significant improvements to enough parameterizations that some of those structural errors will go away. The second thing I'll just say really quick is that I think we're going to have to start thinking about calibration in some sort of more hierarchical way, on those right ways, we call it calibration cascade on the land side, is maybe stepping up through the timescales, like work on the fast processes first, then work on the next. But that's like thing we have never tried to do yet. We haven't tried to do it yet. It'd be fun to try and see if that might get us more luck than trying to go for everything all at once. So.
All right, thank you. Okay, our next speaker is Kirsten Meyer on extending Camulator to subseasonal prediction.
In my back pocket. Be very careful this time. Okay, can you all still hear me? Okay, great. Hi, everyone. Okay, so I'm going to talk about a lot of planned work. This is all very preliminary, and I have a few results that we have for real-time prediction, as well as some hindcast predictions that we've done. Okay, so broadly, I'm going to define subseasonal timescales here as 2 weeks to 2 months. And if you're familiar with this time frame, you know that there's this general hypothesis that given its place between weather and seasonal timescales, that we can get a lot of predictability from a variety of different sources. So that can be from the atmosphere, from the land, and from the ocean. So when we want to think about a machine learning emulator for subseasonal prediction, we want an emulator, hypothetically, to include all of these components coupled. And fortunately, here at NCAR, we already have a machine learning emulator of the community atmosphere model, or CAM. This is known as Camulator. I have a little promotional video. Oh, it's not going to let me skip verification. No. Okay, whatever. We'll pass. It looks really cool, I swear. Okay, so this is a video of the lowest model level, and if you're really curious about it, I can send it to you. But basically, Camulator looks very physically realistic, and I'll show some stats after this slide. But if you're curious in learning about Camulator itself, there is an archive paper already out. This was led by Will Chapman, and I highly recommend it. So just a general overview of Camulator. So it leads to about a 350 times speed up over CAM6. It inputs atmospheric variables and a variety of forcing variables, including dynamic variables and static variables. It's trained on an AMIP style simulation from 1979 to 2014 using CAM6. It's on order of 1,000 lines of code. It has many, many parameters, but in comparison to like ChatGPT, it's only about 0.4% of how many parameters that uses. And if you wanted to download it yourself, it's only 3 gigabytes. So this is based on a transformer unit-like architecture. So we input these atmospheric variables and forcing variables. It's passed through this machine learning model. We apply some physics conservations, and then we ultimately get some output. In terms of the actual variables that are input into Camulator, we have U, V, T, and Q at 32 hybrid sigma pressure levels. We also input surface pressure and 2-meter temperature. These are input and output by the machine learning model at a 6-hourly time step. We also have dynamic forcing variables that are only input into our model. This includes incoming solar radiation and sea surface temperature. And then in terms of our static forcing variables, these are 2 variables to describe topography as well as our land sea mask. So once you pass this through Camulator, you get our U, V, T, and Q back, as well as our surface pressure and near surface air temperature. And then we get a variety of diagnostic variables that are output, including precipitation, some cloud cover fraction, wind stress, and a variety of fluxes that are output by Camulator. So Will wanted to see whether we could run out Camulator for very long time scales stably. And so this plot here is actually demonstrating more than a 200-year run of Camulator using climatological SSTs from 2000. And he did find that we generally have a stable, unchanging climate when you force camulator with sea surface temperatures. Possibly a little more interesting to all of us is actually if we force camulator with observed SSTs. What we have here is CAM in purple and a bunch of ensemble members from camulator in teal. And what you can see is that the ensemble members generally cover the CAM simulation when we force with observed sea surface temperatures, which is what we would hope to expect when we're trying to emulate CAM rather than observations, just to be clear. So that's just a general overview of camulator. What I was particularly interested when I first saw this work from Will is its response to larger modes of variability. And so, as I mentioned, camulator is actually rolled out at a 6-hourly time step, but it's still able to get larger scale modes of variability. So here's an example of the ENSO precipitation response to these sea surface temperatures. So we have CAM 6 on the left during boreal winter and camulator on the right. And what you can generally see by eye is that these look relatively similar across the globe. And if you don't believe me, the pattern correlation is approximately 0.9. Going further, we can also look at different modes of variability, such as PNA and NAO. And that's what you see at the top and bottom. The top is camulator, the bottom is CAM 6. And again, just by eye here, it's generally getting these modes of variability. An interesting fact is Z500 is not actually output by camulator. And so it suggests that when he calculates the Z500 field, the machine learning model seems to be able to get between level information pretty well. Okay, so I've been talking about camulator version 1, which was trained on this AMIP style simulation. Since then, we have camulator version 2, and it's now available on the Credit GitHub. I'll have a link to all of that at the end of this slide. It was briefly introduced by Dave. But the update to camulator is mainly that the training data got pushed down below into white. But the training data is now trained, it's now trained on a coupled simulation. So now we have interactive SSTs. But camulator is still forced with SSTs. It's not actually interacting, having input and output SSTs. So that's still a forcing variable within camulator version 2. He's also included CO2 and ice fraction as an input into camulator version 2. So from this, this is where our subseasonal timescales come into play. This is currently a work in progress. And we're referring to it as sub-CES emulator. This is basically a play on camulator, but now we want to include a coupled ocean and land. At the moment, what this looks like for us is just adding in a couple new variables as prognostic variables. So we have all of the same atmospheric variables in camulator, but now we've included sea surface temperature, soil moisture at 10 centimeters, and surface temperature. This is trained on these coupled simulations that Will ran for camulator version 2, training on 1980 to 2024, validating on 2025 to 2030. Something here is that when we initially trained sub-CES emulator, we were using a slightly different architecture and the upsampling portion of the machine learning model. And so we ended up getting these gridding artifacts on the output of sub-CES emulator that also show up in camulator version 1. These have since been fixed in camulator version 2, but we're in the process of retraining sub-CES emulator. So the results that I'm going to show later are going to be focused mainly on camulator version 2. Okay, so I've mentioned that we are training on the CSM2 coupled runs. Something that I'm particularly interested in is actually taking sub-CES emulator a slightly different way and training it on data that's already available through the CSM2 large ensemble. And if you're familiar with subseasonal timescales, you'll understand that our observational record isn't that long when we start to try to understand the modes of variability associated with subseasonal predictability, especially if you try to start compositing by El Nino, MJO phases 5 and 6, QBO easterly. Once you start doing all these things, our observational record isn't very long. So the hope here is that I can take this data that we've generated with the CSM2 large ensemble and take a portion of that from each ensemble member that looks very similar to today's climate. So right now I'm thinking 1990 to 2025, and then explore a variety of members as our training data. So that would end up with about, if we did 5 members, 175 years of data. Our limit here would actually be how long it takes to train the machine learning model rather than the amount of data we have to train it. And typical S2S ML models train on our satellite era, so 1979 to 2025. And they can only use a portion of that just given the fact that we also need our validation and testing data for machine learning. And so in total, that's 46 years of data. So using the CSM2 large ensemble approach is, I think, a promising way forward. And I'm in the process of getting all that data into a data loader to actually train this machine learning model. And then ultimately add more land and ocean variables. This is going to be our first test run to see, and I'm happy to take suggestions on what you would all like in this model. Okay, so here's the 3 in process or already done emulators. And like I mentioned before, I'm currently retraining Sub-CS emulators, so we're going to focus on the workflow and some results that we've come through with Camulator version 2. And in the process of creating the Sub-CS emulator, I got an email from Judith who said we should probably participate in the AI Weather Quest, which is a forecasting competition on subseasonal timescales specifically for machine learning models. And I thought that was a fantastic idea. And in my head, I thought it was fantastic because I think it leads to a very interesting scientific question is, can we actually use a model trained on CESM to make real-time forecasts? And so that's what I was mainly interested in. Not necessarily getting the best performing model. However, we didn't submit Sub-CS emulator. We've ended up submitting Camulator with the hopes of ultimately switching to that. So like I mentioned, this is an international competition hosted by ECMWF. As participants, we have to provide weekly global forecasts at a 1.5 degree resolution of quintile probabilities for weekly means of days 19 to 25 and days 26 to 32. I'm just going to call this week 3 and week 4 for simplicity. And the 3 variables we're supposed to provide are temperature, precipitation, and sea level pressure. And then we are evaluated against ERA 5 using a ranked probability skill score. Again, if we wanted to do the best performing model, we'd probably train a machine learning model on ERA 5, given we're being evaluated against it. But here we're going to focus on training with CESM. So in terms of initializing our model, we grab the 31 initial condition members output by GEFS, and then we perturb each of these 31 members 11 times using the perturbation method that's defined in the CSM S2S hindcast. And that leads to 341 members that we ultimately submit to this competition. In terms of dynamical forcing, we have SST and ice fraction as input into this machine learning model. In order to deal with that, since we don't know the future of SST and ice fraction, we end up persisting their initial conditions currently. This probably isn't the best way, but it's what we've been able to do so far. And then lastly, we need to define quintiles for this model. They provide ERA 5 quintiles, but just because we're training on CESM, we decided to define the quintiles based on the CESM data to hopefully account for any shifts in data. Overall, this takes about 7 hours to submit the entire forecast. And I wanted to provide an example forecast for week 3-4. This is actually a forecast for this week. These are all of the quintiles, and shading here is the percentage of ensemble members that fall in that grid cell for that specific quintile. So basically, if you see dark purple, all of the members decided that it should be in that, or have forecasted that it's in that quintile. And what you may be noticing is that our less than 20th quintile and our greater than 80th quintile seem to have a lot of members that all agree that it's going to be either extremely cold or extremely warm. And we're still unclear why this is the case, and it's happening in a lot of our forecasts. Why it's not focusing on the center. It's actually a very strange problem for machine learning models. Usually it's the opposite. So we're still exploring that, and it could be related to our ensemble generation method. But again, not sure. Okay, so here's our week 3 skill from the AI Weather Quest. This is for DJF. It's our period aggregated RPSS. The blue, teal, green colors and gray colors are the top performing AI models that are submitted to the AI Weather Quest. And then I've also included 2 orange lines here. One's ECMWF and one's the dynamical model. And then the other is the multi-model mean from the S2S database. And then way at the bottom there is purple, and that is our submission to the AI Weather Quest. if you're not familiar with RPSS, 0 means that you're performing at climatological skill. If you're below 0, that means you're worse than climatology. So we are indeed worse than climatology in terms of our performance. We're not the worst model, however. If we're looking at all variables, we're 28th out of 36 models, 2-meter temperature, 38th out of 40, mean sea level pressure, 34th out of 38, and precipitation, we're 33rd out of 40. So take it with it what you will. Here's week 4. Again, all of those top models clustered are the dynamical and the top performing AI models. And then again, at the bottom here in dark blue now is our machine learning model that we're submitting. And we're about the same ranks in terms of models that have been submitted to the AI Weather Quest. So in terms of next steps, we'd like to move from Camulator to subCES emulator. I have a feeling that might improve our 2-meter temperature forecast, given we won't be persisting sea surface temperature. I'm also interested in switching to the stochastic decomposition layers for our ensemble generation method. This is a method created by John Schreck, and it was just published on Archive, I believe. And it's been shown to have good spread skill ratios through the medium range timescales when you fine tune the model to have these layers. And so I'm hoping that this would also extend to subseasonal timescales. So switch to using that method instead. And then right now we're only looking at the quintile forecast, and I'm also interested in exploring some non-quintile statistics, and maybe that will provide some directions in which we can go for areas of improvement. Well, now that we have that whole thing in order and we're submitting automatically, I could turn my focus to the machine learning S2S hindcast that I would really like to generate. Again, since subCES emulator is currently training, I've been creating this pipeline for Camulator version 2. But the ultimate goal is to create 2 machine learning S2S hindcasts, one for Camulator, one for subCES emulator. I'm using the same initial conditions that we used to create the CESM S2S hindcast, as well as the same ensemble generation technique, but I would like to explore other ensemble generation approaches, like I've already mentioned, as well as create more than 10 ensemble members, as we're not as limited in terms of computation. I'm also interested in running additional initialization dates. We currently only do weekly. I'm hoping to change that to daily and possibly extend the initializations all the way to 2025. I believe we've currently stopped in 2023. And then also apply a bunch of diagnostics and explore how good they perform. And then lastly, make it available to the community so you all can interrogate it and suggest improvements for me. We're about 2 weeks too early for me to have all of the hindcasts run, but I was able to run just one initialization from January 3rd, 2000. This is the 2-meter temperature forecast for Boulder. Camulator is in teal. The CESM S2S hindcast is in this purplish color, and ERA 5 is in the gray color. And again, we're training on CESM, so we would expect Camulator to follow CESM rather than ERA 5 in this case. And so you can see that I'm quite happy with this random initialization day with how this is looking, but I can't make any extrapolation as to how we will ultimately perform in terms of S2S timescales with Camulator. So just in general, coming soon is Camulator hindcast and subCES emulator hindcast, as well as a different way to train subCES emulator using the CSM2 large ensemble output. So we'll have a lot more training data, and hopefully this will also improve our model. And then I didn't have time here to talk about it, but also do some awesome science with these emulators. Lastly, I did want to mention that this wouldn't have been possible without credit in terms of scaling my training to our HPCs, and then also creating this entire architecture for subCES emulator. So if you have any additional questions, I would direct you to this team or this website, but I'm also happy to address questions to the best of my knowledge for that. And with that, I'd be happy to take any questions if we have time.
Questions? Yeah. Hi, nice talk. So it's very nice that your model is stable in the long run. I just want to know, have you checked that how Camulator works when predicting climate state outside the training? For example, El Nino, La Nina events.
Yeah, so in terms of Camulator version 1, Will has actually explored, he's the first author of the Camulator paper. He actually explored forcing the model with SSTs that were added 2 Kelvin and 4 Kelvin, and generally found that the machine learning model was okay at 2 Kelvin, but was too cool at 4 Kelvin. So it does okay when it's dealing with out of sample forcing, but that's all I know in terms of its sensitivity so far.
With S2S, you have the opportunity to have a model with data assimilation capability, presumably. Is that correct? Have any of these models got data assimilation? No.
No.
Oh, really?
Really?
But isn't that a bad idea? You need to have some truthfulness. Or near it.
Well, in my case, truth is CESM. So I'm training on CESM data and I'm trying to mimic it as best as possible.
Yes, but that's not reality.
That is not reality, that's correct. But we have a lot more data.
Why not have some reality?
Well, you're initializing with.
We're initializing, for the hindcast, we're initializing with true values. So I think true in terms of.
But not the forecast.
The forecast is rolled out using the machine learning emulator. So it has no data.
But you could have some. ECNWF, for example, has enormous data assimilation capability. So couldn't that not be the truth, so to speak?
It's very expensive to do data.
But so what?
Are you asking?
Yeah.
I mean, truth, come on.
But you are initializing ERA 5. The question, why not train on ERA 5? Is that?
Well, the whole point of not training on ERA 5 is the fact that we only have 46 years of data, and that's not a lot of data in terms of subseasonal timescales. In terms of
well, it's better than nothing.
Yeah, so the option here is to train on CESM. So we have a wide variety of samples of different modes of variability interacting, and then we always have the opportunity to fine tune to ERA 5 if we really want to.
The complex point.
Jerry?
Yeah, so for the contest, the fact that you're performing much worse than the other models isn't surprising, right? Because you're training on CSM with all the systematic errors.
Well,
So
one
that's
would,
what you'd expect that, right?
well, one would hope that we perform similarly to the CSM S2S hindcast. I actually haven't compared where the CSM S2S hindcast would fall with these quintile probabilities. We only have 11 members, so I don't know how good that would be. But yeah, we would expect not to do as well as had we trained on ERA 5. That's correct. Yeah.
Andy, did you have a question?
Oh, yeah. I'm curious. I mean, I appreciate the desire to leverage the large ensemble for the training sample size. Is there a way you can do a climatological correction of that to the ERA 5 climatology so you can kind of train on something less biased, but still harness the full large ensemble?
Absolutely. We could apply like post-processing to our forecast. We did that in a very simple way by using the CESM quintiles instead of the ERA 5 quintile cutoffs. But yeah, there's a variety of ways we can take this in order to improve it, including fine-tuning on ERA 5, if we really wanted the best model here. But I'm trying to create this model for scientific applications, not best performing model.
Thanks.
I just wanted to comment that on these timescales, CSM itself initialized is also not as good as climatology. So we haven't done the comparison, but it might as well be that the emulator is as bad as CSM.
Which would be great, which is what we're trying to go for. We're trying to emulate CSM, so yeah.
Is there a reason not to train on the S2S hindcast?
Yes, there's just not as much data as CSM ensemble. And for my understanding is that S2S hindcasts are just run using CSM.
Yeah,
So
it seems like there'd be more data overfitting or something. Yeah. Right, Jesse. Yeah.
Zach, well, just to focus on getting CSM and his question about the out of sample, I mean, is there any value in like paleoclimate simulations to like force to get a CAM simulation that's way outside of the norm?
absolutely. And I've been playing with the idea instead of focusing on 1990 to 2025 of actually training on the full length of the simulation, including pre-industrial all the way to 2100. So we have, that's also a huge benefit is when we go out of sample into the future, we wouldn't be out of sample in terms of CESM. Thanks.
Cool. Thank you.
Yeah.
Oh, sorry. Was there one?
I don't know if I want to answer
In that case, I think actually you're better off training if I remember correctly, from 1920 to 1950 in the CSM2 large ensemble, because that'll be a better skill than the current 30 years.
To match our current climate, you mean?
I would, yeah, do the training, but if you're going to shift periods, you're better off shifting. The 20 to 35 does a better job basically predicting ENSO than the current period does.
Great to know. Thanks.
All right, thanks. Our final speaker before the break is Mike Levy telling us about the new Cupid diagnostics package.
Hey, hi everyone. Yeah, I'm aware that I am standing between you and coffee. I'll try to stay awake if you try to stay awake. So Cupid is a CSM unified post-processing and diagnostics. Most of this talk is going to be on the diagnostic side. You get better pictures out of it that way. This is a project that I was working on with Tegan King, who was also in CGD up until about 3 weeks ago, and is left to tomorrow.io. There's also input from a bunch of other people. I said countless on the last slide. There are 37 names. Sorry to ruin your game. You can try to find the misspelled names instead. I think I'm missing several people on this list. If you're in the room, I'm sorry. I do want to highlight that we have a bunch of students and interns. The CI Compass program, that's an NSF cyber infrastructure program, has sent us four students over the last 2 summers, and it's been great working with them. We have representation from pretty much every lab in CGD. GeoCat is a geoscience community analysis toolkit. It's the team that is spinning up the replacement for NCL, that Pivot, the Python program. They've been a great help as well. Let's start with just what is Cupid. Here's our vision statement. Like, we're just trying to be a framework, like the single tool you need to run all of the post-processing and get diagnostic plots out of CSM runs. We want to avoid inventing our own tools and really just provide a framework that makes it easy to use existing tools. So if you think of, time series generation, like no matter what tool you use, your time series file should look the same. And we just want to make sure that the steps for generating time series in the atmosphere are the same as doing it in the ocean and the land. And that's just a very, very simple API. This is a giant task list that is growing over time, but this is what we're aiming for with Cupid, and just highlight some of the things that we've gotten done. So we can provide key metrics like these diagnostics from most of the components in CSM. We can bring in some external diagnostic packages, and I'll show examples of that. We have what I hope are pretty straightforward command line arguments. We provide a common environment for running all of our notebooks. So you need to install 2 conda environments, one for the actual infrastructure and then one to do your analysis in. We have documentation. Like, the first rule of documentation is that it's never enough, but it's a start. We're incorporated into the CSM workflow, so you can run case.submit and have it run Cupid at the end of your run. And we're working on getting the summarization steps into the workflow. And one of our big targets is to just have support for any machine that can run CSM, and we're not there yet. So everything needs to be done in-house at NCAR right now. So just as an example, like, how do you use it? So you install these 2 conda environments, and then you run the Cupid diagnostics command, and that runs a bunch of notebooks based on the configuration file in your examples directory. And then you run Cupid web page, and it builds a website. And then you spend weeks learning how to get a website off of Derecho because they don't run a web server there. But eventually you can just bring up a web browser and look at plots. So I mean, if you check out Cupid, theoretically you could run this. We saw a talk earlier talking about the difference between model and actual, like the whole theory versus practical. You'll probably need to email me when it doesn't work, but this is the dream. For part of the CSM workflow, there's an environment variable in your case directory called run post processing, and the default value is false. And so when you run CSM, it runs, when you do case.submit, it runs CSM, it runs a short-term archiver, and then it's done. If you set run post processing to true, then after the short-term archiver, it introduces this new case.cupid job. we have a whole bunch of Cupid underscore XML variables that you'll need to change to set up Cupid to run the way you want it to. But then when you run case submit after the archiver, Cupid will run. Or if you've already done the run in the archiver, you can do this only job case.cupid option. And I think Cecile is testing this out. I'm not sure that we're ready to say that it works flawlessly every time, but it has worked in the past and it will work in the future. So just running through on the diagnostic side, some success stories from the Atmosphere group. So Isla showed some plots very similar to this in her talk yesterday morning. Right, that was yesterday. No, I've lost track of time. And she gave us one of those notebooks to look at this normalized mean square error for I think surface pressure, and it just gets run with Cupid. And then the ADF, which I thought was the Atmosphere diagnostic framework, or maybe the AMWG diagnostic framework, but might also be the AMP diagnostics prototype. Somebody got an F for passing in spelling as a kid.
Must be Justin.
Must be Justin. Yeah. So this is a set of Python scripts. Yeah. This is a set of Python scripts that generates diagnostic plots, and it can be launched through Cupid. So if you configure your Cupid configuration file correctly, it will just run the ADF for you. So this is its landing page. I should say that, so on the left is like the sidebar you get from the Cupid website. Then if you click on ADF, you'll get another page that has a link to this page in it. And then you can bring up plots that the ADF generated inside your Cupid website. The climate variability diagnostics package, CVDP, this is something that Adam Phillips has put together. So it can be run through the ADF. This is now like Inception, right? You run CVDP through the ADF, through Cupid. But it's the same deal. You click on the CVDP page, link on the sidebar, you get a link to the landing page, and then you can bring up plots and you can explore through there. Hopefully a future success story. So for the past like 3 months in the CSM project meetings where we look at the CSM3 development run diagnostics, Adam Harrington has put up some version of this plot and he makes it himself. And every time he shows it, I'm like, I should really talk to him about getting this into Cupid and then we can make it for him. I told him about this yesterday and it'll probably get done sometime in the next month or two. And then beyond that, we have some future work for Cupid. So Atmosphere specific, we've talked about bringing in notebooks that provide metrics from forcing data sets. So we don't just want to look at model output. We want to make sure we're forcing it with the data we think we're forcing it with. We've had some issues with emissions data sets in the past, and this would help us spot those a little bit faster. And maybe we could also get Cupid into a standalone CAM release. So something that's happening on the land side is that the CTSM team is bringing in Cupid for the standalone CTSM release. And they're going to put together like a land-only example. And I think it would be pretty nice to have something similar on the CAM side. Some general Cupid features. So we want to support the CMIP rapid evaluation framework or the REF. And I'll talk about that a little bit on the next slide. We want to introduce kind of this quick look functionality. So what we've called the key metrics was supposed to be just a small set of metrics that are quick to run and easy to look at, and it's grown beyond that. And so now we need an even more key metric that is just cheaper to run and easier to look at. We're still in beta testing, for lack of a better word, but we do want to work towards a version 1 release with better remapping, integration with summarization. Hopefully this can happen before the CSM3 release. So going back to the rapid evaluation framework, this is basically just a figure that I grabbed from the website to let Dave know that I've been looking at the REF website. But I mean, this is the workflow for CMIP data that I think is like really standardizing the data, making it easy to look at, and we can pull in some of these things like their benchmark portal might be what we want the top metrics to be. Yeah, so just to summarize, Cupid is a framework for post-processing CSM output and also generating diagnostic plots. A lot of work has gone into the post-processing, even though we didn't talk about it. It can be run as part of the CSM workflow or launched by hand after run has been complete. You can run just individual Jupyter notebooks, or you can bring in external packages like the ADF or the CVDP. We're always looking for people who want to contribute. And so we've got the website and the GitHub page on there. We're also always open to bug reports. It is a work in progress, so it won't take you much time to find the bugs. I'll advertise too that the software engineering winter working group meeting, which is a month from Thursday and Friday, is a hackathon, and we'll have some Cupid projects on there. So if you want to come and work on it, you can do that. The land model working group meeting will also have a 3-hour Cupid tutorial that will be, based around this standalone CTSM incorporation. Yeah, so I think that's it. I talked really fast, sorry.
Perfect. Any questions? This hackathon, are you specifying the projects, or is this an opportunity for people who want to come and add in something to them?
So I think registration for the next 2 weeks, you can suggest projects, and then sometime in the middle of February, it'll be locked in. Just come work on those ones.
Keep you open coffee. Can you what would it take to get like Cupid to run in a CAM standalone? Because obviously we're already pulling Cupid in as an external. Do we just need to like have a config file set up for the workflow, or
standalone? Yeah, so I think we need to set up the management example and make sure that is like the default value for what Cupid example you want to base your configuration off of. All right, cool. I didn't know it. You're way ahead of the
Questions? Okay, coffee break time. We'll come back at 3:20. All right, hi everyone. Now we have a double act. Haipeng and Jesse are going to tell us about CAM SEMA and the CAM4 Aquaplanet and plans in that area.
Thank you. Good afternoon. Can you hear me? I can probably move this. I'm back. My name is Haipeng Lin. I'm a software engineer in AMP. And today, Jesse and I are presenting on some updates on CAM SEMA. I'll focus on CAM4, and Jesse will focus on some other exciting updates beyond CAM4. And no, it didn't come from a time machine right off the break. We are talking about CAM4 because talking about CAM SEMA. So CAM SEMA is the next generation of CAM with modern software engineering practices. And more importantly, it uses physics driven by the Common Community Physics Package framework developed in collaboration with NOAA and other collaborators. This provides better runtime configurability, modularity, and allows us to better share physics parameterizations with other models. And this brings us benefits to scientists and developers alike, which hopefully you will cover some of these advantages today. So what I mean by CCPP compliant physics parameterizations or physics schemes, the code is still written in Fortran, so you can kind of understand these new points as a set of conventions. And so CCPP compliant physics parameterizations have standardized init, time step init, run, and finalize phases. There's no read NL anymore. CAM SEMA automatically handles nameless reads. So you no longer need to write individual read NL entries or go into a very long nameless definition or nameless defaults.xml to change nameless parameters. Instead, each scheme owns its own nameless entries in a separate XML file for each parameterization. And most importantly, there's this concept of metadata. So for CCPP compliant physics parameterizations, instead of passing in the CAM model state or the physics buffer, pbuff variables that are kind of model specific, each physical quantity that is passed into or passed out of a physics parameterization is an explicit argument in and out into that subroutine. And there's this file called the metadata, which kind of looks like a lot of blocks like this that map the individual arguments in the subroutine to unique physical quantities that are documented, uniquely identified by a standard name here. Say KVM argument is the eddy momentum diffusivity at interfaces. And the units are also documented together in this metadata file, which means that gone are the days where you would look at a pbuff variable and have to hunt down in the code what the units actually are. And the framework will take this information and be able to validate at build time whether each scheme's inputs are readily available in the model state or as an output from another scheme. And third point is that we try to reduce or remove the number of host model, in this case CAM, specific assumptions or dependencies in the code to allow it to be shared across different models. So once we have this CCPP compliant physics parameterization, we can assemble it together into what we call physics suites. Think like CAM4, CAM5, CAM6, CAM7. And instead of having this phys package.f90 and calling individual subroutines individually and having to hunt down the inputs and outputs, because we have this metadata information, the framework will be able to assemble the calls for you in the order you specify them in an XML file, say here scheme, cloud particle segmentation, and it will take the metadata information and assemble the inputs into that scheme and output from that scheme. And because current CAM is still the workhorse model that's used in CESM, the conversion of physics into the CCPP framework versions has to be done under the hood to avoid fragmenting the code base of the physics parameterizations. So this is current CAM. Once we move a physics parameterization from CAM into a CCPP compliant version, we move it into this atmospheric physics repository. You can see it in CAM under source / atmosphys. And what is left behind in CAM are just minor interface calls that take the information from the pbuff and pass it on to these explicit arguments into the CCPP compliant subroutines. And the converted physics parameterizations in atmospheric physics can be used directly in CAM-SEMA through the CCPP framework and can be mixed and matched into different physics suites. And the advantage of these suites is that your physics suite can be just that parameterization, and you can run only one parameterization based on archived CAM outputs to make sure that they are validated bit for bit against current CAM and give the same results as they would be ran into CAM. And once converted, the same code is compliant and is shared by CAM and CAM-SEMA under this atmospheric physics repository. So there's no fragmentation or duplication of scientific code. It's all under one unified code base. So how close are we to that future? Today I'll talk about CAM4 physics, which has been fully converted into CAM-SEMA. CAM4 Aquaplanet configuration is now available, and we're actively working with ACOM to bring in the bulk aerosol model so we can soon have a real Earth configuration of CAM4 in CAM-SEMA. So this CAM4-ish configuration of CAM4 in CAM-SEMA uses RTMGP for radiation instead of CAM-RT, so we can share this with CAM7. And the die core support is slightly different. It's the SE and MPAS die cores instead of the original ones that shipped with CAM4. And to prove that this model does exist and does work, this is courtesy of Jesse. It's a 10-year QPC4 run in CAM-SEMA using the MPAS die cores, the temperature at lowest model level, and water vapor at 5 kilometers. So yeah, this model does exist. And now that I've proven that it exists, I'll talk a little bit about some of the benefits and lessons we learned as we put together CAM4 inside CAM-SEMA. So this is convect shallow .f90 from CAM before we moved it to CAM4, before we moved it to CAM-SEMA. And this is CAM4 code, but a lot of CAM physics looks similar. You have this you have this call to some computation, but it's not truly just the science code. It has CAM-specific assumptions, like it has chunking. Maybe there's some model state or pbuff or CAM libraries used underneath. So you couldn't really take this subroutine and take it to another model and use it directly. And there's some setup from the pbuff. And it wouldn't be complete CAM code if it didn't have permanent leftovers where it says it's supposed to do something, but it's actually not. And this will do for now. By for now, it's on the time scale of decades, usually. And there's usually some code that's detached from the actual computation. Sometimes, if you're lucky, it's mostly used for diagnostics. But there could also be cases where you're unlucky and you bump into a variable. It's actually shared within the pbuff, but it's detached from the computation. It's not documented, so it ends up affecting something down the line. So these are kind of hidden surprises that often happen if you're developing with CAM code. And we try to reduce these things and separate concerns in the code. And this is the suite definition file that runs the shallow convection scheme from CAM4. In CAM-SEMA, we cleanly separated out this shallow convection science code into this hack convect shallow scheme. And for the diagnostics and diagnostic-specific computations, we separated out into these diagnostic schemes because the way that add-field and outfield calls are done, it could be different across models. So you want to separate that from the science code, which may be used in another model. And there's these common tendency updaters, which are reused by every physics scheme if you have to update the tendencies after running the science code. And what I wanted to point out is the subcloud evaporation after.
Okay, CAM, it was to try to cover configurations that all labs care about. Some of them, like WACM and WACM-X, do of course exist in CAM already, but we want to make sure that eventually that's incorporated into SEMA. But the real thing that's unique to, from a science standpoint, to SEMA is bringing the incorporation of NWP configurations, right? Of M-cube physics, WRF physics. And not only that help us match, a lot of the experiments where we mix and match between CAM and MPAS, for example, but since NOAA has agreed to take on MPAS as well, and they also use the CCWG framework, we can also, in theory, replicate UFS configurations. So we could have more direct connection with NOAA. For my talk, and most of the software engineering focus has been on MMM, the global weather configurations with MPAS. So that's what I'm going to focus on. Oh man, it's so small. Okay. Doesn't matter. Okay. So the first thing we got to do is bring in the MPAS DICOR. If we want to do global NWP configurations, this already exists in CAM, so we've done the same in SEMA. And in fact, those CAM4 configuration, those CAM4 plots you saw were with the MPAS DICOR. So the MPAS DICOR fully works, including with idealized configurations that have been scientifically validated. But it's not just a straight copy and paste. Quanchi has spent a lot of time trying to do good software refactoring of the dynamics physics coupling layer to make it easier. And actually this does kind of help because, I should say it definitely helps, but these pictures kind of help. So on the left is a snapshot from the dynamics physics coupling in CAM. And on the right is the CAM-SEMA. And the code actually doesn't matter. What matters is on the left, that is like one block of code within hundreds and hundreds of lines. And on the right is the entire dynamics physics coupling layer in SEMA. Now, of course, the sheer amount of code is the same, right? Math's got a math. But what Quanchi has done is spend a lot of time splitting up all of these hundreds of lines of code into separate subroutines to make it much easier to follow. So in SEMA, you can go in here and you don't even have to be Peter Luritzen and you can follow what's going on in gory detail. So, so that's from a software engineering standpoint, that's been a major boon. But again, I said that, CAM already has MPAS, so who cares if SEMA has that? We also want is the physics, right? The physics schemes from MPAS. That there's kind of generally two physics suites that MPAS uses. Here they are. And there's basically two different configurations. You can kind of think of them as the left one is sort of lower resolution, the other one's sort of higher resolution, but they mix and match all the time in M-cubed. And so we kind of wanted to just bring over at least some set of these physics schemes to have something that we can justify as being able to run at short, weather timescales. And so we wound up with this.
And so I want to kind of make two highlights here. First, everything in red has either already been ported or is already present in SEMA. So we're actually getting pretty close. And at the rate that Quan Chi is going, because Quan Chi is the only one actually working hard on this, we will probably be done by the end of the fiscal year. So we will have a model that can do both CAM and MPAS physics configurations in the same code base. Now that I've cursed him, I will also emphasize that we have several new schemes here as well that haven't ever been run in an MPAS configuration. So a lot of them are just kind of iterations on current physics schemes. For example, we have RRTMGP. That's just a continuation of RRTMG. We're going to bring in the tempo microphysics, which is essentially a continuation of Thomson microphysics. But we have totally new options like CTSM, right? Like MPAS standalone runs with the NOAA land model. And so bringing in CTSM, which my understanding is a more complex land model, will allow for more land-atmosphere interaction studies that simply have not been doable before. So that's, so this is like truly new science. So this is not even showing things like MOM6 and other Sci6, all of the other coupling options that we will soon have. I'm going to skip this because Peter actually covered at the beginning, but there's also this water isotope project. And all of the physics and options for this is going into SEMA. So if you have an interest in water tracers or water isotopes, please fill out this survey. There's a URL and a QR code. And a lot of times I could talk for 2 hours on why everyone should care about isotopes, but the real connection is, we want general water tracers for hydrologic studies, and eventually we want water tracers because we can trace things like the temperature of water. Because when you can trace the temperature of water, now you can no longer just assume what the temperature of rain is as it falls in the ocean. You know the actual value. And so that's actually better thermodynamics. It closes the energy budget better. Cool. All right. I have 9 minutes so I can make you all suffer through some software engineering talk. So let's do it. Yes. I'm trying not to contain your excitement. So part of this is really to emphasize that a lot of times it seems like our software engineers aren't doing anything, but we really are trying to make the code better in a way that helps you all, right? That helps the users. And so one of the things we've been pushing in SEMA is runtime configurability. And if you want to figure out why that matters, imagine if you're running, say, the CSM tutorial and the users only had to build it once and then they could do every experiment with just runtime configuration. That would save a lot of time, a lot of computer resources. We're not there yet, but we're trying to get there. Things that we can now set at runtime that we can't necessarily set in CAM includes things like the number of MPI tasks, which actually you can do in CAM, the number of vertical levels, the number of constituents or tracers, advective species, whatever you want to call it. You can set the known set of chemical reactions, and that's provided by Musica, which is mostly developed by Kyle Shores and Juwan Jim and others at ACOM. And then we're also trying to move a lot of physics parameterizations have like hard-coded tuning parameters. So we're trying to also expose that into nameless variables. Another thing, oh, thank God this is bigger. Whew. All right, so the other thing we're really trying to emphasize from a software design standpoint is kind of the separation of concerns. And you can imagine something like file reading or file writing. Obviously, scientists, software developers need to do file I/O, but they generally don't care how it's actually being done, right? They just want to have, it's just like, using X-ray in Python, just open data set, and they don't really care how it's being done. So we're trying to do that by bringing in an object-oriented approach into SEMA for those kinds of infrastructure things. And so here's an example of a file reader object that we have in SEMA, where again, I won't touch it, sorry, I'll back up. You just you create the file reader object, you call open file, you just make sure nothing disastrous happened, and then you get the variable. And all of the actual gory details are hidden from the physics developer. And so that's really helpful for infrastructure code, but we found that can be a problem for things like physics code because physics teams would say, oh, I have the Richardson number, and another physics team will go, oh, great, I also need the Richardson number. But of course, they're two different Richardson numbers. And so they ended up causing errors in the model. And we also want a way where you can track down exactly which equation did you get this Richardson number from, because especially in CAM 4, there's a lot of equations that seem to come from nowhere. So, so what we've done is then emphasizing what's known as a functional programming approach. And so that's what's on the right. This is a function in SEMA for calculating the Obukhov length. It doesn't really matter what we're calculating. And And it looks like a boatload of code for what's essentially that just bottom 2 lines. But the core thing is in the comments, which you probably can't see, is we have a very specific provenance. We state exactly in which textbook we found this equation, the DOI, what page, the equation number, there's the LaTeX formulation of it, exactly what the units are that we're expecting in that variable. And then the other thing which matters from a software standpoint is that label of pure in the top left. The elemental is not as important. And the pure means that this function can only output the obocoff length. It cannot, the compiler will check. It cannot do anything else. It cannot write to the log, cannot write to a file, cannot use a pointer, cannot do anything other than provide obocoff length. That sounds really restrictive, but that's actually really helpful for debugging, because if you're using this and it crashes your model, then it just means the obocoff length is bad or the inputs are bad. You're not doing any sort of weird thing. So a lot of times weird things take us SEs and scientists a long time to debug. The other thing we're trying to work on is design documentation. So CAM, even CSM as a whole, we have users guides describing how to use the model. If we're lucky, we have scientific documentation that describes the science behind it. What we don't have is like design or developer documentation, which is kind of describing like what is the code actually doing? Like why is this piece of code here and not there? And so we're trying to build that for SEMA. So here's two workflow diagrams that Courtney made, and essentially it's just showing, okay, the flow in the actual code. The model starts up, you have physics and dynamics, they both initialize, and then I kind of split it, but essentially it would show that, okay, DP coupling happens first, so the dynamics actually reads the data, writes it to the physics state, then you run the physics, then you run the dynamics, and then you write the dynamics code back into the physics, and that just loops for however many number of time steps. We found that having this documentation really helps, particularly starting software engineers, because they can come in and be like, oh, okay, this is what the code's actually doing, as opposed to just like, there's a giant state thing that does something. Real quick too, we're also, you'll probably hear on Wednesday, there is this general desire to move away from Fortran for various reasons. And one thing we're trying to prepare for that is taking things that any language can do, like variable declaration and definitions, and pulling them out of just core Fortran source code and putting them instead into languages like XML or YAML. Could do the same thing. And so here's an example, right? Like here's physics tendencies defined in CAM, and so they're defined in the Fortran. Where on the right, we have a registry, which is the same thing that WRF or MPAS does, where we're defining tendencies here. And the advantage is that it looks like more code, but again, it provides more information. It tells you the dimensions, right? This, you actually don't know what the dimensions are. You just know that they has 2 of them. And it also provides info like what would the variables be called on initial condition files. The advantage of this too is in the future, if we ever move to, I think tomorrow let's talk some Python JAX or C++ or those things, they all can handle XML. So we have this data that's kind of like now language agnostic and saves developers from having to get into the guts of SEMA. That's just, we have testing. It's great. Finally, I have 3 minutes. There's some real quick on potential feature stuff. This is things that like people have written proposals for. We haven't gotten necessarily funded yet. One is mixed precision capabilities. If you actually, the quickest way to speed up the model is just to drop precision. Fortran allows you to do that, and you could basically double 2x the model just by going to single precision. But not every physics can handle that. Sometimes integrals won't close or implicit calculations won't converge. So, there has to be some work on that, but definitely mixed precision is a goal for that capability. Obviously, continued GPUization. That's kind of the future of supercomputing, at least to our knowledge. So trying to get better at running on GPUs as a core. And then also, as I mentioned, there's recently been a real push on trying to see if we can use Jack accelerated Python. And the really cool thing about that is not just converting it, but trying to use AI to convert it, because that would save us SEs a lot of time if we can just kind of press a button and be like, make this, do this code translation, and then we can come after that and clean it up. Again, it hasn't been necessarily done yet, but it's definitely a target goal. So, okay, that's it. Thank you. Appreciate it. What's Haipeng? You want back up here?
All right, thanks. Any questions for Haipeng or Jesse? I'm wondering if you have an estimate of when we will be fully moving to CAM SEMA
There's some politics wrapped into that. So, we hope to have CAM 7 function, low top CAM 7 functionality maybe by this time next year. The question is then like WACM and WACM-X and CAM and other capabilities that are in CAM. It'll just take longer. So my guess is we'll probably have a version of CESM where SEMA is like maybe the workhorse, but we'll still have another branch where until we convert all of the other ones for the other configurations.
Thanks.
No problem.
Dave?
How much are you at all sharing experiences with the SEMA with other components?
Not a ton. Probably more we should. We haven't been sharing them we've been in discussions with MQ groups. And so that's probably the one we're sharing with. And obviously ACOM, the ACOM knows about it as well. Yeah, we should. We talked a little bit we talked a little bit to people like Bill Sachs and things on the CTSM side. Because it's also, column physics. So you imagine some of this stuff could be applicable, but we got other priorities too.
Sure, CGSM is mechanic because it's an in-house developed model. You could try to make them consistent on all the benefit, but just an example, I really like the sort of in code documentation of the equations, even just, having that a philosophical, way we're going to develop the code would really make it like long-term sustainable and usable. So, because we have our separate documentation, but it can get out of sync. And,
right. Yeah.
Anyway.
Yeah, I'm happy to stand on that soapbox. So, yeah.
Counter that to a certain extent and ask whether you, in rewriting a lot of the code and kind of expanding in the way you did you say, this is just too much? As in, like, if someone comes in here, there's just too much information in terms of if they were to develop code, did you back off anything? Because you could take for example, you could take every pure function and just say every little bit of calculation you do, we can put that in a function.
Yeah. But there is some performance. Yeah, there's a general question about modularization, like how much do you modularize? That's part of it. So for the functional stuff, what we started with are equations, which this is known equations in literature, right? Like if I say, give me the potential temperature, we should all generally, we don't agree. And CAM, we don't agree what potential temperature is. But you can imagine that we could agree on what potential temperature is or moist static energy, right? All of these equations that have known definitions. So those are the ones we started with, is we can find it exactly in the literature. It's, in a textbook, it's here. Here's the documentation. The ones where we did kind of back up a little bit are ones which they seem very ad hoc and they'll even in the comments be, I don't think this should work, but it does, question mark. So we didn't turn that into a function. We just kind of left that as is. There'll always kind of be a discussion, but we would like to, ultimately, we'd like to get to all of the things that you kind of learn, all of the functions you might learn in undergrad or grad school. We want to make functions, and all the ones that are super specialized for CAM or something is one probably would basically where I'd put it.
We all agree on the radius of the Earth.
We don't even agree on pi. Sorry, we do. We're great.
All right, thank you. We'll move on to working group updates. Steve or Kathy, are you there online? Yeah, Steve's there.
I'm here. Can you hear me?
Yep.
Super. And does that look good?
Yes.
Okay. Well, hi, everyone. Sorry I couldn't be there in person today, but I look forward to joining you tomorrow and connecting for the CVC and ESP working group breakout sessions. So just a pretty brief update on the Earth System Prediction Working Group. In these sort of joint sessions, I always like to put up our mission statement just because there's always new people in the room, just so you can know what we're about. I'm not going to read through this, but you could. The bottom line is a group of individuals interested in initialized Earth system prediction and sharing our research on that topic. So we've got our webpage and mailing list, and please join the discussion. One of the key foci for this working group is to generate and curate initialized production data sets for the community. And I'm sorry, this slide has a lot of words on it, but I'm just going to highlight this collection that we've now extended that encompasses sub-seasonal to multi-decadal prediction data sets. From CSM1, we had the CSM1 S2S and decadal prediction large ensemble, and then with CSM2, we've now extended from sub-seasonal reforecast sets to the intermediate timescale multi-year, out to decadal, and most recently out to multi-decadal timescale. So a very rich resource for people to pursue predictability research. And I just wanted to highlight some recent developments. We've got several of these reforecast data sets now uploaded to the Geoscience Data Exchange, thanks to Pegan and Nan and others. Those are well documented, available for download or accessible via Glade. And we've been using our allocation resources most recently to extend some of these data sets. So the original CSM2 small data set started in 1970. We backward extended that to 1958, so permitting a larger sample exploration of predictability and state dependence. We completed the CSM2 decadal prediction reforecasts that go all the way back to 1958, and the most recent initialization in 2023. And then we're now exploring this range beyond decadal with 10-member 20-year hindcasts that are initialized every 5 years, starting from 1960. So analysis of that data set is underway in a multi-system study. I should also mention that we completed multi-year forecasts that followed this TBI MIP protocol. This is the Tropical Basin Interaction MIP. And you can find the description of that MIP in this geoscientific model development paper by Ingo Richter. So those replicate SMILE, but with SST nudging in the tropics of the Pacific, Indian, and Atlantic basins. And the upload to GDEX will be coming soon. Oops. Okay, I wanted to throw in some select science highlights. This is one that really showcases some nice science done with the CSM2 SMILE data set led by Yu Lang at Scripps. So he explored the dependence between March MJO in the 1997 initialized forecast from February 1st of 1997 and how that related to the subsequent hindcast spread in the winter El Nino. So going from March 1997 to December 1997, showing really surprisingly low correlation between those two factors across the hindcast ensemble. And you can check out his paper where he shows that the causal precursor really seems more related to the North Pacific meridional mode. Sorry. Another science highlight with this multi-year data set, we're now able to participate in these multi-system analyses that really shed a lot more light on how we're performing. So we're not just analyzing our system in a vacuum. So this is a study that Nick Dunstone is leading, analyzing all these systems that go out to year 2. And he's showing that CSM2 is quite a good performer for that second winter El Nino prediction. So I'm showing you that here on the upper right, one of the better models for the second winter Nino 3-4 skill. And another interesting finding from his work is that in terms of year one global mean surface temperature predictions, 2023 was the largest forecast bust across this multi-system ensemble. You can see that here, the forecast error reaching this large value in 2023, and it turns out CSM2 is one of the worst. So, you know, we're getting some interesting feedback on our system and things to explore further. Here's a study that Dylan Oldenburg is pursuing. He's doing a multi-system analysis of initialized decadal predictions, looking at North Atlantic Ocean heat content skill, forecast years 6 through 10. So kind of looking at the latter part of the decadal forecast. And this is the first time I've seen this inter-system comparison this way, where he's showing the deviation from the multi-model mean skill shown here in the center left. And it's interesting to see that both of our decadal prediction systems from CSM1 and CSM2 are performing quite well compared to other DTPP systems from CMIP6. So he's pursuing this question of what explains the skill spread across systems, and he has a talk Wednesday afternoon in the ESP session. Another science highlight is work looking at the intercomparison of our decadal prediction systems for skill over Africa. So this is in collaboration with the UN Office for the Coordination of Humanitarian Affairs, looking at country-level precipitation skill in these decadal prediction systems. Here comparing CSM2, CSM1, CSM1 high-res from Mesa Clip, and then the uninitialized historical CSM2 large ensemble. So you can see there's quite a bit of variety here, large skill in the Sahel in general across all these systems. But a surprising result is that in the Western Sahel, it turns out that the low-res CSM2 actually outperforms the high-res. So Nina and Emily are asking, is this skill actionable enough for UN purposes, and what explains the skill sensitivity? So we've also used ESP allocation for development work, and this is a figure from Meg Fowler showing her S2S exploration of the sensitivity to land-atmosphere coupling. I won't go into detail because I'll let Meg describe the results, but the bottom line I think here is that when you add stronger land-atmosphere coupling, you do see some benefits in weeks 1, 2 for summertime surface air temperature skill, and then kind of mixed results for weeks 3, 4, and afterwards. The working group is also supporting work to better understand the role of model formulation and physics in S2S skills. So Abby J. and Judith Berner doing work that compares the CSM2 standard S2S set to, I think, an atmosphere-only CAM6 initialized hindcast, and then 2 versions of the MPAS atmosphere model, 60 kilometer and 120 kilometer. And finding that MPAS appears to be outperforming CSM2 in these critical weeks 3, 4 forecast periods. So Abby's going to be talking about this also Wednesday afternoon. We've also been using working group allocation to support the development of the Decadal Climate Prediction Project protocol for CMIP7. And we're getting help from people like Evan Meeker at Wisconsin-Madison to probe the optimal design of idealized forcing experiments that could inform decadal predictability mechanisms. And this is just an example of one of the experiments that the DCPP panel is exploring. So this is an idealized dilution low forcing in the North Pacific, lasting for 10 years, giving rise to this SST response in the coupled CESM2 model. That SST response then has a positive feedback on the original dilution low forcing with some knock-on effects in the North Atlantic that have impacts on AMWG. So this is candidate for one of the experiments that might be proposed in the mechanisms part of the DCPP protocol. And Huili has been doing similar work, but this time looking at idealized SAM forcing. So forcing of the ocean, the Southern Ocean, and looking at how the coupled model responds to that perturbation. So here, this is an experiment where we're applying an idealized Southern Ocean wind stress forcing. It gives rise to sort of a weak IPO response in the first 10 years, but then a very pronounced IPO plus response after you finish the forcing. So I mentioned DCPP. As part of that panel, I can provide the working group some insider info on what to expect in CMIP7. Basically, the protocol for CMIP7 will follow the same structure as in CMIP6, with component A being prescribed retrospective forecasts. Component B will be the real-time forecast protocol, and then component C, these process experiments that I was just sharing with you. But some key differences from CMIP6 are that we plan to lower the barrier to entry. So we'll have a DCPP deck set of retrospective forecasts that should be roughly 1,000 simulation years, which is substantially cheaper than the protocol for CMIP6. And that will hopefully facilitate more groups to participate, including groups that want to run with more expensive, possibly higher resolution models. There'll also be an option to choose a multi-annual route through the DCPP protocol. So groups will have this option of submitting multi-annual reforecasts or decadal forecasts. So this will again help to explore this intermediate space where we think we have most skill from these initialized systems. In association with that new multi-annual route, there'll be a protocol for real-time multi-annual predictions, updated each year or possibly even more frequently. We're going to propose, experiments to test the impact of updated forcings on past reforecasts. So as the CMIP7 forcings get updated, there'll be a prescribed protocol for how to redo those reforecasts and look at the impact of the observed forcings. I mentioned the new coupled experiments to probe decadal mechanisms cheaply using standardized forcings. And then another novelty will be that this protocol will be open to any AI ML contributions. So we're not limiting it to dynamical systems. So looking ahead in the working group, we're going to continue development, exploration of sensitivities and novel experimental frameworks, probably focusing on the CSM2 baselines that we already have in hand, and looking forward to initialized prediction tests with CSM3. I think initially wanting to use similar methods as with CSM2 to facilitate direct comparison of predictability, and then move towards CSM3 production contributions to subseasonal protocols and the DCPP of CMIP7. And at that point, using whatever best available methods we have to maximize system skill. Some of the perennial challenges in the working group, there's strong demand for real-time capability, so there's need for a better initialization method, and hopefully there'll be some synergy between ESP and the Ocean Model Working Group with their development of C-Force. the strong interest in high resolution. So there's a need for well-designed minimal experiments that can, as I said, lower the barrier to entry for these very costly ensemble experiments. And I just wanted to end with an advertisement for the ESMO S2S2D meeting in Reading in September. Abstract deadline is a couple weeks away, and we're happy this working group is able to facilitate participation in this kind of conference by the broader university community with CVSM. I'll end there.
Do you have any questions for Steve? We'll also have discussion time at the end for broader discussion on future plans for the working groups. But any questions right now? All right, we'll get, Andy, yeah.
Hi, Steve. Thanks for the talk. I have a question you might not know the answer to because you're reporting on a lot of other people's work, but it's interesting that when you look at those multi-model experiments tracking the error in the forecast, many of the models seem to have basically a sort of same time sequence of errors, but the CSM model departs from that a little bit more. Have you guys looked into that at all?
No, so you're referring to Nick Dunstone's work. It looked like there was a lot of commonality to the forecast error there for global mean surface temperature, which I would suspect relates to forcing errors. But I admit I did not notice that CSM stood apart there. I don't know the answer.
Any other questions? Okay, all right. Thanks, Steve. We'll move on to the Climate Variability and Change Working Group update. I'm going to keep using this mic because we're going to switch between. Is that okay? Okay. All right. So this is an update for CVCWG on behalf of co-chairs, me, Isla Simpson, and then Aishu is going to take over on the presentation in a minute. And then Sarah Larson, who unfortunately couldn't make it here in person. And then Adam Phillips up there is the liaison. So in case you're not familiar with the working group, I just want to point you towards our website, which is, I think, the best place to go if you want to find out about the simulations that we produce. And so you can, when you go to this website, you'll see this big list of all of these large ensembles and then more idealized simulations that the working group has run. And if you go to any of these, Adam has nicely organized these web pages so that on each of these, you'll see clear instructions for how to get at the data, whether that be on GLADE or from the web access from the Geoscientific Data Exchange. And so CVCWG is more of a kind of producing simulations working group as opposed to developing the model. And I'd say in the last year, we haven't done so much of that because we're kind of waiting for CSM3 to be ready, and then we'll start doing a lot of simulations. But there have been some things going on, so we have some brief updates on that. So one is this multi-column ocean model. This has been going on for a long time, I think many years in the making, because there's been many challenges. It used to be called the pencil model, but now it's being called the multi-column ocean model. There were many challenges in getting this running and stable, but it is now kind of close to being completed. So this is being led by Young-Oh Kwon, and Gokhan has also been heavily involved in this. And what we're talking about here is that second configuration, which is in between the slab ocean and the full 3D ocean. And so in the slab ocean, you basically just have a swamp of water, and you have to tell the model what the mixed layer depth is. Whereas in this multi-column ocean model, you basically have a single column ocean model at every grid point. So it's doing mixing, and you have a prognostic mixed layer depth. And so this is now set up and running. This is all being done in CSM2 because it's been quite a long running project. Young-Oh and his group have now run a 700-year-long pre-industrial control with this configuration. And the data for that will be made available. It can be compared then with existing pre-industrial controls that have been run by the working group. And that will be made available when the paper is submitted or accepted. And I think it will be submitted very soon. So you can look forward to that soon. Here's just a sneak preview of some of the results. And so here, what you're seeing is the SST climatology. On the right is the slab ocean model, and then relative to the full ocean model. So the bias relative to the full coupled model. And then in the middle is the multi-column ocean model. And you can see that having this mixing and the prognostic mixed layer depth is giving you reduced SST biases compared to the slab ocean model. He's also finding that when you look at the seasonal cycle of the mixed layer depth, this idealized configuration is doing pretty well at capturing that in most areas except for in the tropics. There's also been work done with the allocation for this working group on perturbed parameter work, and we've already heard a lot about this already today. So Adisu and Brian have been calibrating the model with this new machine learning based autoconversion and accretion scheme. And so they've run a perturbed parameter ensemble that we've already heard about to try and optimize the parameters in this machine learning based scheme. And they've changed many parameters. And on the right there is a figure that I think Dave already showed, where you're seeing the precipitation distribution, and then the purple line is this kind of optimized version of this machine learning based scheme where it's doing much better at capturing the extreme precipitation events compared to the original Kharitonov and Kogan scheme in the red there. And they've also tried to optimize that. And so there's definitely some kind of big improvements there through this process. We also already heard about this, that the PPE that Adisu ran was also used in this effort that we heard about from Yang to kind of step through and iterate through and kind of home in on the optimal parameters for CAM6 in their PPE work. And then Brian is also starting to use initialized hindcasts for PPE work. So he's running short. You can see there sort of, I think 18-day forecasts or 10-day forecasts maybe, initialized from observation-based states, and then running forward in time with prescribed SSTs, and then looking at how does perturbing parameters change the skill of these hindcasts. And what you see there on the right is just one example hindcast. The orange is the kind of regular S2S forecast, and they have a big spread because there's bigger uncertainties added to the initial conditions to kind of represent the uncertainties we have in the observations. But the important point is that the green is when you just do a random noise perturbation to the initial conditions, and you have a very small spread in the trajectories of the members. And then the blue is the perturbed parameter ensemble, and you can see that you have a bigger spread as a result of changing the parameters. So there's spread that can be looked into to understand how parameters change the skill, and also is there sensitivity to how parameters affect the skill depending on the kind of the initial state. So that work's just getting underway, and I'm sure Brian will have more of an update at some point in future meetings. We've also been trying to explore the use of initialized predictions in the coupled model development, and we heard very similar work to this from Jonathan, and we were kind of finding very analogous things to that. We didn't really maybe use it really that effectively in this development cycle, but I think we tried some things, and I'm hoping that we can do more on that and have this as more of a part of our workflow. Just a couple of examples up there on the top is showing you a bias in one of the development configurations in the free running model on the left. And then on the right is initialized predictions starting from May 1st. And you're seeing the bias relative to observations in June, July, and August. And the point there is that the free running model had this warm bias over mid-latitude land. And then the initialized predictions over this very short window of 4 months also develop a very similar bias. So it can maybe give you a more efficient way of trying to tune the model and get rid of some of these biases. And then the bottom case there is a case where it's maybe not so effective. So this is showing the impact of changing the explicit diffusion in club, turning it off, I believe. And so the free running case, you can see that turning it off gives you this big warming in the Arctic. You don't get to see that yet in the initialized predictions because it hasn't had time to develop. So we'll be doing some work along these lines, but hopefully we can do more of that in the future. So now I'm going to hand it over to Aishu to tell us about these other projects.
Thank you. Okay, Steve mentioned this tropical basin interaction experiment of called TBI map already. And this is a part of a project for the clever tropical basin interaction research focus, which is established, I think, in 2021 or 2020. Because of COVID, so the overall project goes kind of slow, but it is sunsetted by the end of last year, 2025. And because some of the objective of this project has been finished, but some others has not, and TBI map is one of them, which haven't really finished yet. And the protocol paper for the TBI experiment just published last year. And in order to further carry on this project, so now the TBI map is becoming a working group under the Clever Climate Dynamics panel. And it's almost official in this year. And this working group will be led by me and Dr. Lei Zhang from South China Sea Institute of Oceanology. For this project, basically, there's 3 sets of simulations for each of these basins that is pacemaker for tropical Atlantic, tropical Pacific, and tropical Indian Ocean, as shown in this figure. And in this experiment, the SIT is relaxed back to the observation, either as the anomaly of the full SST. And the tier 1 is the ones we relax to the SIT anomaly, observed anomaly. Then tier 2 is for the SST historic and the full SST. And for CSM, and we have finished both the handcast and historical pacemaker experiment. And the South China Sea group, they finished the tier 2 using CSM2. And there's also another 5 models running the same experiment. Currently, most of the models have finished the experiment, and the analysis of this result is underway. And the papers hopefully will be submitted later this year or early next year. So if you're interested in these simulations, just for historical simulation, at least how you can access this. This data has not really released to the general public. If you're interested and if you want to get the data, you can access this, but please let me know and you are planning to use them. And for the handcast experiment, you can ask Steve. I think Steve has posted the data somewhere, and you can ask him to access. If you want to use other models, experiment result, right now, Ingo, he has get some of the data to GIMSTAC. So you can ask him to get the data from other modeling group. Next one is called the TIPMAP or Tipping Pond Model Intercomparison Project. The protocol paper has been submitted to GMD. Right now is under review. If you want to know more about this project, also you can go to tipmap.org. This is a European-funded project. Underneath this project, there's currently 8 domains. They call Earth System domain, Earth system modeling domain, ice sheet, ocean, permafrost, biosphere, regional. And after these 6, there's a what if map and method, team map method. And those two, the last 2 domain actually it related to all the top 6. But at NCAR, we right now participate the ESM domain, ocean domain, biosphere, and what if. And most of the experiment car design for this project is under future scenario, idealized future scenario. Just like this ESM, the experiment basically is run model using emission driven instead of concentration driven. It have a target of 0.2 degree global mean temperature increase per decade, and then it will stabilize the climate at 2 degree warming and 4 degree warming. And then you run this 0 emission for at least 50 years, and you can run negative emission and let the CO2 concentration back to the pre-industrial level. This paper, that protocol paper is also submitted to GMD, and right now it's under review. For TMAP Ocean, we have designed 4 experiments. Last year, at this time, this experiment is still under development. Right now, it's basically ready. For these 4 experiments, the first 2 focus on Greenland ice sheet melting. So we have experiment A and B, and C is an extension of the North Atlantic hosting map project. And experiment D is for the 8.2K event, which at that time there's big freshwater runoff from the North America into the Labrador Sea region. For this experiment experiment A is in connection to the Earth system modeling part. We have designed we have this standard forcing ice in the ESM, the 0.2 degree increase per decade, and at 2 degree warming, we run 0 emission and ramp it down. At the same time, we also have the freshwater runoff from Greenland. It's ramping up from 0 to 0.1 or 0.3 threshold in 200 years. And then we run this constant forcing at 0.1, 0.3 threshold for 50 years. And then it's just freshwater forcing run down. The experiment B is related to the more realistic setup instead of this idealized simulation experiment A. Experiment B, we use the best available estimated Greenland ice melt. So we do the same compared to the historical simulation. We start from 1900 and run all the way to 2015. Afterwards, we use projected ice sheet melting and then run to 2100 at least. Right now, we propose to run the SIP 126 scenario and SSP 585 to get the envelope between the warmest and the coolest climate condition. For experiment C is we run it under pre-industrial condition and also 2 degree warming condition. We add 0.3 threshold freshwater forcing at 50 north of 50 degree north in Atlantic and including Arctic. So we run it for at least 100 years. At year 50, we switch the freshwater forcing off and see whether the AMWG will recover or not. For the 8.2K event is we just ramp up the freshwater from 0 to 0.3 or 0.6 threshold in 50 years, and we ramp it down in another 50 years. Afterwards, with 0 freshwater forcing, we run another 100 years at least to see whether the AMWG will recover. So overall, for the current TMAP Ocean experiment, we'll focus on the North Atlantic and focus on AMWG. This is phase 1 of the focus of this project. And the paper is going to be submitted, I think, by sometime in maybe late February or early March. And if you're interested in this experiment, just let me know.
All right. I think that's pretty much what we had. I just thought I'd flash this slide up again. Peter showed this yesterday, but just a reminder of various places where you can receive news about things that have been happening in CSM and the working groups. And then here's just a summary of our future plans. So Adam is working on Pythonizing CVDP, the Climate Variability Diagnostics Package, and expected date for that is this coming summer. We still have the plans to explore the impacts of the different aerosol forcings from different eras in a single forcing context. That's really just waiting on me to get my act together and make the emissions files. And I keep saying that every year and I haven't done it. I'm going to do it. And then we'll plan to perform the standard baseline simulations that we typically perform when CSM3 is ready. So we typically run an AMIP ensemble. We've been testing out new SST data sets for that. And then thinking about our contributions potentially to CMIP7, such as single forcing simulations. And then maybe there'll be plans for CSM as a whole to be thinking about a large-ish ensemble with the new model, and I think it's up for discussion at this point what that looks like. There's quite a lot of work going on with regionally refined configurations, but I didn't really mention any of it here because it's all kind of in progress. So hopefully we'll have some updates on that soon, and definitely glad to hear thoughts from you all on simulations you think the working group needs to run when we move on to the discussion session next. And just a reminder of where you can join the mailing list for the working groups to get updates on new simulations and data sets as they become available. So thanks. Any questions? We're going to have some more discussion time. So you can think of them for the next couple of minutes. Well, Mari is just going to jump in with an advertisement for a session, a proposal for a session.
Thank you. So I'm just going to take a couple of minutes of your time to suggest a working group session, a cross working group session that we would like to have at the summer CSM workshop. It's based on it stemmed from an EOS article that Laura Landrum, James Stone, and Diamond Titcher and I wrote on extreme indices. And as we were developing that, we were thinking, well, really, not only do the metrics that we use matter, but the way that we tell stories is really important. Storytelling has been around since humanity as our main way of communicating, but there's become a bit of a disconnect between the science communication and what is communicated externally. You've all been telling different types of science stories for the last couple of days, but when that gets picked up by media, that's not necessarily the stories that we want to tell. So what we would like to propose is a session where we can tell the Earth system stories from a perspective of CESM and the amazing science that it does, but also that resonates with the things and the decisions that people are making, the types of metrics that they want to know, the different types of science. So this is essentially a bit of a marketing ploy to the people who are planning the CSM workshop to say we'd love to have a cross-working group session, but then also to anyone who is attending to say, please start thinking about what your storytelling opportunities and what your science, how your science might be presented in different ways, so that we can have this discussion about what could we be doing differently? How could we do this? How can we leverage our Earth system science stories? Thank you.
Thanks. Okay, so now we are in an open discussion session. There's no real format here. Anything goes. I did put up a few suggestions of discussion topics, but yeah, we can talk about anything else. So if anyone has any thoughts on any of these things or other things, also online, feel free to post in the chat or raise your hand. And if not, then we will,
There's a MIP showcase going on this week. It's going to be Thursday, and the session that your WAWG 4 is the 9 a.m. one, and you can get it from the same 7 website and sign up. And there's actually a couple of, well, it's actually going on for a few weeks. But as all of the MIPS will present essentially their plans for CMIP 7, and community input is nice to have. So if you're interested to think about MIPS, there's also these going on for all of February. And the first one is this test.
And the other thing is you can sign up for those and get the recordings if you can't attend in person. So there'll be recording for each one of these sessions. So I've been encouraging people to try to participate in these so we can start making plans, or working groups can start making plans for the CMIP simulations that they want to run.
Yeah, that's good. Okay, question from Gaurav in the chat.
Whether there will be a single forcing runs for CSM3 anytime soon. I guess not anytime soon, but I think that would be definitely something that would probably fall under the realms of CVCWG to think about in terms of their contribution. And I would imagine chances are high that we would run single forcing simulations for CSM3, but probably not soon. And there's a strong, I'm assuming you're asking because you're interested in that. So definitely good to hear people's interests. Yeah, Danielle.
Unrelated topic, which is, what are the plans for a version for CSM3 that can be easily run in the classroom or for more educational purposes, as opposed to these very computationally intensive ones?
Yeah, that is really into what Haipan was talking about. So we've had to, it's not CSM3, but it's a
classroom, a cheap version. So the reason that we have the funding to do that CCPPizing of CAM4 and CAM5 is to make sure that we can have cheaper physics options available within the most up-to-date model that's being supported. So that would be one option for classroom purposes. We use CAM4 in the CSM tutorial just because it's cheaper. And does that answer your question, or are you looking more for lower resolution? Or
I actually was thinking, what's available out there, right? And there are reasons why something like CAM4 is interesting, but also something that is very low resolution. There's for CSM2, there is the very low resolution one, the 10 by 15. That is useful, and I was wondering if there's any plan to do something like that for CSM3.
Right. I'm not aware of a plan. Dave, do you have anything to say about that?
There's no specific plan, but we can, we need to have a cheap, there's a question of it's super cheap or a cheap and usable. Super cheap, just for education, or a cheap and usable. I think there might be different.
Yeah, they're kind of different things. Yeah, maybe the super cheap one is not necessary, but super cheap, because you can just use the old one. But something cheap to run for the community, for the broader community, would still be a relevant thing.
Yeah, we're aware. We just started having some conversations about this in the last few weeks. Among the possibilities are a F19, so a nominal 2 degree, possibly with fewer atmospheric levels. So we're going to think about that. It just depends on how hard it is to tune up. But yeah, we kind of recognize we're going to have a pretty expensive model. So having something that people could run faster with is quite useful.
About CSM, MLE, that can be a cheap model to use.
It won't be cheap. No, that'll be, yeah.
Any other thoughts or online? Okay, Brian.
There was a question from this person, Kaurav.
Oh, yeah, I think we already covered that.
Okay.
The single forcing simulations.
So Brian is asking whether we have any way to improve the workflow for generating initial conditions, and I definitely think that is a good idea. I think various people have scripts for interpolating from ERA 5 model levels onto CAM levels, and it would be good to have maybe some officially supported scripts. And then I think that was also maybe one of the barriers of using the initialized predictions in the development, is that it required some extra work to get the initial conditions, particularly in the coupled case. I don't know, Brian, do you have any thoughts on what we should be doing, or
No.
or Steve, I guess?
Easier than it is.
Here to talk about DA if it wants to.
Yeah. Do you want to say anything?
Steve, do you want to chime in about the initial conditions at all?
You know, I wish I had a good answer. I think the problem kind of depends on what your application is. If you're looking at S2S like Brian, maybe you're less concerned about ocean initial conditions, more about land and atmosphere. And I think that land initialization is one of the weak points in our workflow. I feel like we don't have well vetted land spin-up procedures. But yeah, that's my take on it.
Okay, thanks. Yeah.
Spin-up procedures and any operational center, because I wasn't really that aware of it, and obviously people do initialized prediction in operational centers. So if that's your only, may not be your only, but if that was your only stumbling block, that shouldn't get in your way.
Anyone from the land want to chime in? I guess we're not, they're maybe doing more data assimilation in the land at operational centers, and we're running offline land simulations. So that could be one difference. Did you want to?
The GEPS V13, the operational subseasonal model, which may never be operational, but if it is, they have to do hindcasts first, and they've been basically using this replay technique because they also don't have necessarily a complete, internally consistent initialization data set. I mean, they haven't done any sort of analysis with that model. So they do what amounts to a nudging, which I think you guys are pretty set up for that, potentially.
Actually, now there's a group of people working on land and air covering, which is really the.
Sorry, my hearing aids are not good enough to hear you.
Now there's a group of people. They are at NCAR and outside. They're doing this atmosphere and land covering, and specifically targeting on the subseasonal to season prediction. Because I think that was last year, and WAWG, they published a paper which showed the land utilization does not really improve the subseason to season forecast. And they want to know why. And because some theoretical studies suggest on a subseason to season timescale, land utilization should play an important role. That's why these group people.
But I think that's kind of that's an interesting question, but I think there's this larger question about whether it would be advantageous from a model development standpoint and certainly a diagnostic standpoint to routinely or semi-routinely do initialized prediction. You don't have to do decadal. I mean, most of these errors, this is what we're trying to show up in a couple of months. It can be fairly short. You could do subseasonal. You could basically have a fairly large data set. And so you do want to have an initialization, and yeah, it would be nice to have the land initialized, but if you're going to wait for that, you could be waiting till doomsday, I suspect. But certainly in the meantime, you can do a reasonable job of initialization. Even when they do land initialization in operational centers, their main concern is getting the initial temperatures right. And so that's their main goal. It's not really the land per se, it's the surface temperature. Nighttime. So, it's not, I wouldn't let that get in the way, is what I'm saying.
No, I'll just add that we do have at least samples of spun up land, which was either forced by basically a decade of the CAM6 reanalysis. So basically real weather, or it was actually spun up using observations over some period of time. So we can look at the quality of those things and the consistency with CAM and suitability for using as initial conditions. I believe last year it was reported that when some of these S2S forecasts you substituted in the CLM states that we had generated, there were significant improvements, like in the tropics over land. So we do have some products that can at least be used as demonstrations or examples, and we can generate more as they would be useful.
This is with a simulation in the land, or this is just offline but forced with the reanalysis?
It was the latter.
Okay. Okay. Are you chiming in about this topic, Judith, and then we'll go to Steve? Okay.
So, I think the problem with the land model, as with the ocean model, is that it takes a long time to spin up. And so I agree with Matt that I think our nudging technique, how we initialize the S2S simulations, is pretty similar to the replay. Maybe not as good, but not bad. And I think one of the open tenders, and maybe we're emulators of ocean and land, will help is to decrease the spin-up time so that we don't need hundreds of years or something to spin up the land and the ocean, but do that much faster, or do it via an emulator, and that would be quite helpful also for initialization of the land. Do you want to chime in about this?
Yeah, I guess, I don't know if this technique is already used by people like Judith, but I think having a fully coupled reconstruction would be really helpful across timescales. And I've wondered if anyone does that with CAM nudge to some other reanalysis, maybe using the Patrick Callahan's spectral nudging or whatever would kind of give you a fully coupled historical state. Has anyone done it?
I run a nudge simulation, but not fully coupled. But we did do it in a pre-industrial control context as well. I think that would be probably, hopefully, straightforward to do. Does anyone else want to chime in about that? Yeah.
Avoid some of the shock, right?
Yeah. You need to be careful, because if you have a coupled system and you nudge the atmosphere, you are de facto damping the atmospheric variability. And that means that your ocean will see a low frequency filtered atmosphere. And so then you run into problems with coupled modes, because you change the time scale of the atmosphere by nudging de facto.
Yeah, but I mean, wouldn't the spectral nudging help get around that?
Because you're only doing the
large scale.
Talk about this. It's not clear to me why, and GFDL has noticed this and stuff. I think we would need to nudge the ocean, but then we have the problem that we don't have that many observations to nudge the ocean. We would really need to do multi-time scale nudging.
Does this depend on the time scale of the nudging? So like, if you weekly nudged it, then you would have the high frequency variability that you're talking about. Is that true?
Still, so we went to 1 hour and we still see a signature of that damping. It's better in 1 hour nudging than in 6 hour nudging.
Well, I was suggesting the other direction. Like if you did a 48-hour nudging, like then you're just kind of gradually pushing it, whereas the kind of higher frequencies might be able to vary in the right way.
Bill Chapman, But Fei Lu Sheng from GFDL sees there's the same, Canada sees the same. And what we were trying to do, we did a perfect model. We just tried to nudge the model to its own state at one time step. And the moment we go to 2 time steps, which is 1 hour, we see the effect. And it gets worse the longer the nudging time scales are.
Yeah. Well, definitely seems like something we could look into. Anyone else have a bring up? Not, I think we're at time, so we can finish there and see you all tomorrow for the individual working group sessions. I think Elizabeth is going to send out an email. She may have done that already with the rooms that the different groups are going to be in. So see you tomorrow. Have a nice evening.